morning. Please welcome VP of Product Management, Android developer, Matthew McCullough.
Hello. Thank you for joining us at the 2022 Android Developer Summit. It's exciting to be here in person with so many of you and able to wave hello to everybody on the live stream. Today, we're going to talk about 3 themes that we're seeing across the Android ecosystem. 1, modern Android development. 2, building for a multi-device world. And 3, the latest improvements to the Android platform and getting it into users' hands. But first, allow me to introduce myself. I'm Matthew McCullough, and I lead Android's developer organization. We build the APIs and tools that you use in turn to build your apps. I'm new at Google and what they call a noogler, but I've been building developer tools for about 20 years. And I care so deeply about making developers like you more productive. I love how that productivity gives you more time to be creative and helps you build delightful experiences for your users. One of the reasons that I'm so excited to work on Android is the unique Android developer community. It's a network of resources and skills and sharing that contributes to helping one another build great apps and serve the greater Android community. For an example of what your Android community makes possible, look no further than Asan Aman, a student from Pakistan. After his mom received a counterfeit banknote, a big problem in rural Pakistan, he set out to build a fake note detector. With the help of his local Google Developer Student Club and supportive online Android developer community, he was able to create an ML-powered Android app that fulfilled that vision and is now working to scale the idea. Another example is the Android Developer Hangouts and weekly Twitter Spaces hosted by Google developer expert Madonna Wambua and Matt McKenna. It's great, yes, round of applause. It is really great to see them creating a space that brings the Android developer community together to share knowledge and help each other in an environment where everyone feels valued. And lastly, Android Developer Summit. This event is literally an expression of this community, bringing it together and sharing stories, giving shared learning, and bringing an opportunity to give feedback to product owners. Talking directly with you and hearing your perspectives helps us make Android better for everyone. So let me share a bit more about the 3 themes that we're seeing across the ecosystem and want to explore with you today. First, the platform. We're evolving the Android platform to meet users' demands for privacy, security, and personalization. We see apps in the Android platform as symbiotic and are working to enable you to build amazing apps on top of it. And we know that you want to use these features sooner, so we're working to make them available on ever earlier Android releases. Second, modern Android development. Users' demands of apps have grown, and in fact, they expect rich, dynamic, delightful applications. We want to help you build those by easily shouldering the complexity and providing powerful building blocks and sharp tools. Third, form factors. We're seeing people owning and using multiple Android devices and are expecting apps to work across them seamlessly. They want their devices to be better together and uniquely leveraging each form factor for exactly what it does best. We're seeing especially strong growth in wearables and large screen devices, and we want you to be enabled to build for those opportunities. So without further ado, let's dive into the technical content. Please welcome Ramon and Florina to take us through the latest updates in modern Android development.
A few years ago, we introduced a set of libraries, tools, and guidance that we call Modern Android Development, or MAD. And our goal is to make it faster and easier for you to build high-quality apps across all Android devices. And that's why we brought you Android Studio and Kotlin, and a bunch of Jetpack libraries, powerful Google and Play services, documentation, code labs, and a lot more. And we're always investing in every single part of the app development experience to simplify it and keep you productive so that you can focus on what matters the most to you, your apps, your business, and your users.
We want the skills you learn to be applied across the entire ecosystem of Android devices. For example, we believe that Jetpack Compose is the best way to build rich, beautiful UIs. Compose already lets you ship delightful experiences on phones and tablets. And earlier this year, we released Compose 1.0 for Wear OS, making Compose the recommended way to build wearable UIs. Compose is now taking the next step, and I'm glad to announce the first alpha release of Compose for Android TV. Components like feature carousel and immersive list are already available, and more are coming soon.
And we've heard from you that Compose is changing the way you're building apps. It's reducing the number of bugs and increasing your development speed. So now, over 160 of the top 1,000 apps on the Play Store are already shipping Compose. That's a 50% increase since Google I/O earlier this year. And it's been great seeing apps like Cash App saying they're going to use Compose for all their new features. But what's been even more amazing is seeing the reaction across the community and witnessing the incredible creativity of everything that you've been building.
But we know we're not done. So far, we released all Compose libraries together since 1.0 a year ago. But we wanted more flexibility so different Compose libraries can move at their own pace. So we started versioning each Compose library independently. To make it easier for you to manage your dependencies, we're now introducing a Gradle bill of materials, BOM for short, that specifies the latest stable version of each Compose library. We'll, of course, update it for every stable Compose artifact we publish. Our first BOM release, Compose October 22, brings many new features like lazy stagger grids, custom lazy layouts, volt refresh, variable fonts, and performance improvements. For example, in this release, we started a major refactor to the Modifier system to improve performance. We've been able to introduce this without touching public API due to the solid layering and abstractions that Compose is built upon. We're focused on making Compose performant out of the box so that your apps are buttery smooth. And
that's not all. A year ago, we introduced Material U with Android 12, Google's most expressive and flexible design system. And now, Material U 3 components for Compose are stable, and you can start using them to build fresh, beautiful apps that put your brand front and center. With Compose, you can write dynamic, efficient apps across a wide range of form factors. So we believe that you should use Compose if you are new to Android or starting a new app. And to help you and your teams on this journey, we recently updated our Android Basics training course and launched a series of Compose Camp events to help you learn Compose.
Okay, enough talking. Let's start showing. So I'm using here the latest release of Android Studio Flamingo, and I'm just creating a new project using the defaults. Okay, so usually the first thing I do when I open a project is check out my dependencies. So I'm going to go to my build.gradle file. And then here we can see that Compose is the default whenever you're creating a new Android project. So we talked earlier about the BOM. Let's see it in action. So here I'm importing the BOM. So this means that now I can just do this. And that's it. I can remove the versions. OK, we just have a grading here. Let's build some UI. So I'm going to add some code, and then I'm going to replace my greeting with my screen. And then let's see what we have here. So in my screen, I have a scaffold, and then inside I have a large top app bar. And then in my screen content, all I have is a text and a list of items.
Of course, the preview is great, but we also want to check what the UI looks like on a real device. So Florina just moved to the running devices pane, and now she's plugging in her Pixel phone. And with the new device mirroring feature, we can see and interact with the phone display directly from within the IDE. So now I'm running the app, and I can directly just scroll my list from Android Studio. So
this looks okay, but I think this would look much better if the top app bar would collapse. Well, with the new Material 3 APIs, I can do just that. So I'm adding a scroll behavior, and then in my scaffold, I'm connecting the scroll behavior, and then in the top app bar, I'm assigning the scroll behavior to the top app bar. Okay, this is much better. So now I can see how the top app bar collapses, and I can see more of my screen. Okay, next, I want to show you one of actually my favorite features that are available in Compose 1.3. So I have this text here, and wouldn't it be cool to show this as a gradient? So to do that, I'm first going to add my gradient, and then all I have to do is, in the text style, add a brush, and then in the brush, use my linear gradient. And then, yeah, I can see the gradient.
And you can see that we also have a scroll to top button, and the visibility of that button depends on the index of the first visible item in the list. So when you do a state read like this in Compose, you can create unnecessary composition, which can be bad for performance. But thankfully, we have tools to help you there.
Yes. So in the layout inspector, now we're able to see the recomposition count. So like how many times a composable has recomposed. Okay, let's try again.
It worked great during the rehearsals.
Let me see. I'm going to switch to the other machine quickly and see.
We also have studio folks in the room. Maybe they can come debug it.
So I'm just going to add my stuff. Replace this and this.
Can we switch to the other machine?
This is great. Let me switch the actual phone as well.
At least you know it's real. Unless we're faking that as well.
And in my running devices, yeah, I see the pixel. And
see, that's one good thing about the device mirroring feature. If you have to change the machine, at least the app is still running.
Okay, let's see. What does the layout inspector do there? Yeah, there we go. So now, if I'm going to my animated visibility, because this one is the one that depends on the show button, and then I'm scrolling, I can see how the number of possible recompositions is increasing here. I don't know why you're clapping. That's not what we want. We don't want that number to be that high. But luckily, Lint actually also has my back, because it tells me frequently changing state should not be read in composable functions. But not only that, it also tells me the solution. So I should wrap this with derived state of. I'm just going to replace this one here and make this a delegate. And then I'm going to enforce it and get value.
I see some people are used to that one.
Okay, so now if I'm scrolling and going to my button, okay, let's see. This is the time where you're supposed to clap. We know that you want your apps to be as smooth as possible, but understanding and fixing performance issues can be tricky. So we're adding tools and libraries to help you.
And of course, Jetpack is a lot more than just Compose. Our goal is to assist you in building and improving every part of your app with regular updates to our core library. So here are a few examples. Benchmark 1.1 helps you monitor the startup and runtime performance of your app with the introduction of macro benchmarks. And in Benchmark 1.2 Alpha, you can now measure the power usage and have detailed composition timings in your Compose code. Fragment 1.4 brings a new strict mode to automatically catch common issues about fragments. And Activity 1.6 adds support for predictive back on Android 13. And if you're already using the Jetpack fragment and navigation libraries, you don't have anything to do. It's fully automatic as soon as you upgrade the libraries. And I wish I could tell you about all the changes and improvement that the team has been making over the past few months, but I would like to focus on performance. The best performance improvements are the ones you get for free. And baseline profiles are a powerful way to improve the startup and runtime performance of your app without changing a single line of code. Using baseline profiles, you can improve startup time by up to 40%. So we are making generating baseline profiles easier with macro benchmarks and AGP 7.3. And to learn more, I encourage you to go to watch the talk, I think that's right after the keynote, called Making Apps Blazing Fast with Baseline Profiles.
Finally, we know that building an app is more than just writing code. And that's why we introduced App Quality Insights earlier this year. This feature, available in the latest version of Android Studio, allows you to see crash reports from the field and navigate to the offending code, all from within the IDE. Now available in the beta channel, App Quality Insights goes further and helps you communicate the status of issues with the rest of your team. You can filter issues by play track and quickly identify new ones requiring action. By quickly adding a note from your IDE, you can let your team know that you're on it. And then when the problem is fixed, just close the issue.
You know, there's this joke that everybody's adding stories to their product. It feels like we're doing just that. So I don't know how to feel about this. Anyway, that's the latest from MAD, with Jetpack and Compose updates, new tools, extended guidance to make it faster and easier to build great apps across devices.
Now, let's see how Zepeto shipped their app faster with Compose, and then we'll hear from Vicky and Sarah on the latest on Wear OS.
Jetpack is a 3D avatar service that has captured the hearts of over 300 million users in over 200 countries. My name is Ho-Jun Kim, and I'm an Android developer working on Jetpack. We decided to adopt Compose as we were looking for a better way to build UI. They embed scope for the coroutine, so I think Compose has a good combination with Kotlin. Compose enabled us to build a design system with organized fonts and the size in a more intuitive way and help us build more efficient code. So far, there are 330 preview functions in the project. We implemented Compose across many features. We wrote the character shop feature in Compose. It was much faster to write the feature in Compose. And we reduced the amount of code by over 10%. We rewrote our dialog component in Compose and were able to clean up more than 1,600 lines of code, which makes it easier for us to maintain. Compose reduced our development costs. Migrating to Compose dramatically reduced the time required for UI debugging. Compose simplified our UI layer logic, making it easier to understand code written by my colleagues. Compose is very easy to learn. Compared with previous Android view systems, Compose was much easier to use. The person who wanna use Compose, the person who hesitated, I wanna say, just try it.
Hey folks, let's take a look at the smallest and most personal Android device, the watch. It's a growing target for Android developers as wearables become ever more popular with users. Just last year, we launched our joint Wear OS 3 platform together with Samsung. And this year, we've seen 3 times as many device activations. We've seen beautiful new devices this year from Samsung and from Montblanc, Fossil Group, and Mobvoi, all powered by Wear OS 3. And earlier this month, we at Google launched the Pixel Watch. It's our first ever smartwatch. It brings the best of Fitbit and many of your favorite Google apps to your wrist. All of this progress has resulted in really exciting opportunities for your apps.
Wearables bring something completely unique to Android. There are sensors like heart rate, and there's payments and notifications right on your wrist. Making the most of the different wearable surfaces can increase users' engagement with your app across all devices.
Sometimes you'll create a full app, but you might want something more immediate, like a tile for a single task, or a complication that stays directly on the watch face. As you design, consider what really works on the wrist. Focus on a few simple user journeys that add value and can be achieved with short user glances and quick touch or voice interactions.
There are many tools and utilities in Wear OS and in Android Studio that make it easy to create each of these options. Let's take a look at developing the app. To make it faster and easier to build apps for Wear OS, we announced the Compose for Wear OS 1.0 release this summer. This means that the API is stable and it has everything you need to build production-ready apps. Going forward, we recommend using Compose for Wear OS to build your Wear OS app. So let's jump in and see how it works. It's really simple to create a beautiful Wear app from scratch. So I'm opening up a project I've been working on in Android Studio. I used a Compose template to get started on building a swim tracking app, because I always lose track of my laps.
Sarah is setting up the scaffold component that's tailored for the watch. Scaffold fits the time at the top of the screen and puts a progress bar on the side and keeps content perfectly centered. Compose for Wear OS has more than 20 UI components specifically designed for wearables, like time text and position indicator that we're using here. And there's even more in the Horologist library. That's our open source incubator project. These components help you develop for all Wear OS device sizes with minimal code. Now we have the scaffold in place, let's add some content. Scaling lazy column. It's one of our favorite components, despite its name.
You can add chips or cards or other components that are specifically designed for the wearable screen into the scaling lazy column. We already created some, so I just added those in.
As you'll see, scrolling the list shows a subtle fisheye animation, and the list handles content padding for any watch size with no extra work. You can see the time stays fixed to the top, and the progress indicator on the right shows the scroll state.
Now that we can scroll, and remember that default material theming is automatically applied, like this ripple effect, and you can easily add additional customization.
And of course, standard Android Studio tools work for Wear OS too, like the emulator and live edit, and the preview tool we've shown here. So you can directly deploy to a live Wear OS surface and see the results as you work.
So now that we quickly built out our UI, let's see how we could connect this to the device's sensors. We'll use health services, which is now in beta. So first, I'll declare the exercise type. So here we want swimming. And then I'll go ahead and add the data types that we're interested in.
The Health Services API makes it simple to build power-efficient apps that use data from any device sensor and from a range of calculated metrics. It's our recommended approach for building health and fitness apps. Long battery life is one of the most important things for wearable users, and Health Services is optimized for power efficiency across all Wear OS devices. So you can gather high-frequency sensor data without draining power too fast. And you can get data from complex metrics without having to write complex code.
So now that I've added all these metrics, like we have heart rate, GPS, and even swim laps, I'll go ahead and connect this to our UI, and we can start tracking. Then our app can easily collect health and fitness metrics without sacrificing any battery life.
So we've collected all this personal data from our sensors in our Wear app. Now we want to record and analyze the data over time. But how do we store the data and share it with other devices in our Android ecosystem? And how do we still keep it completely private and safe?
We've been working on a solution to make this easier, Health Connect. It's an API on the phone that we built in close collaboration with Samsung. It's a unified API for storing and sharing health data, all while giving users a single place to easily manage their permissions. So here's an example of inserting the data that we've collected into Health Connect. Once your watch app collects data, send this to your phone app and write it into Health Connect so that it can be shared securely with other apps in the Android ecosystem. Your mobile app can read data from other apps using Health Connect as well.
Wearables are a core part of the Android ecosystem, and we're constantly improving Wear OS as a developer platform. Android developers are already producing great apps for the fast-growing Wear OS user base.
Many of the developers we've been working with have seen Wear apps increase user engagement and have used our tools to reduce development time. Todoist increased the rate of installs by 50% since rebuilding their app for Wear 3. And Outeractive reduced development time by 30% using Compose for Wear OS. Some things that used to take days now just take hours.
So today, we've seen how Compose, health services, and other Wear OS features make it easier to develop for the watch. So you too can extend your app experiences to reach the growing number of Wear OS users. Check out our updated Wear OS landing page to see code labs, design guidelines, case studies, and more. Try out Wear OS development for yourself. It's so worth your time.
And now let's take a look at how Strava increased user engagement with Wear OS before handing it over to Daniel and Diana for the latest on large screens.
My name is Dave Rosenai. I'm an Android engineer at Strava, and I've been there 7 years. Strava is the leading platform for athletes. It's the world's largest sports community with over 100 million athletes in 195 countries. If you sweat, you're an athlete, and Strava's mobile apps and website connect millions of active users every single day. Investing in wearables helped us take our product and experience to the next level. Recording a run, a ride, or hike, or any activity is not convenient with your phone. For users wanting to take their experience to the next level and invest in a wearable, we wanted to bring the best of Strava to their wrists. With Wear OS 3, we let athletes access the Strava experience on their favorite wearable device. They can record over 15 sport types with real live-time performance metrics and stay safe with our Beacon safety feature that allows real-time location sharing with friends and family. And with Wear Health Services battery optimizations, they can record activities longer than previously possible. Unfortunately, living in busy areas, GPS signal is not always the best. With Google's latest technology, we're able to fall back on other sensors to compute distance when GPS signal is lost. This is a big win for our experience and accuracy for athletes' activities. Nothing is more frustrating than uploading a run or ride and having it be inaccurate. Tapping into Google's APIs, libraries, and Android tools enabled us to save time and let us take care of the little pieces, the details that'll make the experience authentic and true to Strava. Overall, we've seen Wear OS significantly impact athlete behavior on the platform. We saw increases in activity level with 25% more activities for those with a wearable versus without. Wearable users on Strava had over 30% more active days on Strava versus users who did not use a wearable. Wear OS has made major improvements. The hardware is considerably more capable, the APIs and UI libraries provide building blocks to speed up engineering, and the development tools make the process easier than ever. You can learn more about how developers like me build Wear OS apps by heading to developer.android.com/wear.
We're continuing our big changes to help apps expand to large screens like foldables, tablets, and Chrome OS. These devices are driving a generational hardware shift, changing the way users interact with Android apps on any size screen. New devices like the Samsung Galaxy Z Fold 4 and the Lenovo P12 Pro showcase recent OS updates like updated tablet UIs, the taskbar, and updated compatibility modes. Here at Google, we're getting really excited. Earlier this month, we showed a preview of the upcoming Pixel tablet. Arriving in 2023, it's bringing the best of Android and Pixel together in a tablet. And over 50 of our most popular Google apps have been shipping updates. From Photos to Chrome to Gmail, these updates are now available in the Play Store. As you explore updating your app, we're making it so easy for you to see how your app works, even if you don't have the device. Let's take a look.
Android Studio has new emulators that the Google Keep team used to rapidly iterate on their new large screen layouts. To quickly test apps on a variety of representative devices, Android Studio now includes the experimental resizable emulator. With this, you can toggle between reference devices, representing a typical phone, unfolded display, and tablet. Additionally, if you want to test your application on Chromebooks, we have a new desktop emulator as well. By default, launching your app in this emulator launches it in a freeform window, allowing you to resize the window to any size you'd like. Keep is just one example of many that has been able to leverage the power of Android Studio to build great large screen experiences.
The Play Store app is also making updates to provide a better experience for users on large screens. We're redesigning the store listing and home pages with beautiful layouts that show off how awesome an app can be on the larger screen. As you work to optimize your app, updating your listing with screenshots and videos means you can take advantage of these richer formats. We're also making changes to help users find high-quality apps. On these devices, ratings and reviews will be specific to users on tablets and Chrome OS. Apps that support large screens will also be easier for users to discover in personalized recommendations, collections, and editorials. And optimized tablet apps will be available for users to browse and install across devices, downloading an app to their tablet directly from their phone. With these opportunities in the Play Store, we're excited to see many apps taking advantage of large screen-specific layouts and use cases. Canva has added updates like drag and drop when there are two apps on the screen to create new files. And Concepts enables amazing stylus interactions like drawing and shape guides for Chrome OS and stylus devices. They see a 70% higher usage on tablets compared to phones. We've learned so much from developers like you around how your app can take advantage of the larger screen, that today we're launching a new gallery on developer.android.com with app designs and guidance. This includes high-fidelity mockups, links to material design guidance, implementation guides, and case studies from real apps. We have examples of how a media app can scale video playback, or how shopping apps can display more products as the screen expands from a phone to a desktop device. If you want to know how to implement messaging responsively and get examples of what it should look like, you start here. Beyond the guidance, we've also got more tools to help you identify design issues. Let's see how.
We know it can be challenging to stay current on best practices. Don't worry, we're bringing that info directly to you in Android Studio. Switch over to the next demo. Here's an app we built with views using sliding pane layout. Updates to the layout editor now show me the same 4 reference devices you just saw in the resizable and the desktop emulators. By designing the UI to work well across these 4 reference devices, your application will look good in nearly all display sizes. While reference devices in the layout editor ensure I don't need to own every single type of Android device, I still want to keep up with evolving UI best practices. One of my favorite new Android Studio features is the new visual lint feature provided in layout validation. Go ahead and open layout validation. We built this tool to flag the most common large screen UI issues directly in the IDE. For example, here's a warning recommending that I use a vertical rail instead of a bottom bar for navigation on larger devices to improve reachability. Let's go ahead and fix this in my large screen layout. First, I'll add the nav rail, and I will adjust the margin of the content to account for the new nav rail. And then I will remove the bottom bar. Oops. And voila, I can see the warning has gone away. And I can quickly preview the updated UI on each of the respective devices.
So updating the nav rail and 2-pane layouts are a great first step that we've seen many apps adopt. Facebook has recently updated to a vertical navigation rail with a tablet layout, as well as the ability to launch Messenger from Facebook directly into split screen. Instagram and WhatsApp have also recently added tabletop mode for video calling on a foldable. Whether you're working on an existing multi-activity-based application or building a new app with Jetpack Compose, we're working to make updating layouts less work. We've released new APIs like activity embedding, window size classes, and Jetpack Compose support to make it easier to build responsibly. Speaking of Jetpack Compose, let's see how Android Studio can help Compose developers.
Switch over to the Compose app. So the Now in Android app is a sample built with Jetpack Compose and Kotlin that shows recent Android developer news and updates. As part of the stable Material 3 Compose release, we have a new library that provides the easiest way for Compose developers to adapt layouts to window size classes. With just a single function call, I can get my window size class layout breakpoints, where I can then use Kotlin conditional logic to determine or to change my Compose layouts. You can use these breakpoints directly in your Compose tree, or you can set Boolean values, as we've done here, to determine which navigational element to show, such as only showing the bottom nav bar on compact displays. Additionally, with Compose, the same 4 reference devices you saw in the previous demos are here as well, this time with the Compose multi-preview feature. This lets you configure your multi-preview configuration just once and reuse it in all your layout previews to detect and fix UI issues impacting all screen sizes. Throughout your development journey, we're making it easier for you to support all screen sizes within your existing workflow.
So, with our upcoming devices, Play Store changes, new guidance, and updated developer tools, we've got so much to help you update your app for large screens today. Now, over to Charmaine and Dan to tell us about what's new in the Android platform.
With updates like the taskbar, activity embedding, and compatibility mode, Android 13 delivers an even better experience on tablets. But there's so much more to Android 13, with enhancements to personalization, privacy, security, connectivity, and media. More importantly, we're using a variety of technologies to allow you to deploy these features to earlier Android releases. Dan and I will walk you through some of the many ways you can take advantage of these technologies. Starting with personalization. The world is multilingual, with people often communicating in different languages in different contexts. With Android 13, we've introduced per-app language preferences to improve the experience for multilingual users.
All right. I'm going to reset my Git demo here. So we are going to go back and start demoing here. Let's see if we can actually get this to run for you guys. So enabling per-app language preferences for apps running on Android 13 involves adding a locale config XML file and a locale config attribute file in the Android manifest. Now, this means that Android users on Android 13 get the setting in a very consistent and discoverable place, but we can do better. And building a custom in-app language picker that synchronizes with Android 13 settings like Google Maps has done gives Android 13 users the best experience while letting everyone use per-app language settings. All right, now to the demo. Now, I've added some language-specific resources to the Affirmations app from our Android Basics with Compose class, along with a Compose custom language picker dialog. Now, I've implemented this using the Android 13 APIs, but the app compat version is actually even simpler, and it provides backwards compatibility. So I just changed this to locale list compat over here, and this is where we take the locales that we're setting, and then I can call the app compat delegate to set the locales, then I get rid of all of this, like, SDK version checking that's sitting here, which is cool. And then we actually have to go and make one more change. So one of the cool things that this library can do for us is actually store the locale setting on our behalf. So I just put a service definition here in the Android manifest file, and that will happen. So let's stop this so it doesn't actually say, sorry, you've changed the manifest, and run it again. And now we have implemented a per-app language picker that runs on every version of Android that it supports, and it synchronizes the setting for Android 13.
All right, let's switch gears and talk about privacy. If your app needs to get a selection of the user's images, like when choosing a profile picture or sharing a post on social media, you can call the new Photo Picker API. Using the Photo Picker is a privacy-friendly way to allow the user to select photos and videos they explicitly want to share with your app. And in the upcoming months, the picker will also include media the user has stored in the cloud.
Now, to begin our integration of the Photo Picker, we create a pick visual media request. by registering for an activity result with the pick multiple visual media result contract. And this returns a callback that gets the returned content URIs. So I'll go and set these into my ViewModel. And then we have to actually go to launch this thing. So one of the things we can do is is photo. There we go. Is photo picker available? I can do this. I can type. There we are. I type. And is photo picker available? And then we can launch it with the type of media that we actually want to select. And this can be photos and or videos. So let's run this thing one more time. And with that, the photo picker can actually be used to replace these beautiful images that Romain Guy has with something a bit more whimsical. Now, Photo Picker is supported back to Android 11 using an SDK extension. And this is a technology that uses Google system updates with modular system components to add functionality to an OS release. Is Photo Picker available internally calls get extension version, which, by the way, is how you check for the presence of an SDK extension at runtime. If the photo picker isn't available on the device, the support library automatically invokes the action open document intent, which isn't quite as rich of an experience, but also functions back to API 19 without requiring additional permissions. So in many cases, your app will no longer need a runtime permission at all to access user-selected media. Now, new to Android 13, you can also tell Android to revoke any held permissions your app no longer needs. Your longtime users will appreciate how you've been considering their privacy.
Android 13 also introduces a notification permission to give users easy control over which apps can send you notifications. This happens regardless of what API level you are targeting. However, targeting Android 13's API level 33 allows you to improve the user experience, with control over when the permission request happens, the ability to provide more context, and the chance to requery the user. To help you target new API levels, we're introducing the Android SDK Upgrade Assistant tool within Android Studio.
All right, so in the Upgrade Assistant, you select your upgrade path, and then you get this step-by-step documentation for the most important changes you need to consider when migrating. So for example, when migrating to Android 12, you'll see, okay, here's what I need to do for Bluetooth and location and intent filters and important things like foreground service launch restrictions. And what we're launching with Android Studio Flamingo here is just the beginning. We're working to provide contextual filtering along with auto migration to be even more helpful in the future.
With updated Android Studio tools, backwards compatible app compat libraries, and the use of SDK extensions within the platform, we're making it easier than ever to adapt your app to platform changes, while enabling you to take advantage of the latest features Android has to offer. With that, I'd like to invite Matthew back to the stage.
Hello again. Thank you to my colleagues Florina, Romain, Sarah, Vicky, Diana, Daniel, Charmaine, and Dan. Thank you very much. From modern Android development to wearables, foldables, and large screens, and from Compose to platform updates, even after 14 years, we still have so much progress to share every time we come together for ADS. It makes me feel honored to have been welcomed into a team that works so hard every week to support our developer community. And that's you, ADS audience. We're here to listen and to serve. And we have even more learning opportunities in store. Next up, we have talks themed around modern Android development. And in the following weeks, we'll have a live stream track from form factors on November 9th and one for platform on November 14th. And then we have visits also to Bangalore and Tokyo in the month of December. So join us now and drop your mad questions into the YouTube comments or on Twitter using hashtag AskAndroid. And tune in later today to see if we answer your questions live. From the experiences you build for users to the feedback that you give us to help make our tools better, thank you. We appreciate you taking the time to join us today and look forward to chatting more during the rest of Android Dev Summit 22. Thank you so much for joining us.
Please welcome Android Developer Relations Engineer, Simona Stanovic.
Hi everyone, my name is Simona Stanovic. I'm an Android Developer Relations Engineer working on Compose. Unfortunately, it's going to be just me on stage today because Rebecca couldn't make it. So, today we're going to combine two Compose UI forces, custom layouts and graphics, to build a seemingly complex design in Jetpack Compose in just 20 minutes. So our approach today will be more of a hands-on, where we'll get to build a mind-blowing, super fun, and extremely original and creative design of a graph. But we're going to make it pretty and fun, I promise. This is going to be a sleep tracking app called Jetpack. So let's begin with the first part, custom layouts. This time graph will be the custom layout that we want to build. So how do we build this? Let's break it down. The x-axis of our graph shows the hours of the day. The y-axis shows the days. And lastly, the bars represent the sleep hours for each day. Now, there is a bit more. If you tap on a sleep bar, it expands to show a bit more info. So when you break down a design like this, you might think that there's a lot of ways of achieving it. And you might be wondering, why go with the custom layout? Can't I use existing composables instead? And to answer this, let's see how these three graph components work with each other. So day labels need to be positioned at the start of the screen, but beneath the hours header. The hours header needs to be at the top of the screen, but after the day label. Each sleep bar is differently positioned, taking into account the start offset and the sleep duration, and it needs to be placed in line with the day label when it's collapsed, as well when it's expanded. So TLDR is, we need a lot of coordination here. And every component needs to know the exact info on all of the other elements for its own sizing and placement. So this is a perfect use case for a custom layout, because in Compose, custom layouts give you the full control over manually placing and sizing its layout children. This means that our graph or our custom layout will actually have 3 responsibilities. Calculating how many day labels and sleep bars are needed. Now, the hours header at the top is only going to be 1 composable, so nothing to calculate here. Measuring all 3 components, and placing all 3 components. Now, let's first define the graph's input. As mentioned, our 3 components are the hours header, the day label, and the sleep bar. Now, for simplicity, let's imagine that these come as the following composables. A single row composable containing all of the hours, a single text composable for 1 day label, and a single box composable for the 1 sleep bar that we have. Now, we can actually use this information to define the parameters of our graph. However, to know how many day labels and sleep bars we have, we also need 1 more parameter, which is the total count of the sleep bars or days, or simply graph rows. Now, when we multiply the day label and the sleep bar composables with this total count, we get 2 lists of composables instead. As mentioned, the hours header is just at the top. It comes in as 1 composable, so again, nothing to calculate here. Now for the second step, measuring all components. Every custom layout starts by calling the layout composable. And this composable is actually the key core component of the Compose layout system. It accepts composable content for laying out the children, and as well the policy for measuring and sizing these same children. So all higher level layouts like rows and columns are built on top of this composable. Now, for our graph, we'll actually use a new and handy overload of this layout composable, which accepts a list of content. Now, the layout composable is actually the main protagonist of the layout phase in Compose. And this phase consists of 2 steps, measurement and placement in that specific order. Sizes of child elements are actually calculated during the measure pass, while their positions are calculated during the placement pass. The order of these steps is enforced with Kotlin DSL scopes, which are nested in a way that prevents placing something that hasn't been first measured, or doing the placement phase and the measurement phase. Now, during measurement, the layout contents can be accessed as measurables, or components that are now ready to be measured. Now, let's think about which component needs to be measured first. Elements that can be independently measured in our graph, meaning that their size isn't impacted, are their size isn't impacted by any of the other components that we have in the layout, are the hours header and the day labels. Now, we know this also because we let these composables define their own sizes when we pass them as input. So our layout only needs to take in those sizes as the main source of truth. Now, let's start by measuring the hours header first. Inside layout, all measurables come as lists by default. So we grab the first element from our hours header measurable because we know that there's only 1 coming in. And then we measure the header as it is, without changing its predefined size with incoming parent constraints. This in return gives us an hour header placeable, a component that is now ready to be placed. Following the same pattern, we take the list of day label measurables, and we measure each label 1 by 1 with incoming parent constraints, keeping its original size. Again, in return, we get a list of placeables that are now ready to be placed. Now for the sleep bars. Let's figure out how to measure these first. Each sleep bar width is based on the total sleep duration for that specific day. Now, we need the duration in the measurement phase to be able to calculate its width properly. We also need to know the hour when the user went to bed as the starting offset of that specific sleep bar. We need this offset in the placement phase to know where to place the bar. So for each sleep bar measurable, we need its duration inside the layout to measure its width properly. But we currently don't have that information. So to solve this, Compose actually offers a very handy API called Parent Data Modifier. Now, Parent Data Modifier actually enables child composables to pass data to the parent layout, which is then used for actual measurement and sizing of the specific child. Or in our case, every sleep bar actually needs to pass its duration and offset upwards back to the parent. And this will actually help measure its width and position correctly. So let's use this API. So first of all, we create this time graph parent data class, and we override the parent data modifier interface. We override its modify parent data function to pass the duration and offset wrapped. So now we have the actual package, but how do we ship it back to the parent? For that, we actually create a custom modifier which accepts input from the sleep bar and uses it to then pass the duration and the offset. We then wrap this in a parent data to ship it back to the parent layout. We apply this modifier to each sleep bar when we are passing it as input, and that's all. Now our parent actually has the information that it needs. So when measuring the sleep bar width, we actually paused because we didn't have the duration, and now we can get the duration from the parent data property, which was previously passed via the modifier. Use it to calculate the bar's width. We then call measure function for each sleep bar, passing in the new constraints. Once measured, we get sleep bar placeables in return. Measurement done, let's move on to placement. Let's determine which components need to be placed independently. Now, the hours header is independent because once it's measured, it just needs to go at the top of the graph. The sleep bars are placed one after another with a starting offset, and the day labels might seem like they're independent, but do remember, when we tap on them and expand them, they need to stay in line with the matching day label. So the day labels actually have some dependencies for placement. The placement step starts by calling the layout function and entering the placement scope. Now, the placement scope now allows us to use all of the placeables that came as a result of the measuring pass. To start placing children, we first need the X and Y coordinates. X position starts where any of the day label ends because they're all the same width. Y position actually starts where the header height ends. We then take the hours placeable and place it at the position of X position and 0, which is the top of the parent. Next are the sleep bar placeables. Every sleep bar needs to be placed after its starting offset. If you remember, the offset is actually the second piece of information that we were getting from our parent data. We use this offset to calculate each bar's X position and then place it, but we're actually not done yet with this specific step. Remember that we said that the delay label needs to stay aligned at the top when it expands? So to achieve this, we'll actually place the day labels in the same iteration as the sleep bars, because their placement is coupled and they require the same Y position. Using the sleep bar index, we find the matching day label. We then place it with the position of 0 and Y position coordinates. And lastly, we increment the Y position by the current bar height so that every other element comes beneath it. Placement done. So if we run the app now, this is what we'll get, and we can verify that our graph is looking really good. Great, so now that the custom layout part is done, let's move on to drawing the sleep bar details. The sleep bar currently is drawn as a rounded rectangle with color, but to match our designs, we need its initial state to actually have an emoji representing the sleep score, and the expanded state to show a bit more info. Looking at the expanded state design, the offset and the size of each rectangle is based on the duration of sleep. The sleep periods are connected together with lines, and there is a gradient representing different sleep periods. Now, to draw something custom in Compose, we have different options for different purposes. For example, modifier draw behind draws the content behind the content of the composable. Then we have draw with content, which specifies the order of drawing details. Draw with cache caches the content until the state or the size actually changes. We then have the canvas composable, which is just a wrapper around modifier draw behind. And finally, the graphics layer, which applies effects to composables that is already drawing something on the screen. For us, we will actually use the modifier draw with cache because we need the brush objects that we're going to create to be cached. Now, to draw the sleep bar, we can use any composable here for drawing, but we chose a spacer because we don't need any other content to be added to the screen, and the spacer actually doesn't render anything. Now we have access to the onDrawBehind function where we execute the drawing commands. Now it may look like we don't have a canvas object here to call the drawing functions on, but inside this onDrawBehind function, we're actually in something called a draw scope. Now, what is a draw scope then? Draw scope is Compose's answer to declarative stateless drawing, where you can call drawing functions without needing to maintain your own state. And it's a much nicer API than using the onDraw method in Canvas, as it handles a lot of the complexities for you. Now, if you remember the moments where you needed to save and restore state with Canvas before, those days are luckily over. In the definition of the draw scope, you can actually see that it has a bunch of methods for drawing. And we can get also this, access to the size and the center of the drawing areas, which are particularly useful when adjusting the sizing and the placement of an item. So let's get into it and draw the bar. Now that we know how to use the draw scope, we can actually get our design back to a rounded rectangle with a gradient. We call the draw rounded rect with a gradient brush to get this fading effect. We could also use a color here because there are multiple overrides of the draw functions that take in both brushes and colors. Now running this code, you can see that the sleep bar is now drawn in a rounded box. The next thing to do is to draw the sleep score emoji. And this is actually text, so let's learn how to actually draw text on Canvas. New APIs have been added in Compose 1.3 to cater for this specific purpose. Back to the code. So, to draw the text on Canvas, we actually need to create a text measurer. We provide the emoji string that we want to draw, and then we call the measure function. We call draw text then with the result of the measuring string, and this draws the text at 0, 0 coordinates of the canvas. We can also customize the text size, alignment, and other properties, but for our individual purposes, we don't really need to because we just want the emoji there. Now that we have the emoji at the top of the bar, this is looking pretty good so far. Now we have the non-expanded state implemented, but we want to also implement the expanded state. Now, this looks like a pretty complicated design, so let's break this down. The first step is to increase the height of the sleep bar composable on click. Animating the height of something that on click actually requires us to create an expanded variable and use it for determining this height. Back to the code. First, we create this isExpanded Boolean, and then we toggle its state on click. Now, to use this expanded state with an animation, we can actually create a changing height value. We create the transition objects to coordinate multiple properties that should animate when the expanded state changes. In this case, we're only animating the height of the item. Great, so now the size of the bar increases on expansion, but we actually need a few more bits there. Next step would be to draw the sleep periods with interesting path logic. And this is where things start to get a bit more complicated. We can see that the expanded state shows time spent in each type of sleep. Whether it's awake, REM, light, or deep sleep, they're all connected together. These rects are also rounded, as there is also a vertical gradient across all of the bars and parts. Now, instead of the rounded rect for the whole bar, we want to draw a path that we generate by iterating through each sleep period. This path will be used for both expanded and the non-expanded form. For each sleep period, we actually check if there's a previous sleep period, and we keep track of this variable as we iterate. So if there is a previous period, we call the path line2 to draw a line between the start and the end of these periods. Now, the next thing to do is to add the current sleep period as a rectangle to the path that we're going to draw. The rect size and the offset are calculated based on the duration of sleep period, and each bar gets a vertical offset on which, dependent on which type of sleep it actually is. Then we call path move2 to move the path to the start of the next line. We move it to the right of the rect that we just added, and path move2 doesn't actually add any lines to the output that will be drawn, it just instructs where the next drawing command will be executed from. This process is then repeated for each sleep period, building the path that we draw. So drawing a line, then a rect, then moving to the point, then drawing a line, then a rect, then moving to the point again. So we have our generated path, and we can now call the draw path in our previous scope, applying the vertical gradient brush with different colors. Great, so we have our bars drawn, but where are the lines that we generated? The default for draw path is to actually use draw with a fill style. And for our purposes, to get the lines drawn, we actually need to draw the same path with a stroke style. We can actually customize the stroke to set the rounded corners and run them based on how far the expanded animation has progressed. And there it is. Now it's looking a bit more like hard design. So we have the info shown on the bars, and you can notice that the height animation actually hasn't changed here. The difference here is that we're no longer actually drawing the original rect, but the segmented path in the collapsed state. But we're actually still missing that final magic touch. We want to make our background a bit more dynamic by adding these yellow wavy bars to the top, and we will actually use shaders to do this. Now, previously to use shaders on Android, we needed a surface view with OpenGL, but now with AGSL, shaders can easily be incorporated into DrawScope drawing calls. AGSL stands for Android Graphics Shading Language. It's based on GLSL, and it runs on Android T and up. Now, shaders also run on the GPU, so they perform individual pixel calculations in a very efficient way. So we have our shader that now we're taking from online shader tool. Let's see how we can actually integrate this in Compose. On the Jetpack screen, we actually want to draw this as a background to the top of our bar. And then what we do is we take the actual shader from one of the online tools with a few adjustments to make it fit the AGSL language spec. And this is a bit complicated math, so we won't get into this right now. We use Modifier's draw with cache on the column, as we want the shader and shader brush objects to actually be cached. In order to compile our shader, we actually create an instance of the runtime shader, giving our AGSL string as input. And we then create the shader brush with the shader input. We set the resolution of the shader to the width and the size of the drawing area. And then we call drawRect and onDrawBehind with this shader brush. And this will actually draw our background without any movement so far. So we can see the static result of calling this drawRect with our shader. But as we mentioned, there is still no movement. So let's fix that. In order to add movement, we actually need to create the animation and pass the animation time into our shader. We will actually start this by creating a time variable that increments itself using this following function. And this will be updated on every single frame. We then set the uniform variable of our shader to take in this time that is being constantly updated. So let's see what this looks like now. Great, so now our shader actually applies movement over time, hopefully making you a bit more peaceful and feeling a bit more relaxed when you see it. And yeah, that's it. So today we've actually learned how to do some pretty custom things in Compose, using custom layouts and its own measuring and placement logic, drawing bars in a very dynamic way, and also we've learned all about different graphics APIs that are available to you to draw and animate custom things. So in order to take a look at the code, take a look at the Jetpack sample that we have, and for more information on layout and graphics, you can look at the following resources. That's it. Thank you.
Good morning, everyone. My name is Rahul, and I'm an engineer on the Android Toolkit team.
And hi, I'm Tomasz, and I'm engineer on the developer relations team. And today we're going to talk about how to make apps blazing fast with baseline profiles.
So far, we've announced baseline profiles early this year, and we have about 250,000 apps publishing with baseline profiles on the Play Store. This was even before some of the toolchain for building and publishing with baseline profiles was ready. Now that everything's ready, I'm going to make a claim. You can probably make your app at least 30% faster if you use baseline profiles. The reason why we are so confident will become clear once you understand how code execution evolved in the Android platform. We look at execution in 3 dimensions. First is initial performance. This is performance after an install or after a process cold start. Second is eventual app performance. This is performance after the runtime has a chance to discover some hot paths in your code, for example. And third, we'll look at the cost of these optimizations in terms of additional disk space required. In Android 1, your code was interpreted. So the runtime, initial performance was slow. Eventual performance was also slow, but importantly, we didn't use any additional disk space. This is because we didn't really do much to optimize your code. There's nothing to save. This was a key consideration back then, because disk size in early devices was really hard to come by. In Android 2, we introduced Froyo, we introduced a just-in-time compiler. This additionally, so even though your code started off in interpreted mode, the just-in-time compiler would discover hot paths and optimize them. But those optimizations got thrown away once the process died. This is, again, a key consideration because disk space was paramount. In Android 5, we decided to do something slightly different. We introduced full AOT, or ahead-of-time compilation. The way this worked was, after app install, we ran a new compiler called dex to oat. And this converted your dex code to optimized dex file. So we compiled it at install time. And once the user interacted with the app, they only loaded the odex files, which is the compiled code. And as a result, the user saw the performance improvements. Now, 2 caveats here. First, we introduced a new compiler, dex to oat. Remember, this is running on a resource-constrained device. So this is not particularly fast. Also, we are optimizing the entire app. Second, there's the cost of storing that compiled code. This also gave us this dialogue. Anyone remember this? The reason why this happened was every time we introduced a new optimization, we had to compile every single app on the device to take advantage of those optimizations. So this was clearly not ideal. Going back, we improved some performance characteristics, though. So we made app launch faster because we have a new compiler. We made disk size a bit worse because now we have the cost of storing that compiled code. So in Android 7, we decided to do something that took advantage of the best of both worlds. So we wanted to not compile the entire APK because that was slow. And we wanted to identify the important parts of the app. So to do that, we went back to a hybrid between just-in-time and compiling the important parts of the code. We called it profile-guided optimization. And the way this worked was you start off the app in interpreted mode with the just-in-time compiler like you saw before. But instead of throwing those results away, we would store them additionally in a file called profile. And profile is just a list of classes and methods that are important for us to convert to machine code to make sure the app is fast. Once the device was idle, that compiler that you saw before ran in something we call background dex-opt. So we would only target the methods and classes in the profile, and now we would only conditionally compile them instead of compiling the entire app. This was much faster because we knew exactly what parts of the app are important. And when the user was interacting with the app the second time, we have the odex files and dex files, and given we've optimized the important parts of the app, the user sees the benefits in performance. And not only that, this process repeats again and again. So as the just-in-time compiler discovers new hot paths, it can dump them into the profile. That can be picked up by subsequent passes of background dex-opt, which is great. So let's look at the table now. So we've improved disk size usage because now we are no longer compiling the entire app. But now we have a mix of slow starts and fast starts. Right? We have slow starts because your code starts off in interpreted mode with the just-in-time compiler like before, and then eventually gets fast. So if you were to plot app startup time and days since install, you would see something like this. As the just-in-time compiler knows more, it optimizes more, app launch typically gets better. It's not just that. This story repeats on every single user device, right? It's more like this. So every time your app is installed on a new device, we start from scratch. But wouldn't it be nice to take advantage of profiles that are computed on devices that were similar to yours but not your device? So trying to crowdsource this profile information. That's exactly what cloud profiles are. So in Android 9, we introduced cloud profiles. The idea is to identify common traits in profiles on a device that were generated on a device similar to yours and on a platform version similar to yours. And we start aggregating them, right? So we identify those common traits, and we upload that aggregated profile to Google Play. Once we have enough of those profiles, that profile is then provided to the app at install time as APK metadata. And then new users will see the benefits, and they'll see a much flatter curve. This is because we took advantage of profiles from other devices, and then we used it on new devices, right? So this is great. One caveat, though, the profile aggregation can take several weeks, because it really depends on how often your app is used and how many users you have, for example. So the more users your app, the more passes we have at background desktop, then we can build a better profile. Let's revisit that curve. So now, if you look at performance characteristics, we have a new caveat here, which is every time you release a new version, we don't have profiles. And so we have to start over again. This happens every single time, right? Every new version. So if you've seen something like this before, we're sorry, but now you know why. OK, now let's go back to the table. We've improved on initial performance, because now we have cloud profiles from other devices supplanting profile information generated on your device. So let's look at the curve again. This is the curve as it stands today during Android 9. What we really want is this. We want app startup to be fast in the beginning, and we want it to remain fast. That's where baseline profiles come in. Baseline profiles are a way for the app to provide what is important to the runtime. So it's a way for you to bundle that information into the APK itself, and we consume that at publish time and app launch time. It's not just for apps, though. It's also for libraries. So when a library like Jetpack Compose declares baseline profiles, all consumers reap the benefits, and they can take advantage of it. And finally, I want to stress that the toolchain is now stable. So if you've seen problems before, you won't run into them anymore, I promise. And it should be a much better experience. Baseline profiles can be backported all the way to Android 7, because we can take advantage of some of the same toolchain, Dex to Oat namely, and we can backport a lot of the same functionality all the way to Android 7. That covers approximately 95% of the device population. And so we solve the slow start problem, because you're telling us what to optimize ahead of time, and then we give you great performance to boot. And if you include Android 5, which does full AOT, that means profiles are used in 99% of the device population. So that was a lot of theory, and now I'll hand it off to Tomasz, who can show you how to generate them.
Thank you. OK, to get started with baseline profiles, you can use Jetpack Macro Benchmark library to generate them. You write a simple instrumentation test, let's call it baseline profile generator, in which we'll use a baseline profile rule that will provide us all the necessary scaffolding. And we write a test method, generate, in which we use collect baseline profile method from the rule. It requires two parameters. First, the package name of the app you want to generate the profile for, and second, the profile block lambda, in which you write interactions of your app. As part of the interactions, you should cover your most important user journeys of your app, such as app startup, scrolling the feed, adding stuff to the basket if you're an e-commerce app, and stuff like that. But also, you may cover journeys that are not called as often, but are worth optimizing. This could be a user login flow, sign-up flow, etc. That's because these journeys may not be covered with Cloud Profiles soon. But also, if you've got some kind of A/B testing in your application, you may consider covering both of the scenarios, because the slower performance of one of the scenario actually can affect the metrics of the A/B testing. All right, let's write some interactions for the Now in Android sample app. We'll start with start activity and wait. This will start the default activity of your application and actually waits until the first frame is rendered. Once the code of your app is executed, the library takes care of capturing all the called methods and classes in the background. Next, we wait until the content is asynchronously loaded and ready and shown on screen. And again, once the test is executed, the code will be collected again. In our example, scrolling the feed will be one of the most used features. So we find the feed on screen, and and we scroll it with the flick gesture. Again, triggered code will be collected in the background. So once the test is done, all the reference methods and classes are saved on the device in a text file. The file looks something like this. There's no magic there, just some classes, methods in a human-readable form. You can read it, but you definitely don't want to write it yourself. So that's why we recommend generating it with macro benchmark library. And this file basically is the baseline profile. So next, you just need to copy the file into /main folder next to the Android manifest and name it baseline.prof.txt. And that's it. Next time, later, when you build the production version of your app, if any dependency you use has a profile, it will be merged with the one you just generated and included into app APK or app bundle in a compressed binary form so that it doesn't take a lot of space. And then you can just upload it to the Google Play, where it's processed for various device versions. Once uploaded, it can be distributed to your users in two ways. The first and most optimized way is when you install your application on Android devices running 9 and through Google Play. That's where the cloud profiles also can be distributed. So in this case, when your users install the app for the first time or they update it from the previous version, it will download the APK and also the processed baseline profile. And on device, the package installer installs the APK, and it uses the included profile to run a targeted DEX optimization at install time. And that means that the optimized DEX files are generated even before the app is launched. And users see the performance benefits from the first start of your app. But also on Android 7, that's 7 and between 9, the package installer doesn't know how to install the rules. So we've got a fallback for that. And not only those versions, but also like if you don't ship your app through Google Play on other services, that will work as well. The only thing you need to do is add Android X profile installer dependency to your app. So in this case, when users download the APK with baseline profiles, the package installer installs the app, but it doesn't optimize it immediately. So when user opens the app after the install or after the update, it runs in interpreted and just-in-time mode, as before. But also, the profile installer knows where the current profile, where the profile is, and what format it needs. And so we save the included baseline profile rules there, similarly as the just-in-time compiler would over time. And later, when the device becomes idle, the rules from the profile are compiled, and we'll get the optimized text file based on the baseline profile rules. So next time the user opens the app, it'll be optimized and run fast. This means you should always add the profile installer to your dependencies. Now, let's see how to verify the benefits of baseline profiles. There are two ways. The first option is you can check your field metrics. That is Google Play Vitals, Firebase Performance Monitoring, or any other service you use for metrics of your app. You should see improvements of your app startup or smooth experience, but that's only after you ship the version of your app. To check it in the lab environment, like on a CI or locally on a device, we can use the same Jetpack macro benchmark library. So again, we write an instrumentation test, and we use this time macro benchmark rule from the library. This will provide scaffolding for benchmarks. And in this case, we write a helper function, startup, that we'll use in our tests later. It'll use measure repeated method from the rule. We need to fill in all the necessary parameters, that is how many iterations, what package to start, and what metrics you care for in the benchmark. So we care for the startup timing metric. But then we'll also write one optional parameter of the method, which is compilation mode. This will help us distinguish between when the app uses a baseline profile and when not. And last thing, we write a measure block lambda, in which we specify the interactions with the app similarly to the baseline profile generator. So here we've got press home to start the app from the launcher always. We've got start activity and we wait until the content is loaded and ready to use. Now that we've got the helper defined, we just write two tests. One that uses compilation mode none, that that runs the app in the unoptimized state without baseline profiles, and one that uses compilation mode partial, which partially precompiles the application. We should run these benchmarks on a physical device. If you can, run it on the most frequently represented device so that you see the impact for the majority of your users. The results come directly on Android Studio output pane. You get duration in milliseconds, so you get slowest, fastest, and median startup time. So in our case, what we can see is that the app started over 100 milliseconds faster with baseline profiles, which is 40% improvements. That's even bigger than Rahul said in the beginning. And the slowest run was even longer than that. The other way to look at these results, or verify if they work, is with system tracing. Micro-benchmark records system tracing of every iteration of the benchmark. And it provides the traces within the same system, within the same output pane. So you can just click on the first iteration of the compilation mode none, and it will take you directly to the system tracing profiler. So let's do it. So here, we've got the compilation mode not, and we can see that in the system tracing profiler, there you could see a lot of information. But what we want is we'll search for the JIT thread pool. That's the bottom pane. We can see that during the startup, there was a lot of work executing, and that is the just-in-time compiler compiling the interpreted code. So that's the thing that is doing. If we open the other test, the trace from the other test, from the compilation mode partial, we would see that in the JIT thread pool, there's almost nothing happening there. And that's because the code is already compiled before the app startup. And that's the massive performance boost you can get. You may see that there's still some tiny speck here that can happen sometimes. But with system tracing, you can investigate more, and you can improve the profile generator so that next time it covers actually it. Now, performance is not just about numbers and metrics and profiling. It's actually about the actual user experience. On the right side, we see that with baseline profiles, the app starts faster. But it's not just about app startup. It's actually about smooth experience as well. So the app scrolls smoother, animations run smoother. So the performance gets better in any case. And bear in mind that we didn't have to rewrite the app. We didn't have to change the architecture of our app. We just had to write an instrumentation test and follow a simple process. Your new users will get better first impression of your app, and existing users will get consistent performance. There are some links you can follow for more information. We're here later to answer all the questions. Now go and make a baseline profile. Thank you.
Hi everyone, I'm Takeshi. I am a developer relations engineer for Android developer tools.
And hello everyone, I'm Paris. I'm a product manager also on the Android developer experience team. Today, along with Takashi, we'll walk you through the state-of-the-art of Compose tooling in Android Studio. Through a typical UI development workflow of design, develop, and debug. We'll share our favorite Compose tools in these 3 different stages. Specifically, in the design stage, you'll learn how to leverage Compose Preview and its sub-features to create components, design systems, and screens to align your design specs. In the develop stage, you'll learn how to accelerate building and testing your running applications with Live Edit and Compose Editor features. And finally, in the debug stage, you'll learn how to analyze layouts and recompositions to improve UI performance with Layout Inspector and Profiler. So let's get started. First, starting with the design stage, let's build some UI with Compose Preview. But before we do, just a quick refresher, Compose Preview is a tool where you can annotate any of your composable functions with the preview annotation and see a visual rendering of your composables on their preview panel. Essentially, it is a way for you to iterate on your UI without running the app, see different states, navigate to go, and other features that we'll go deeper into. So let's get started. We'll be using examples from the Now in Android app. Let's say you're trying to build a For You screen here, and starting with a very, very simple component, the button. The button, this is the button specification. There's some color definition as well as some padding. So what I've done here is I've already created a NIA fill button composables. I usually add a preview composables so I can see my preview side by side as my code changes. Let's update the style colors as well as add different paddings so that the button is more to spec. You can see that the preview now is faster and it's updating as I make my code changes. This is a result of our continued investment into stability, and it's available in the latest version of Android Studio. We've also updated, you may notice, the status indication to the top right corner of the preview. You can see all different statuses of the preview on this top right corner. This tells you whether or not the previews are up to date compared to the code in this current file. Now let's say the designer actually wanted a color change anytime this button was clicked. So here I've just defined a very simple generic click event that changes the button colors in the code. I can then use the interactive preview to test it out. So if I enter the interactive preview mode, you can see I just click on the button and the color changed. The interactive preview is useful as a sandbox environment to quickly test different states as well as gestures such as this one. It also plays animation. It does have some limitations. It's not running the actual device, but it is meant to aid in your design workflow quickly. Speaking of animations, Jetpack Compose's animation API are great to make designers' motion spec come to life. If you have animations built using Compose, the preview will detect and show the third animation icon. So I can enter the animation preview to scrub through the animation. I can also control different speed, in this case, slow it down to pinpoint what's going on. I can even freeze individual transitions so that I can coordinate to make sure they coordinate together. Look at the graphs to compare it with design spec. Currently, the animation preview supports update transitions and animated visibility, and we plan to add more. All right, now that the button is to spec, I can start using the preview parameters to ensure it works correctly across different conditions. For example, I have localized my button here into different languages. So I want to create different preview by repeating the preview annotation into a different language. So I can have preview for a Japanese button, Hungarian, Arabic. You can actually find a full list of the parameters in the preview documentation, but some common ones you can think about are themes, font sizes, and devices. Let's say my app target these languages, so I want to be able to reuse these 4 previews quickly. To do this, I can use the multi-preview annotations, which is a way to define an annotation class that itself has multiple preview annotations with different configurations. Adding this annotation to a composable function will automatically render all the preview at once. So let's see this in action. I have grouped these 4 different language previews into something called locales preview annotation. And all I have to do is to use this locales preview annotation to apply to the button that I just made, and you will get the 4 language previews directly. You can even use multiple multi-previews together. So here I've defined at the top a themes preview that has a light and dark theme, and at the bottom I have 4 different font scales into a font scales preview class. If I apply these 3 different themes, font scale preview, as well as locales preview into the different buttons that I make in this app, you can see that I now have multiple states of my buttons. So many buttons. This actually leads to my next use case of Compose Preview, which is building a full design system. On the screen here is a sticker sheet of the Now in Android design system. You have your color themes, typography, and of course, all the buttons and components. what I love to do is actually recreate my own sticker sheet using Compose Preview. On the left, you can see this is my themes preview, also my typography. On the right, you can see a catalog of all the components that is available in this app. This is not only useful to compare with design spec, but also for any newcomers to the team, they can quickly ramp up just taking a look about what components is available in the app to build new screens. If and when my designer decided to make any changes to the themes, in this case, changing this purple base to a green base palette, I can make the same changes in the same file and just compare the spec side by side. I can also check to see if the new things have affected the components correctly, the styles are inheriting correctly. Now that I have my components, sticker sheets, I will continue to use the preview to build bigger components, such as this card, as well as full screens. When you're building bigger and more complex components, like the card here, you may need to start supplying data to your preview so it resembles your data type. In this case, this chart takes in a news resource type that has a header image, authors, URL, content, and more. One neat trick here is I can create a resource data card provider class that implements a preview parameter provider class and returns the sample data as a sequence. This is a list of news resource sample data that I just put in with different styles. You can think about things like no authors or longer paragraphs. And then all I have to do is to pass that sample data to the composable preview function by adding a parameter with a preview parameter annotation of this resource data provider, which then will populate the cards in the sequence of the sample data I provided. All right, finally, when building full screens, I can also leverage the device spec parameter in preview to put screens into different screen sizes. I can make custom device sizes, but autocomplete will actually give me the recommended reference device list. If we leverage what we just learned about multi-preview annotation, we can put all those preview devices into a device preview class. And if I apply that to the For You screen, I can see that my UI changed across different screen sizes easily. To recap, in the design stage, Compose Preview is my favorite tool to iterate the UI without running the app and make use of the various features such as interactive preview to test gestures, multi-preview to build components, sticker sheets, preview parameters for sample data, and animation preview for fine-tuning animations. There are more extended functionalities of the preview that I couldn't go over today, but make sure to check out this short link for more. Now I'm going to hand it over to Takashi here to walk you through his favorite tools in the develop and debug stages of building Jetpack Compose UI.
Thanks, Paris. Now let's talk about the Compose tooling during the development phase. After the design is fixed, you are going to develop a feature and see how the app experience is like on the device. Lightweight is a tool to help you iterate the development cycle quickly without waiting for the entire app to be built and deployed to the device. The typical development workflow will look like this diagram. At first, you want to edit the code, run the app, wait for the app to be built and installed. And then finally see how the code change affects the UI. Then you go back to editing again. Lightweight makes this cycle faster, as now you don't have to run the app and wait for the entire app to be built and deploy to the device on every edit. Let's see how Lightweight works using Now in Android. Here, I have an emulator in Android Studio. I'm going to add social links to the author screen. First, I'm going to add an icon for Twitter and load the drawable from the resource and adjust the size by using a modifier. Then I do the same thing for the icon for Medium. Actually, I want these icons aligned horizontally, so I will surround with row. The layout looks now good, but clicking the icon does nothing at the moment. So I will add a click handler that sends an intent to the author's profile page. OK, once I'm done, then click the icon again. This time, it has brought us to the author's profile page. As you see, all of them happened without restarting the app. You may be wondering what is the difference between Compose Preview and Live Edit, because they are similar at first glance. You can use Compose Preview when you work on the individual composable, or when you want to see a composable under different configurations, such as device themes, device sizes, and font sizes. On the other hand, Live Edit lets you see the entire app experience on the device, which allows you to load real data. Since the introduction of Live Edit, we've added new features. The first point is that Live Edit no longer needs to reset the composition after code changes. As you can see, making an edit to the interest screen with Live Edit used to navigate, taking us back to the first screen of the app. From electric view, Live Edit doesn't reset the composition, so you don't have to navigate back to the interest screen after the edit, which makes the experience less interruptive. The second point is when Live Edit refreshes the device. A feedback we received repeatedly was the developer wanted to have more control over when the code changes are applied to the running device, depending on the current task or preference. Auto refresh, which means the code change is pushed to the device on every keystroke, has been the default mode since Live Edit was announced. But there were some situations where you don't, where auto refresh wasn't the best option. For example, when you don't want to re-execute the code over and over as you type. Starting from Flamingo, you will have the option to trigger the code change manually to the device. With manual mode, refresh mode selected, once you start editing, the status is changed to needs refresh. After editing the code, change is deployed to the device when you explicitly type the combination of keys, giving you more control over Live Edit. The last one is about the error handling. Previously, Live Edit would pause when there was an unexpected error, but it didn't tell you what part of the code caused the error. Starting from Flamingo, Live Edit shows you the path. Starting from Flamingo, Live Edit shows the path to the stack trace, allowing you to navigate to where the code error happened. The screen capture is the sneak peek of the feature. The experience will be improved while incorporating your feedback in the Canary channel. Note that in some situations, you still need to rerun the app, even if you are using Live Edit. For example, when you run the app for the first time, when you add or delete a method. At the moment, Live Edit is an opt-in feature. You can enable it by going to Settings, Editor, then Live Edit. In Android Studio Flamingo, Live Edit will be enabled by default in manual mode, where the developer needs to trigger an update. Next, let's talk about the editor features. As you are getting used to Compose development, these will allow you to boost your productivity. They are divided into 3 categories: intention actions, code completion, and the live templates. You don't have to remember all of them because there are a lot of features. But let me introduce some of my favorites. The create a composable function intention allows you to create a composable function based on the selection in the editor. The intention will create a composable function signature with the argument inferred from the selected code. Another useful intention is to surround composables with a container. That means any of the box, row, or column. This allows you to avoid adjusting the matching parentheses at the end of the container. When creating a modifier parameter, you don't have to, you can start typing the name of the modifier without typing modifier first. Using this auto completion will also add any imports that are needed. Here, some frequently used live templates. You can type COMP to create a new composable. Similarly, you can type PREB to create a preview function. It's much quicker than typing them manually. Let's recap what I have talked in the development phase. I explained the live edit makes the development cycle faster, and the manual mode that is added in Flamingo. Check out the linked URL for more details. I also talked about the editor features. They are divided into 3 categories. I explained some of them, but we are working on more to come in addition to those. Moving on from development to debugging. As you gain users, some users might start reporting issues such as junk on the UI. There was an actual issue in Jetpack that scrolling the title bar caused a junky animation, especially on low-end devices. Note that the issue is now fixed, and I will just take it as a case study. This is often caused by too many recompositions. Let's go over what is the recomposition and how it matters on app performance. Remember that Compose has 3 phases. The composition phase determines what to draw by building the tree of composables. The layout phase takes that tree and determines where to draw by calculating them. The draw phase actually renders the composables to the screen. Recomposition is the process of calling your composable again when inputs change, which triggers that composable to go through the phases again. If no inputs are changed, the compose can skip the entire phase, which leads to performance gains. That's the reason you need to care about the recomposition counts. Android Studio offers a tool that allows you to see the number of recompositions in layout inspector. The numbers on the left are the recomposition counts, and the number of the right and the skips counts. If you look at the Jetpack before the issue was fixed, you can see the increasing number of recompositions on every frame or so, which looks problematic. Note that starting from Android Studio Electric Wheel, the UI component that recomposed is highlighted in red. Now we have identified that too many recompositions are happening. Starting from Android Studio Flamingo, you can use Compose composition tracing, which allows you to see the composition tracing in the profiler. Before it was introduced, the profiler only showed the block per frame, but it didn't tell you which composable triggered the recomposition. With Compose composition tracing enabled, it helps you to investigate what composable function caused the recomposition. In JetSnack's case, as I have a closer look at the tracing, it turns out that the function in the title composable may be suspicious. Let's recap what I have talked in the debug phase. We covered what is recomposition and how it matters on performance. And recomposition counts in layout inspector helps you investigate what the part of the UI causes a lot of recompositions. Then starting in Flamingo, you can use compose composition tracing to investigate what the composable function is suspicious. Now we have identified what the composable caused a number of recompositions. There are several ways to improve the code. Check out the ADS talk about the dedicated Jetpack Compose performance, or the Medium post about how to improve the problematic code. Let's recap the tools in each workflow. In the design phase, compose preview and interactive preview let you validate your UIs. And the multi-preview allows you to evaluate the composable under different configurations. Preview parameter supply sample data to populate more authentic previews. And animation preview lets you investigate animations. In the develop phase, live editor accelerates your development cycle. Editor feature boosts your productivity. In the debug phase, recomposition count in the layout inspector helps you investigate, find the unnecessary recompositions. And the compose composition tracing allows you to spot the suspicious function that triggers too many recompositions. We know that the UI development is iterative and often happens in parallel. So you can use those tools interchangeably in the 3 workflows. After this talk, now you are ready to leverage these tools to build a beautiful, performant, and adaptive Compose UI. Check out the Compose tooling doc to learn more. Thank you.
Hi everyone, I'm Manuel Bio, part of the Developer Relations team, and today we're going to go through the different types of stateholders we can find in the UI layer, when to use which, and how to produce screen UI state. This talk assumes some basic familiarity with the architecture and the UI layer, so if you need to get up to speed, check out our architecture pathway that contains a ton of information about this. But as a quick recap, here's our recommended app architecture. Arrows mean dependencies in this context. At the bottom of the hierarchy, we can find the data layer, which is going to expose application state to the rest of the hierarchy and contain the vast majority of business logic. Then we have the domain layer, which its main mission is going to be simplify the potential business logic that could be present in the UI layer. And lastly, we have the UI layer, which is going to display the user information on the screen. Whenever the user information changes due to the user interacting with the device or external input, the UI layer should update to reflect these changes. And the UI layer is made up of 2 entities. We have the UI elements, or UI, that actually render the information on the screen, and we have stateholders. Stateholders are going to hold an exposed state to the UI, and it's going to handle its potential logic. Depending on the types of state and logic, the implementation detail of these stateholders might be different, and that's what we are going to cover today. The UI layer, you can find different types of state in the UI layer. First one is the screen UI state that contains the information we need to present to the user, mostly application data. And then we have the UI element state, or the internal state of UI elements. To see some examples of this, we are going to look at the Now in Android app, which is open source. You can check out the source code over there. Here we are looking at the intro screen for both mobile and tablet devices. As part of the screen UI state, we can find the list of interest under details and whether or not an interest is followed. As part of the UI element state, we can see the selected tab in the bottom bar navigation and the scroll position of the list. When it comes to logic, we can differentiate by what the logic does. We have the business logic, which is the implementation of product requirements that define how data should be created, stored, and managed. As I said earlier, most of the business logic is going to be present in the data layer. And then we're going to have the UI logic that defines how to display state changes on the screen. And the UI logic depends on the UI configuration, such as screen size, language, or orientation. Depending on the UI configuration, the UI logic might be different. Here, looking at the interest screen again, we can see that loading topics or following a particular one could be considered business logic. And then showing topic details or highlighting a selected item could be considered UI logic. You can see how showing topic details might involve navigation in a mobile device or could mean showing an element next to another in a tablet. It depends on the UI configuration. But we're in Android, right? And we know that configuration changes can happen. For example, if we run the app in a tablet, in a foldable device, screen sizes are going to change whenever the user unfolds or folds the device. And this affects how the different types of logic should be executed. The UI logic should be re-executed after a configuration change if it is affected. So for example, in a folded state, we might want to show the bottom bar navigation. And then in the unfolded state, we might want to show the nav rail. The logic to decide whether to show the bottom bar or nav rail should be re-evaluated or re-executed after a screen size configuration change. On the other hand, business logic should likely continue after a configuration change. You might not want to cancel an ongoing request to follow in, for example, an author just because the user rotated the device or unfolded it. That wouldn't be a great user experience. So given the different types of state and logic that we can find in our application, let's see how they relate to each other. We have the data layer, which is going to expose application state to the rest of the app. And we are going to observe it in the UI layer, and we are going to apply business logic to produce our screen UI state. This screen UI state is also going to be observed, and we are going to apply UI logic to modify our UI under element state. So given the differences between this type of logic, where should we handle them? The business logic complexity should be handled in a screen-level stateholder. And the UI logic should be handled in the UI itself or in another stateholder. Both types of stakeholders can be implemented with plain classes. However, in Android, we recommend using architecture components ViewModels as the implementation detail of this screen-level stakeholder. We'll see in a second that ViewModels are going to be in charge of exposing state, the screen UI state, and handling the business logic of the UI. We're going to take a look at some code now, and we'll explain why this is the case in a second. We're looking here at the interest ViewModel, which is going to manage the business logic complexity of the interest screen. You can see how it takes some dependencies from the data layer as part of the constructor. It is going to expose the screen UI state of type interest UI state here. And as you can see, like we will see later in a second, that how to create this screen UI state is going to be applying business logic by combining data from multiple repositories. And it also contains some business logic that is going to take care of user events, for example, following a particular topic. This event is delegated to the data layer, which is the single source of truth for this type of data. This request is triggered using the ViewModel scope so that the request can continue after a configuration change. But why are ViewModels the recommended implementation details for screen-level stakeholders? Because of their benefits. ViewModels survive configuration changes. This can be scoped to an activity, fragment, navigation graph, or a destination of a navigation graph. And they live longer than the screen itself. That's why it's a great place to hold our screen UI state so that it's instantly available after a configuration change. And also it's great to trigger our business logic request so that those requests can survive a configuration change. But not only that, it also integrates perfectly with other Jetpack libraries, for example, navigation. View models are going to be cached in memory or kept in memory whenever that destination isn't part of the current backstack. That makes it ideal to, for example, to go back and forth between different destinations here in our bottom bar without loading the user data again. The data is instantly available. Also, ViewModel instances are going to be completely destroyed whenever the destination is removed from the backstack. That's going to make it safe to go back to a previous destination without seeing previous user data cached in memory. ViewModels also integrate well with other libraries, such as Hilt, where you can easily inject your dependencies from the domain or data layers. But ViewModels are really powerful. We shouldn't overuse them. So here's a list of best practices. Use them at screen level. Do not use them to manage the complexity of reusable UI elements like chip groups or forms, because we're going to get the same ViewModel instance across different UI elements used under the same scope. Also, they shouldn't know about the UI implementation details. They should be generic enough to accommodate any type of UI. It could be a wearable, a tablet, or even a Chromebook. So keep the API surface, a screen UI state, as generic as possible. Do not hold references of lifecycle-related APIs, such as context or resources, because that could cause memory leaks. Again, remember, they live longer than the screen itself, so that could be dangerous. And lastly, don't pass them around. They are managed by the framework, and so keep them as close to it as possible, close to an activity, fragment, or a screen-level composable function. If you pass them around, you are giving them more access to state and logic that they actually need, and that also could be dangerous. So if the business logic complexity is going to be handled in a screen-level stateholder implemented with a view model, the UI logic should be handled in the UI itself or in a plain stateholder class. What to use here depends on the complexity of the screen. So let's start simple with having just some UI logic in the UI. Here we are looking at a custom UI component that keeps track of whether or not it is expanded. The expanded variable is held and managed in the UI itself. But things can get more complicated, right? We can start adding more state and more logic to this composable function, and the UI is going to be complicated. So what we can do is delegate that complexity to a plain class. And Compose have a lot of this in their code base, in the library. That's what we call stateholders. And here we can see the stateholder of the draw composable functions. It's called draw state. You can see how stateholders can expose state, like for example, whether or not the draw is open. And a nice property of stateholders is that they are compoundable. For example, here, current value is going to get its value from another stateholder defined internally, from swipeable state. And they're also going to handle the UI logic, like opening the draw or animating to a particular value. The same way Compose offers this, you can do the same in your application. You can create your own stateholders. So here we are looking at the Now in Android app state, which is the stateholder for the Now in Android app composable function. It exposes some state to the UI that is relevant for it, like the current destination, and whether or not to show the bottom bar, and it handles UI logic like navigating or handling back click events. And what are those plain classes best practices in this case? Well, we say that we can use plain classes to simplify our UI, but actually they are recommended in reusable UI components so that you can hoist out the internal state if needed. Another best practice is that they actually can hold references of lifecycle-related APIs. They are scoped to the UI. They are going to follow its lifecycle. So that, for example, if an activity gets recreated due to a configuration change, you are going to get a new instance of this class, of this type. So it is safe to do that. OK, so back to our diagram, we could say that the business logic and the screen UI state should be managed by a screen-level stateholder, ViewModel in this case. And then the UI logic and the UI element state is going to be handled in the UI itself or in a plain class. Sometimes you might see that, for example, UI element state needs to be hoisted out into the ViewModel because they are needed for business logic, and that's fine. That's totally OK. I think it's time now to play a little bit game, right? Here we are looking at the screenshot of the Now in Android app for view screen in this case, and as part of the onboarding process, you can select some interests and read some news. So let's identify all the different stakeholders that we can find here. we're going to have the Now in Android app stateholder, which is going to manage the UI logic complexity of the Now in Android app composable function, mostly top-level navigation. Then we're going to have the For You ViewModel handling the business logic complexity of the For You screen, and also exposing screen UI state. And also, we're going to find some other stakeholders in the UI itself, managed in the composable functions, like lazy list and lazy grid stakeholders. But you might have been wondering, OK, if we have a really complicated screen and all that logic goes to the view model, that's going to grow insane. It's going to be huge, right? And that's true, but there are different ways you can mitigate this. First way is introducing the domain layer. The purpose here, you can find more information in the documentation, is that some complexity, business logic complexity that is in the UI layer, it can be delegated to a use case. And even that use case could be shared across multiple view models as well. Another way to mitigate this is that you can create different stakeholders to manage the complexity of individual portions of your UI. So here, the view model would simply become a storage mechanism that survives configuration changes, and then the more targeted functionality is going to be delegated to the stakeholder. Earlier, I said that both types of stakeholders can be implemented with plain classes, and that's still true. The idea is that you should use view models in your application if the benefits apply to your use case, if the benefits apply to your app. So let's imagine that, for example, you don't need to use view models because, well, for example, when? You don't need to survive configuration changes. Maybe you are in a pure Compose app and you are handling them all. Caveat here, you cannot handle them all. For example, the wallpaper change in Android 12 and above devices cannot be handled. And let's say that you don't need to use navigation or heels because you have your own solutions. In that case, there is no need to use view models. But we actually recommend introducing this screen-level stakeholder in your UI layer to simplify the UI so that it becomes more scalable and testable. So if even if you use view models, it could be a different implementation detail. It doesn't matter, but it's a good practice to have this screen-level stakeholder. I talked a lot about logic in this presentation. If you are more interested in state, check out the Where to Hoist That State talk by Andres Tamato coming up later today. So we've seen the UI layer pipeline, right? The different types of state and logic that we can find in our UI layer, and also how to manage the complexity of it. And now we're going to look at a particular part of it, how to produce screen UI state. The UI state is the output of a stakeholder processing some inputs. And those inputs could be events or local or external sources of state change. When it comes to the APIs involved, we can say that the UI state should be exposed as an observable data holder. And this guarantees that the UI always has a UI state to render on the screen. And the inputs can come in different forms. It could be one-shot APIs or streams of data. We're going to see some examples of this. For example, we're going to start with just a local source of state change that is going to create our screen UI state. We're going to see how to model it and how to expose it. So imagine that we are on this application that allows the user to roll the dice. We're going to have our screen UI state with some dice values and then the number of rolls. The business logic to roll the dice is going to be present in the view model. Here, it's going to be local to this, and we're going to use one-shot APIs, the random API in this case. The UI state, we are going to model it using a mutable state flow, which we're going to keep it private for now. And this is going to be of type dice roll UI state. Whenever we get the user event, we're going to update our UI state using, calling synchronously the random APIs. And if the UI wants to listen to these state changes, they will need to collect from our public UI state of type stateflow, which is a read-only version of our internal state. This is for local sources of state change. But what if we have something external? Imagine now that we want to greet the user and display their name on the screen. So we're going to get that information from the data layer, from the user repository that exposes a user stream of type flow. This flow, we are going to map it so that we can get the name out of the user object. So this is going to return a flow, right? And we need to expose an observable data holder. For that, we are going to use the stating operator to convert our flow to state flow. we're going to pass in the ViewModel scope. That's going to define for how long this stateflow is going to live in memory, as long as the scope is alive. And then we're going to pass in the started policy of while subscribed. That is going to cancel the upstream flow collections, those coming from the data layer in this case, when there are no collectors for more than 5 seconds. And the UI would need to collect from this user UI state. But what if now we have to combine local and external sources of state change because of product requirements? So imagine now that we only allow the user to roll the dice if they are logged in. So we're going to have this UI state here, loading, log user in, and also the dice roll. The username and number of rolls are going to come from the data layer, and then the dice values are going to be obtained locally, just as before. So the way to model the local source of state change is going to be as earlier. We're going to have a roll state, mutable state flow, an observable data holder that is going to be updated whenever the roll dice function is called. Now we need to combine this stream, roll state, with the stream coming from the data layer, with the user stream. And for that, we're going to use the combine function. In its body, we're going to say, hey, if the username is empty, then we're going to emit the log user in state. And if not, we're going to build our dice roll UI state combining both streams. Username, a number of roles coming from the data layer, and then the dice values that have been obtained locally. Combine is going to return a flow. And to convert it to a state flow, we're going to use, again, the stating operator. And now, like this UI state and these UI states that we've seen so far, they need to be collected, or at least should be collected, in a lifecycle-aware manner in the UI. In Compose, we are using the collect state with lifecycle API that is going to transform the collected values into compose state. Then we can pass into the stateless composable functions that are actually going to render the information on the screen. If you want to know more about this topic, check out the collecting flows in a lifecycle-aware manner talk that should be available in YouTube later today. Now we're going to see that depending on the inputs that we get to build our UI state, how to model it internally and how we are going to expose it. So if we have a local source of state change or one-shot APIs, we are going to model it internally in the ViewModel as a private mutable state flow or compose state, and then we are going to expose it as state flow or compose state. If we have an external stream modeled as a flow, then we are going to expose it as a state flow using the stating operator. If we have both, if we have at least an external stream, then we will need to combine them and expose it as a state flow, likely using the stating operator again. I didn't have time to cover compose state in this presentation, but if you're interested in the patterns and how to model your internal UI state here, check out our documentation where you can find more information about it. That's pretty much it, what we had to share today. As a quick recap, we've seen the different types of state and logic that we have in the UI layer, how to manage the complexity of it. So we have the business logic and screen UI state handled in the ViewModel as an implementation detail of a screen-level stateholder. Then we have our UI logic and UI element state handled in the UI itself or in a plain class. Again, reminder that if you need your UI element state to be used or needed for business logic, then you can hoist it out in the ViewModel. Watch Alejandra's talk later today to know more information about this. We also saw how to produce screen UI state depending on the inputs that we get. And finally, if you're hungry for more information and you want to learn more about these topics and more, check out our documentation. We have stakeholders, UI state production, everything we've seen today, but also UI events, how to handle them in the UI and also from the ViewModel. Thank you so much for watching. I hope you enjoyed the talk. I hope now you also learn a little bit more about the UI layer. Thank you so much for coming, and talk to you later. Bye.
Hello, everyone. My name is Jose Alferreca. I'm an engineer on the developer relations team. In this talk, I'm going to walk you through 5 ways Compose has changed how we test UIs. So let's start with a wish list. Tests should be easy to write, they should run quickly, and they should be reliable. But this is not always the case. Compose was designed with testability in mind, so can we say this is true now? Well, not completely, but it has improved the testing experience enormously. So let's look at 5 ways it did. we'll start with testing in isolation. What does this mean? When you create a Compose test, you can launch one of your activities, like we've always done, or you can start an empty one and set the content yourself. That content is a composable context, so it can be anything, a whole app, it can be a single screen, it can be part of a screen, or even the tiniest composable. Because Compose is declarative, whenever you set content, that composable is basically going to tell you what it needs to render. In this example, a list of items and a callback, which is normally empty in tests. It's as easy as creating a preview. The next improvement is about synchronization. This is how the test knows when to send the next action or perform the next session. In the Vue world, you need to use tools and frameworks like Espresso, which have ways to figure out if the app is busy or idle, and views don't have a way to tell you if they're busy. However, that's exactly what Compose does. It exposes a much more straightforward signal to the tests, making them much more reliable and faster. So if you've ever written thread.sleep in your tests, and I see some guilty faces here, now it's probably the time to remove them. Of course, you still need to handle all the asynchronous operations that might be happening across all the layers of your app, so check out our documentation on that. The way this works is with something called automatic synchronization, and normally you don't have to think too much about it, unless, of course, you want to pause it, which brings us to number 3, controlling time. In Compose tests, in Compose tests, you can pause time or advance the clock as much as you need to and do an assertion at that point in time. The assertion happens immediately. You don't even have to wait for the clock to be advanced. The way you do this is pretty simple. You set the auto-advance property of the main clock to false. Then you call advance time by, passing a number of milliseconds, or you can also go frame by frame. But why would you want to control time in tests? Well, this is very useful for any apps that handle time one way or another, like a stopwatch, but it's also great for testing animations. For example, you can verify state or take a screenshot at particular times and make sure that you never have regressions. Speaking of time, the next one is about waiting for things to happen. As mentioned before, you should never sleep in your tests, and you can rely on automatic synchronization instead. However, as tests grow in scope, it gets harder to deal with all the asynchronous operations that are going on. And in end-to-end tests, it might not even be worth it. Instead of that, we can tell the test to wait until something happens. So for those few end-to-end tests, there's a Compose API called waitUntil that I really like for this scenario. It will pause your test until its body is true. So you can look for a particular element or do whatever you need to synchronize your tests without waiting for an arbitrary time. The 5th one is about testing state restoration. Managing state and restoring it after a configuration change, like a rotation or some foldable gesture, can get tricky. So it's important to test it. You can emulate a configuration change by restarting the whole activity using the recreate method in activity scenario, which is an API in Android X test. But now with Compose, you have a new option called State Restoration Tester, which is very easy to use. You just set the content through the tester and then trigger a recreation. The state will be saved and restored as if a configuration change happened, but much quicker and simpler. Testing UIs has improved a lot with Compose. So if you need another excuse to migrate or start with Compose, testing is a great one. These were just 5 features, but there are a lot more. So check out the Compose testing documentation for more details and resources. Thank you.
Hi, everyone. My name is Wojtek, and in this lightning talk, I will present 5 new and hopefully exciting features in upcoming Android Studio versions that you might not have seen yet, although there were some spoilers in the keynote. So first up, we have some improvements in the network inspector. As you can see, we've eliminated the need to select a range on the timeline before you start seeing requests. But wait till you see this. We're adding network request interception based on fully customizable rule sets that you define. In this demo, I'm intercepting the request for article details in the Now in Android app. So I filled in the host name, path, and status code. I can then replace the response codes, headers, and even the full content body with replacement text. So let's see how my app behaves in various scenarios. So here you can see parts of the response JSON in the Now in Android app replaced on the fly without changing any app code, thanks to the network request interception. This was a highly requested feature, so it's available for you to test in Android Studio Flamingo Canaries. OK, at number 2, we have downloads information in the build analyzer. We know build times are a hot topic for many developers. That's why we built the build analyzer. It's a tool that highlights issues that might be slowing down your builds, such as problems with configuration caching, or showing you when you're still using the Modifier and you shouldn't. But sometimes there's only so much you can optimize in Gradle scripts themselves to make them run faster. That's why we're adding a new metric, downloads impact. This feature shows you what part of your build is spent on downloading dependencies, and also helps you notice when artifacts are downloaded needlessly on every build, most likely indicating deeper problems with your setup, such as using dynamic dependency versions or snapshots. This is available for you to try in Android Studio Electric Eel Beta. For number 3, I want to show you an early glimpse at the Android SDK version upgrade assistant that you might have seen at the keynote already. It's a tool that helps you target the latest and greatest Android OS versions, ensuring that your users always get the best quality and security and privacy in your apps when they update. Thanks to the built-in rules, we can detect when you need to update your target SDK version in your build, and guide you through the required changes in the IDE so you don't have to constantly context switch between the browser, the documentation, and your code. In the future, the assistant will detect code patterns in your project that need updating to match the platform's behaviors and new APIs. But this feature is still under heavy development, so please watch our social channels and new releases to learn when it's ready for you to try. At number 4, we have a new feature in the device manager. So that's the tool that you use for configuring both the virtual and physical devices that you use for running your apps. We've made tons of improvements in this area. So you can pair your device over Wi-Fi. You can quickly pair Wear OS devices, and much more. But now we're adding physical device screen mirroring. For any connected device, you can now stream the UI to your IDE window and interact with it just like you would with the emulator, using simulated touch events. You can also drag and drop APKs onto the device to install them, and even use your keyboard for text input. So all this leads to higher productivity and, again, fewer context switching between devices. You can try that now as an experimental feature in Electric Eel. And lastly, a treat for everyone developing apps that rely on Bluetooth connections. We're expanding our emulator's Bluetooth support. You can now create arbitrary connections between multiple running emulator instances, including for discovery, pairing, and exchanging of data. So here you can see 2 emulators seamlessly exchange pass Bluetooth messages and files with nearby sharing, just like real devices. This addition of a functional Bluetooth stack is useful for local development currently, but we're working on enabling even more use cases, such as being able to programmatically define Bluetooth devices for your tests. Let us know what kind of support you'd like to see here. That's it for this talk. I would like to ask everyone to try out other features in our beta and Canary releases to help us build the features that you'll like. So thanks for coming, and see you on the conference floor if you have any questions.
So hopefully you've been enjoying the talks so far, even if the demo gods weren't smiling on us today.
Hello, I'm Don, and I'm an engineer on the Android Developer Relations team. Today, I'm going to show you how to build a scalable, modularized, testable app from scratch. Now, this won't be a Hello World app. I'll concentrate on building an app architecture which will enable your app to grow. We'll use modules to separate responsibilities and create a test infrastructure to verify that your app behaves as expected. Lastly, we'll look at how to build a flexible, intuitive, and great-looking user interface. I'll be covering a lot of different concepts, so if I cover something you're not familiar with, there's a link on virtually every slide which will take you to more information about the current topic. Throughout this talk, I'll use the Now in Android app as an example. The source code is available on GitHub. In the app, we have a screen which shows content which is customized for you. It displays a list of news articles and allows the user to bookmark each article. We're going to take a look at how the For You feature was built, starting with how bookmarks work. The architecture for a feature like this can be broadly divided into two layers, UI and data. The data layer obtains and exposes app data to the UI layer, as well as performing business logic. The UI layer displays app data on screen and reacts to any changes in that data. An important word here is reacts. By setting up a stream of data between the layers, we are creating a reactive UI. It just needs to be told how to update its state when new data arrives. It's important to understand that the UI does not request or poll for data, it just collects data. The only communication which happens in the opposite direction are events. The data layer handles these events, updating its underlying data and emitting any changes back to the UI. In this way, we have a single source of truth for the app's data, and the data only flows in one direction. This is known as unidirectional data flow and is an excellent way of keeping your app in a consistent state. If we apply this general guidance to this specific feature, we can clearly define the responsibilities for each layer. The data layer should store user bookmarks and expose them to the UI layer by publishing a stream. We can do this using Kotlin flows. The UI layer then displays this information and updates it whenever it changes. The UI should also provide a way for the user to add and remove bookmarks, and these user events are passed back to the data layer so the data can be updated. Let's dive into the data layer to see the individual classes which we should implement. The data layer architecture can be split into two types of component: repositories, which expose the app data and centralize changes to that data, and data sources, which obtain data from a single source. Let's take this from theory to reality by implementing the classes in the data layer. We'll start by implementing a local data source class. This will store bookmarks locally on the device using Jetpack Data Store. Let's take a look at the code. Local data source accepts a data store object as a dependency and exposes a stream of bookmarks in the bookmark stream variable. Each bookmark is just a string ID of the news resource which is bookmarked. Data store provides the underlying data stream. It gives us a flow of data which we then convert to a list of bookmarks using the map function. The most important concept to understand here is that we're not pulling data directly from data store. We're merely setting up the stream of data and mapping each item in that stream to a format which clients of this class can use, in our case, a list of strings. Lastly, it provides a function to update bookmarks by adding or removing them from a map backed by data store. Each time the bookmarks change, a new list of bookmarks is emitted into the bookmark stream flow. We can now add a repository to expose these functions to the UI layer. The code in the bookmarks repository is pretty simple. It takes our local data source as a dependency and exposes the bookmark stream and toggle bookmark function from it. If we were doing something more complicated, like combining data from multiple data sources, this would be the place to do it. A common example is an offline first feature which pulls data from a network data source, then synchronizes it with a local data source. We also need some news articles to display, and obtaining these can be implemented in much the same way. The only difference being that the data comes from the network rather than being stored locally. We can add a network data source to pull news articles from a REST API, and a news repository to expose those news articles to the UI layer. It's good practice to have a repository for each type of data in your app. So that's our data layer sorted. Now our UI layer needs to display those bookmarks next to each news article and let the user add and remove bookmarks. Let's take a look at the UI layer in more detail. Here we also have two component types. The stateholder handles the screen logic and constructs UI state from app data. It does this by listening for changes in the data layer. And the screen displays that UI state using UI elements. Again, applying this general guidance to our feature, we can define the responsibilities for each layer and the classes we need to create. Let's take a look at the stateholder. For this, we can use a Jetpack ViewModel, prefixing the name with For You, the name of this feature. This class listens for data from the news and bookmarks repositories and combines them to create a UI state. Before we dive into the code, let's look at exactly what's happening here. We have lists of news resources coming from our news repository, and we have lists of IDs coming from our bookmarks repository. Our ViewModel combines these two to create a list of savable news resources. Each item in this list contains the news resource itself and whether it's saved or not. The code for these models is pretty simple. News resource has some fields for the news article like its ID and title, and savable news resource is just a wrapper around news resource which also includes whether that news resource is bookmarked. It's used by our UI layer to represent the combined data from both the news and bookmarks repositories. And here's the code for our ViewModel. We accept the data repositories in our constructor and create a combined data variable to store a flow of savable news resources. This is created using the combine function, which, as its name suggests, combines the data streams from our two repositories. Whenever the data changes in either stream, our transformation function is called with the latest news resources and bookmarks. Inside it, we map each news resource to a savable news resource, checking to see whether it's bookmarked. Let's go back to our ViewModel diagram for a second. Once the data is combined, our ViewModel needs to convert this to a UI state, which can be one of two possible values: loading or success. Loading is used when data is being initially loaded, usually when the news resources are being loaded over the network. And success is used when the data has been loaded successfully. It contains the list of savable news resources so the UI can display them. Here's the code which does that. We use a sealed interface to represent the two UI states. Loading is just an object, whereas success is a class which holds the savable news resources. In our ViewModel, we create a variable to expose our UI state as a state flow. This is a flow which can have an initial value and is optimized for sharing state. To convert our combined data into a UI state, we simply map the list of savable news resources into the success UI state. To convert the combined data flow into a state flow, we use stateIn. We specify the coroutine scope which the flow should be started in, and an initial value of loading. Collecting from flows can be expensive, especially if they access the network or sensors. We can use the started parameter to indicate that we only want the flow to be active when there is at least one collector, usually a screen. This avoids wasting resources. When the last collector unsubscribes, we wait 5 seconds before stopping the upstream flow, just in case the collector only went away temporarily, as can happen during a screen rotation. This avoids the potentially time-consuming operation of restarting the flow. The final task our ViewModel should perform is to handle requests from the UI to save and unsave bookmarks. We do this by creating a toggle bookmark function. Inside it, we call the relevant method on the bookmarks repository and execute that call from the ViewModel scope. Now, one of the benefits of using a ViewModel is that it survives configuration changes. This means that operations initiated using the ViewModel scope will continue to run and our UI state will be preserved. Okay, it's time to display something on screen. For this, we create, you guessed it, a For You screen. This will read the UI state from the ViewModel and render it using UI elements. We'll use Jetpack Compose for this, as it's the recommended UI framework for new apps. Let's refresh our memory on what the design for this feature looks like. We can see that the news articles are displayed in a column, and the design concept for each article is known as a card. So let's go ahead and create a draft implementation for our UI. First, we create a composable function for the news resource card. It takes the news resource, its bookmark state, and a lambda which we called when the user taps on the bookmark button. We create a column which holds the UI elements for the title, content, and bookmark button. When the bookmark button is tapped, we call onToggleBookmark. We also create a composable to display a list of these news resource cards called newsfeed. It simply creates a column and iterates through the elements, rendering a news resource card for each one. Now, you can preview composables in Android Studio using the app preview annotation. Here's how our newsfeed looks currently. Okay, it isn't going to win any design awards, and we're certainly not matching the design spec yet, but don't worry, we're going to fix this shortly. Now let's create the For You screen. This accepts the current UI state and a lambda to call when the user taps on any of the bookmark buttons. When the UI state is loading, we just display the text loading, and for the success state, we get the news resources from the UI state and pass them to the newsfeed along with the lambda to be called when the user adds or removes a bookmark. So, how do we get our UI state? Well, we can create a stateful version of For You screen, which obtains our ViewModel And once we have it, we can use collect-as-state with lifecycle to collect from the stream only when the app is in the foreground to avoid wasting resources, and to convert the stream into a compose state. When the UI state changes, it causes any composable functions which has read it, like our For You screen, to be recomposed. Once we have the UI state, we simply supply it to our stateless For You screen, along with a reference to any events which the screen needs to call, in our case, just the toggle bookmark function. So, why don't we just have a single stateful For You screen? Well, as we'll see later, stateless functions are easier to test and to preview. In a Compose app, we still need an activity. This is the glue between the Android framework and your Compose code, and is what shows your UI to the user. We try to keep our activity as simple as possible, just calling set content and then our UI code. Okay, so we've created classes for the UI and data layers. We could just place all these classes inside the app module, but we know that our app is going to do more than just display news articles. By creating modules for each distinct set of responsibilities, we can make our codebase more scalable. Modules can also enable parallel working and potentially reduce build times. Here's the modularization strategy we used in the Now and Android app. At the top level, we have app modules, which are responsible for bringing features together. An app module exists for every app which can be built as part of the project. The mobile app is the most obvious of these, but we also have an app module for displaying the visual design system and could have more app modules for different target platforms such as Wear or TV. App modules depend on feature modules. These are scoped to a single area of user-facing responsibility, such as providing the content for the For You screen. Feature modules do not depend on each other, but can depend on core modules. These are common library modules used throughout the app, also scoped to a single area of responsibility. For example, repositories are held in the data module and networking code in the network module. Let's figure out where our classes should go. Our main activity goes into our app module. Classes which are specific to the For You feature are moved into the For You feature module. Data classes, which are used by other modules, are moved into the core model module. For repositories into core data, classes associated with local storage using data store move into core data store, and network classes move into core network. Now, a common problem with modularization is that you end up with lots of duplicate dependencies and configuration blocks inside your build files. We solved this in Now and Android using a feature called convention plugins. The idea is to move common options and dependencies into a plugin, and then include that plugin in all the modules which require those options. This way, all your configuration stays in one place and can be easily updated. The plugins and supporting code is contained within a separate build logic module, which is built before any other module. This ensures that any configuration changes are propagated to all dependent modules before they're built. Another common problem in modular codebases is keeping track of library versions, especially when they're scattered through multiple Gradle files. Version catalogs is a Gradle feature which solves this. A version catalog is a single file which contains a list of every library used in the app and its version. Each library has a unique ID which can be referenced in Gradle configuration files. Whenever we need to update the library version, we just update it in the version catalog. This modularization strategy helped us to build a loosely coupled graph of modules for Now and Android, enabling us to work in parallel and reduce the amount of time deciding where to put new code. You don't have to modularize from the outset, but if you know your project needs to scale, you can save a lot of time by introducing a modularization strategy early. So at this point we know what classes to create and which modules to save them in. What we don't know for sure is whether our code functions as intended. Tests can do this by verifying the behavior of individual classes and our app as a whole. They allow us to add new features or refactor our codebase with the confidence that if we break something, we'll know about it before our product is shipped to users. In fact, if you have a clear idea of the classes you need to create, it's even better to write the tests first, but it's up to you to decide when to write tests, just as long as you actually write them. There's a lot of theory behind testing, which you can check out using the link below. I'm just going to show you how we can write a unit test and a UI test to verify the behavior for our feature. We should add tests wherever there is logic, and one of the places there's a lot of logic is in our ViewModel. As we've seen already, it combines data from two streams and converts it into UI state. Let's write a unit test to verify this behavior. The first thing we need to do when writing a test is isolate the test subject from its dependencies, in this case the repositories. instead of using the real repositories, which are going to be performing long-running operations like pulling data from the network and local storage, we should instead create test dependencies, also known as test doubles. This allows us to control the inputs to our test subject and verify the output. Plus, our tests will run a lot faster. The problem is our ViewModel depends on concrete classes. We should rename any concrete classes and have them implement an interface which the test subject can then depend on. This way we can create test classes which will be supplied when testing. Let's implement our ViewModel test class. We start by creating a rule which sets our coroutine dispatcher to a test dispatcher. This ensures that any coroutines are executed sequentially inside our test and is essential when testing flows. Then we set up the dependencies and create a variable to hold the subject under test, the ViewModel. And we ensure that it's recreated with our test dependencies before each test is run. Now we can write a test which will verify that after the news resources and bookmarks are loaded, the ViewModel produces the correct UI state. Inside our test, we start collecting from the ViewModel state. Without this, no values would be emitted into the flow. We tell our test news repository to send some news resources to the ViewModel, and our test bookmarks repository to toggle a bookmark for the first news resource. Now we get our UI state. We then check that it's success and that the correct news resource has been bookmarked. Lastly, we cancel the collection job, otherwise the test will run indefinitely. Since this is a locally run unit test, we save it in the test folder in our feature module. Now let's create a test for our screen in a UI test. Here we have a choice. We can either run the UI test directly on our host using a testing framework like Roboelectric. This is known as a local test and is saved in the same location as our previous test. Or we can run it on a device or emulator running Android, known as an instrumented test. Local tests generally run faster but offer less fidelity than instrumented tests. Let's create an instrumented test for our screen. First, we add a JUnit rule which allows us to control composables. Now we create a test which will verify that the news articles are displayed. The setContent method allows us to supply a composable and have it rendered on screen, exactly the same way as it works in our main activity. Inside here we create our test subject, the For You screen, and pass in the success state and some sample news resources. Here we can see the benefit of having a stateless screen composable. It makes it really easy to test. After setting up our screen, we can use the onNodeWithText matcher to find a node in the compose graph with the title of our news resource and verify that it exists. Since this is an instrumented test, we save it in the Android test folder. Now that we know that everything is working as intended and we have a solid infrastructure in place, let's make our app look better. The Material Design System provides a framework and set of guidelines for creating compelling, consistent, and intuitive user interfaces. It includes a set of customizable UI components for Jetpack Compose. Material 3 is the latest version of Material Design, and our design team has given us a beautiful design spec based on this, including colors and typography. We can use these to define a theme for our app. Any Material Design components we use will be styled according to our theme. Let's take a look at this in action. We take the colors from our design spec and define them in code. Then we define a color scheme for light and dark modes. Material 3 gives each color a semantic name which describes the context in which that color should be used. For example, the onPrimary color will be used when on top of the primary color. We can also create a typography class to specify our text styles. Again, Material 3 gives us a set of names to clearly define the role for each text style. With our colors and text styles defined, we can now create a theme composable which wraps all the content in our app. First, we decide which color scheme to use based on whether the device is in dark mode. Then create a material theme based on our color scheme and typography. To use the theme, we simply wrap our content in our theme composable. If we preview our news resource card, we can see that the button is now using the colors we defined in our theme. We can specify our text styles whenever we render text, and we can take advantage of other material design components, like the card, which adds rounded corners by default and derives colors from our theme. One of the great things about material design components is that they're designed to be customized. In Now on Android, we customized several of the stock components and created a design catalog app, which ships as part of the project so everyone on the team can easily see the UI components they have to work with. A good example is the toggle button class. It wraps the material icon button to provide extra features, like the circular background you see when the button is toggled on. Bookmark button then wraps toggle button to provide the bookmark icons for the on and off states. Now, if we swap our normal button for the bookmark button, add some padding, and an image using an image loading library like Coil, we'll start to get much closer to our design spec. Okay, we made it. We learned how to implement a scalable architecture and modularize our codebase, as well as add tests to verify our app's behavior. Lastly, we learned how to use material design with Jetpack Compose to create beautiful, intuitive apps. But wait, this talk only covers the very basics of these topics, and there's some important ones which I haven't covered, which you should definitely check out, including navigation, dependency injection using Hilt, performance testing, and designing for all screen sizes. The Now an Android app includes all of these features, so be sure to check it out. Thanks for watching.
Hi, I'm Ben from the Android Developer Relations team. Today we're going to go over more performance tips in Jetpack Compose. This talk is a sequel to the I/O 2022 talk, Common Performance Mistakes in Jetpack Compose. We're going to go further in depth in this talk, so if you haven't watched the original talk, I would recommend you start there. Make sure to wave to Chuck while you're there. Of course, some points deserve repeating. If you see performance issues in your Compose app, always ensure you are testing in release mode with R8 enabled. It really does make a significant difference. And before we get started on the tips, a small disclaimer. Compose is performant right out of the box. You might not need to apply any of the tips in this talk. But how do you know if they apply to you? Should you just blindly follow them? Of course not. You should follow a defined process and not prematurely optimize your app. Doing so will just lead to hard to maintain code. So the answer to all these questions is, write a benchmark and find out. Performance optimization is not one size fits all. There are just too many variables to be able to give any guarantees. The key to performance optimization is just to inspect, improve, monitor, and repeat. Once you have identified a performance issue, write a benchmark for it, diagnose and try to fix it. Run your benchmark again and see if you have improved it. Continue monitoring your benchmarks to catch any regressions and repeat. Use tools, not rules. We won't go into all the details of writing a benchmark in this talk, but they are just like UI tests. Here is a sample test that measures the scroll performance of a lazy list. First, we get the reference to the lazy list. Then we drag the list 3 times to simulate a user touching and dragging. If you run the test, you will see results like this. Macro Benchmark runs your test multiple times and outputs the results as a statistical distribution. To understand them, you can think of it like this. You can see how long each frame took to render, and if it overran its render deadline. Or in other words, janked. For overrun, negative numbers are good, and positive numbers mean your app will show visible jank and start dropping frames. P50 means 50% of cases rendered faster than this, and 50% of cases rendered slower. P90, 90% of cases rendered faster than this, and conversely, 10% of cases rendered slower, and so on. Why do we output a statistical distribution rather than an average? Well, you might have an outlier that only occurs occasionally. With just an average, you would never get to find this out. But with a distribution, you can clearly see the outliers. It is these outlier frames that are often causing jank in your apps. For more details on how to write benchmarks, watch the Mad Skills Inspecting Performance video on YouTube. Another tool you can use to help find performance issues in your app is tracing. We have new Compose tracing tools just released, and to find out about them, check out this link. Now that we know about how to find out if we actually have a performance issue, let's have a look at some common problems you might face and tips to fix them. First up, defer reading state. While inspecting a screen in JetSnack, in the Layout Inspector in Android Studio Dolphin, again, tools not rules, we noticed a large amount of recomposition when inspecting our app. We know this could lead to janky frames, but a quick look at the app's code doesn't reveal any clues. What can we do? To understand, let's go over some theory. Remember, Compose has 3 phases: composition, layout, and draw. Composition determines what to show by building a tree of composables. Layout takes that tree and works out where on the screen they will be shown. And draw, well, pretty self-explanatory, draws it all to the screen. Here's the cool part. Compose can skip a phase entirely if nothing has changed in it. So if we can avoid changing our composition tree, we can skip composition altogether. And this can lead to big performance gains. But how do we do that? Here is a simplified version of JetSnack's code, with a parent and child composable. The child composable needs to know some state from the parent, and this is passed into it as the offset parameter. This means the offset state is read in the parent, and as such, when the offset state changes, parent will recompose. First off, we can defer reading of this offset state. You should always try and read state as late as possible. If we can move the read of this state from the top level composable into the child, we will limit how many composables need to be evaluated for recomposition and subsequently recomposed. Now to do that defer the read, you might think that this is a good idea, passing the actual state object into your child composable. While this does indeed defer reading of state, it in turn makes your compose code much harder to work with. For example, you would no longer be able to use the by delegate syntax, and you would have to add dot value to every read. You would also be tying your composable to need to use state, and you wouldn't be able to pass in a fixed value anymore. A much better way to handle the deferring of reads is to use a lambda. By using a lambda, you can control when the state is read without affecting the rest of your code too much. You can still use the by property delegate inside the lambda to read the value. So we switch the read to the lambda, and now we can defer the read inside the child composable. This is good, but we can do better. If we can read this lambda inside a modifier that isn't run during composition, we can skip composition altogether. This is because we won't be changing our composition tree at all. This is why our performance documentation states, prefer lambda modifiers when using frequently changing state. But why does this work? How come just using a lambda modifier means we can skip composition? Let's return to the composition tree and see. The composition tree is also built up of any modifiers that are applied to the composables. Modifiers are effectively immutable objects. When the offset changes and the modifier is reconstructed, the old one is removed and the new one is added to the composition tree. This happens every time the offset changes. Because the composition tree has changed, recomposition occurs. However, if we use a lambda modifier, this modifier is not actually changing. Compose is smart enough just to rerun the lambda function when it needs to, and this is why our modifier object does not change, which means the composition tree does not change, and composition can be skipped. So remember, you shouldn't have to recompose just to relay out a screen, especially on scroll, which will just lead to janky frames. So whenever you see unnecessary recomposition, think about how you could move the work to a later phase. So in this case, we can move the read of the offset into the offset modifier. This offset modifier is run during the layout phase, and doing this will mean composition is skipped altogether. How do you know what phase of Compose a modifier runs in? Well, if it's not a lambda-based modifier, it will always be run in composition. If it is a lambda-based modifier, it is almost certainly not running in composition. While this is not guaranteed, you can almost always assume it will be to start debugging. For more information about this concept and a live demo of using it to fix a problem in JetSnack, check out the Debugging Recomposition blog post. Next up, let's learn about stability. Here is the problem. We've used the layout inspector again to inspect our app, and we have noticed that some composables are recomposing even though none of their state has changed. Jumping into the code, we see something like this. We have a simple screen with a checkbox and contact details. Now when the selected state changes to true, this home screen composable starts to recompose. It goes back to the nearest recomposition scope, which in this case is home screen, It then reruns this code. First, the checkbox is called again because its selected state changed. But then as we step through, we also see contact details being called again, even though contact did not change. What could be going on here? To understand why this is happening, first let's go back to the definition of recomposition. Recomposition is the process of calling your composable functions again when inputs change. When Compose recomposes based on the new inputs, it only calls the functions or lambdas that might have changed and skips the rest. Hang on, might. Why might? In order to skip a composable, Compose has to be sure it hasn't changed. If Compose started skipping composables that it shouldn't, this would be very hard for you to diagnose and fix. Because of this, the rules around what is skipped are strict. Compose determines the restartability and skippability of each of your composable functions. Restartable functions serve as a point recomposition can begin at. Skippable functions are able to be skipped if none of their inputs have changed. Compose works out if a function is skippable based on the stability of its parameters. Immutable parameters are types where the value of any of its properties never change. We'll see an example soon, but think of this as a data class with all val parameters. Stable is a bit trickier. Stable types can have mutable properties, but any mutations will notify the Compose runtime of their changes. In practice, this most likely means their mutable properties are defined with Compose state objects. Unstable types are just none of the above. Unstable types are what lead to composables that can't be skipped. Let's see an example. Here is the definition of our contact details composable. It takes one parameter, contact. Contact is a data class with one property, name, but it is defined as var. And because it is defined as var, it is not immutable, and therefore contact is an unstable type. This means that under the hood, Compose determines the contact details function to be restartable but not skippable, as it has an unstable type parameter. To fix this, we just have to make sure that all our parameters are constant. Of course, that example was easy to find. It would be pretty tedious to have to do that manually with all your classes though, which is why the Compose compiler can output a report for you. When enabled, the compiler will output reports about your functions and classes in each module the Compose compiler is run on. This will allow you to quickly look up what is being inferred about your code. Classes.txt is the stability of the classes. Composables.txt is the restartability and skippability of each composable function. There's also a CSV file output which can be used in a script or CI. Opening up composables.txt, you will see output like this. We can see contact details is both restartable and skippable. We can also see its contact parameter is a stable type. But let's look at another one. This is the contact list composable. It's a composable that takes a list of contacts and displays them. But there is something strange happening. The list of contact is being declared unstable, even though we know that the contact class is stable because we just fixed it. This is why Compose treats list, set, and map as unstable. This might seem strange, but there is a good reason why. It's because they are unstable. The Kotlin collections provide no guarantee of immutability. This code here is perfectly valid. Because of this, the Compose compiler cannot be sure they are immutable. So what do you do? There are two options. For collection classes in particular, there are the Kotlin X immutable collections. You can also annotate classes to override what is being inferred about them. Let's have a look at the immutable collections first. First, add the immutable collections dependency. Then, instead of list, we can define our type as immutable list. Immutable lists are easy to create. You can convert a regular list into one just by using toImmutableList. Once you've done that, if you rebuild your app, you should see that your list is now declared as stable. Importantly, this was the fix needed to make our contact list composable skippable. Are we saying that you should always use immutable lists in Compose? No. You should first ensure this is actually causing you a performance issue, Then, this is just one possible fix you can use if it suits your use case. But of course, you aren't always dealing with collections. Let's look at another case. Here is a small data class for keeping logs. It has a timestamp and a log string. Another common gotcha is that any classes from external modules the Compose compiler is not run on will be treated as unstable. We are currently working on a better solution to this, but in the meantime, let's see how you can use annotations to override the inferred stability. Running the Compose compiler on our data class, we can see the timestamp gets declared unstable. As we have no control over this class, our only option here is to annotate the data class with a mutable. You can also use stable, but keep in mind the stable contract mentioned previously. This will be enough to force our log entry class to be stable, even though it still has that unstable parameter. Be careful, incorrectly annotating a class as stable when it is not could cause composables not to recompose. This brings us to the obvious question: should every composable be skippable? No. You should only do this if you have a verified performance issue. Chasing complete skippability is a premature optimization. For example, if you have a composable that never recomposes or recomposes very infrequently, it probably doesn't matter if it's skippable or not. This topic is nuanced and quite detailed. For more information about stability, including how to enable the Compose compiler reports, see the Jetpack Compose Stability Explained blog post. Let's now have a look at derived state of. A really common question we see is where and when is the correct place to use this API. Derived state of is used when your state or key is changing more than you want to update your UI. Or in other words, derived state of is like distinct until changed from Kotlin flows. Remember that composables recompose when the state they read changes. Derived state of allows you to create a new state that only changes as much as you need. Let's have a look at an example. Here we have a username field and a button that enables when the username is valid. It starts off as empty, and so our state is false. Now, when the user starts typing, our state correctly updates and our button becomes enabled. But here is the problem. As our user keeps typing, we are sending the state to our button over and over again needlessly. This is where derived state of comes in. Our state is changing more than we need to update our UI, and so derived state of can be used for this to optimize. Let's rerun this and see how the change goes. Our button starts off as enabled, but as our user keeps typing, this time we are only updating our username state. And of course, if our username becomes invalid, derived state of correctly updates again. Now this example was oversimplified. In reality, our button would most likely be skipped, as we learnt in the stability section. But if your downstream recomposition is expensive, derived state of can be very useful. Derived state of is just another tool in your belt to help with managing state. Let's have a look at another case. In this example, we have two states that we need to combine into one. Because we need to update our UI just as much as this state changes, well, in this case, derived state of is pointless. If though we were doing something a bit fancy or expensive that we wanted to cache across recompositions, well, this is where remember with keys comes in. We can remember the result of our expensive function and make sure it still updates whenever one of its keys changes. Because we need to update our full name just as much as our inputs are changing, we use remember. That is the difference between derived state of and remember with keys. Derived state of, used when your state is changing more than you want to update your UI. Remember with keys, used when we need to change our state as much as our key changes. The last tip of the day, we will look at upcoming changes to help you call report fully drawn from Compose. Report fully drawn is an API on activity that signals to Android that your app is ready to use. This allows Android to optimize your app's startup in the future by preloading I/O calls ahead of launch. Previously, this API was difficult to call at the right time from Compose. But in Activity Compose 1.7, we have new APIs coming to fix this. The new report-drawn-when composable function takes a Boolean condition and will report to your activity when that condition is true. This allows you to easily wait for your first list composition to happen or any other condition you need. Don't worry about it being called multiple times. We handle that for you. There is also a suspending version of this API, report drawn after. This will call report fully drawn when the suspending function completes. This allows you to easily wait for an animation to finish or for data to load. We hope these new APIs make it easy for you to call report fully drawn, and we recommend you do so. Macro Benchmark will also detect these calls and display the information in your startup benchmarks. And we're done. This talk had a lot of information. Here is a quick summary of what was covered. Macro Benchmark, the answer to if your performance optimizations are working. Defer reading state. Reading state as late as possible can help avoid recomposition. Stability determines which composables can be skipped. Derive state of, used when your state changes more than you need to update your UI. And report fully drawn, allows Android to optimize your app's startup. There are lots of great talks at this year's ADS. In particular, related to performance is making apps blazing fast with baseline profiles, which goes over how to create and tune a baseline profile which can lead to big performance gains. And that's it from me. Thanks for watching.
Hi, I'm TJ, a developer relations engineer, and today I'm going to be talking about building offline first apps. Why build an offline first app, you ask? Apps don't always have access to the internet, but that doesn't mean they have to stop working. So let's learn how to build one. Building an offline first app starts in the data layer, with repositories and the data sources they delegate to. An offline first repository that has network access requires a minimum of 2 data sources, a local data source and a network data source. It's the repository's responsibility to populate the local data source with the network data source. Since the local data source and the network data source often defend the implementations for fetching data, it is often beneficial for each data source to have a distinct model representing the data it provides. Consider a news app that has authors. A local data source backed by SQL, for example, may provide an author entity. A network data source, however, may provide a network author. The semantic differences between these two is purely a data layer concern. They should be kept internal to the data layer, and a third model, author, should be exposed to the rest of the app. Next are the 2 actions that can be performed on data in an app: reading and writing. Let's see how these are affected when going offline first. Reads in an offline first app should be made available through observable APIs like Kotlin flows. This is because data can change between connectivity states, and the rest of the app needs to be made aware of changes as they occur. When writing data, use asynchronous APIs like suspend functions from Kotlin coroutines. This is because writes may cross a network boundary, and we don't want to block the UI thread. For both reads and writes, managing connectivity changes requires 2 main concepts. Queuing till the network is available, monitoring to check network access. Implementing the above follows a linear structure where the implementation of each step varies. For reads, this involves queuing the read, waiting for a network connection, performing the read from the network, and finally updating the local data source. It is important to note the external layers of the app must always read from the local data source. This enforces data consistency in between connectivity states. For writes, the pattern is similar. Writing to the local data source first if the business logic requires it, queuing the write to the network, waiting for a network connection, performing the write to the network, and finally, resolving any conflicts that may arise after the write. Writes in offline first apps typically require more consideration than reads because of conflicts. Therefore, an offline first app doesn't need to be able to write data offline for it to be considered offline first. If there's a failure in any of the above, the solution typically is checking if the operation should be retried, terminating if it shouldn't, otherwise requeuing the operation to be performed at a later time. and finally, persisting the result when successful. When connectivity is restored, an offline first app needs to reconcile data in its local data source with that in the network data source. This process is called synchronization. There are two main ways an app can synchronize with its network data source: pull-based synchronization and push-based synchronization. In pull-based synchronization, the app reaches out to the network to read the latest application data on demand. A common heuristic for this is navigation-based, where an app visits a screen, pulls data for just that screen, then visits another screen, and pulls data just for that screen too. The pros of this is that it's relatively easy to implement. Data that is not needed will never be fetched, and then the cons of this are it's prone to heavy data use when screens are revisited. It doesn't scale well with relational data, as dependent data has to be fetched on demand. In push-based synchronization, the local data source tries to mimic a replica set of the network data source to the best of its ability. It proactively fetches an appropriate amount of data on first startup to set a baseline, after which it relies on notifications from the server to alert it when that data is stale. The pros of this is the app can remain offline indefinitely because a baseline has already been established. There's minimum data use after initial sync, and it works well for relational data. The cons of this are versioning data for conflict resolution is non-trivial. There could also be concurrency concerns during synchronization, and it must be supported by the network. If the app writes data locally when offline that is misaligned with the network data source, a conflict has occurred, and you must resolve that before synchronization can take place. There are a lot of strategies that may be used for conflict resolution. However, a common and robust approach is last write wins. In the timeline shown, both devices have been synchronized and are offline. A short while later, device A writes data locally. A little while after, device B writes conflicting data locally too. Device A comes back online and then syncs with the network, writing its data to the network. Device B also comes back online and syncs with the network, overwriting the data written by device A. Device A is then notified about the change and has its local data updated to match that was last written by device B. To learn more about building offline first apps, be sure to check out the Now in Android sample and the Offline First Guide. See you next time.
Hi, I'm Ben from the Android Developer Relations.
Where to hoist state in Compose. And what state we're referring to UI state, or what you need to display on your app together with the internal state of UI elements. In any Android app, there is also two types of logic, UI logic, or how to display your state on the screen, for example, how to show you a list of messages, and the business logic, which are the rules that make your app, like where do these messages come from and your data sources. Where you hoist your state will be dependent on what type of state you need to apply to this state, what type of logic that reads or writes your state. So let's begin with the case of your UI state living in composable. Let's begin with the case of having to apply UI logic to your UI state, where that logic lives in your composable functions. Perfect. That's it. Okay, so let's consider this chat app. We have a bubble that expands and collapses on tap. If you go to a composable functions, we have a show details variable. It's an internal variable, and the logic applied to it is very simple. So hoisting the state in this case wouldn't bring that much benefit. So we leave it here, making the composable function the owner of this state. So as you can see, not hoisting, it's a valid option. But not hoisting your state makes your UI less reusable, and there are some cases in which we need to apply UI logic to it before sending it forward to other composable functions, and that's where we need state hoisting. Let's consider lazy column, what a lazy column does. Lazy column defines lazy list state parameter with a default value given by remember lazy list state. This means that any column composable can define it outside and passing it down if they need to. Now let's say we want to implement two things. The first, in our chat app, we want a button to jump to the bottom of the list, and for this, the button needs access to the list state. And also, we want to scroll to the bottom of the list when we send after typing a new message, and for this, the user input needs access too. Right now, the current owner of the lazy list state is the lazy column. So what we want to do is to hoist it to at least the conversation screen, so that can be forwarded then to the message list, and the user input can call UI logic, and the same thing, the message list can forward it to whoever requires it. In our code, what this turns out to is you go to a conversation screen, you define the state with lazy list methods, pass it down to the message list, you call UI logic in the user input, and then the message list defines it with a default value of remember lazy list state, just like we saw that lazy list does, as a best practice to increase testability, and then we forward it back to the lazy column and the jump to bottom button calling UI logic to it. What we've done so far is just hoisting the state as required and changing who the owner is, while avoid passing it to composables that don't need it. We recommend placing your state in the lowest common ancestor between all the composables that read or write this state. But when your logic becomes complex, you can abstract your state and logic into a plain class, which will also make your composables simpler and allow testing that UI logic in isolation. And we've had that example of that all along. Lazy list state abstracts the state of a lazy column, storing the scroll position for this UI element, and also it exposes methods to apply UI logic to it, like scroll to item, animate scroll to item, etc. So we covered different cases of where to put your state when you have UI logic applied to your UI states, composables, and play stateholder class. Now we'll see what happens when we have business logic involved. Our ViewModel is a great choice as implementation of the screen level stateholder, which handles the business logic. So what we want to do now? Now we want to fetch user suggestions in a chat space when the user types at and a hint. And of course, these suggestions come from the data layer. So what we want to do is and obviously this is considered business logic, so what we want to do is have the input message or the text field state hoisted to at least the ViewModel, which now obviously takes it outside of the composition. You're hoisting your state outside of the composition. And then your state can be accessed from the conversation screen, and you can also call UI logic through the ViewModel's exposed methods too. Notice that now the ViewModel is the lowest common ancestor and owner of this state. In code, we go to a ViewModel, we define input message with Compose APIs, and by doing so, input message also survives configuration changes because of the ViewModel's scope. And for our suggestions, we define a mutable state flow, apply some UI logic as you receive a new input message, and that's it. You have that emitting, the UI collecting from this flow, receives the new suggestions, update the UI, and everyone's happy. So what we've seen is that when we have built-in logic being applied to UI state or producing UI state, you should hoist that state to your screen-level stakeholder, a ViewModel in our case. And that's our table completed. As a recap, where you hoist your state will be determined by the type of logic that needs your state and that needs to write or read that state. And we've explored several examples from having the composables at the bottom as a source of truth, to hoisting it higher, to extracting or hoisting your state to a plain stakeholder class, or to the ViewModel outside of the composition. We recommend keeping state as low as possible, closer to where it is consumed, and exposing immutable state and events to modify that state from the owner for the consumers. Some more resources for you to learn more include the UI stakeholders and UI production talk from LEB today, and the architecture documentation. That's it. Thank you.
Hello, my name is Connie Shi. I'm a software engineer working on Material U. Material U is the next evolution of material design, which we announced last year. It's a radical new design vision focused on delivering styles that are experiences that are personal for every style, accessible for every need, and adaptive for every screen. Historically, apps have been one size fits all. Everyone got the same colors, the same contrast, and the same text size. Not surprisingly, different users want and need different things from their apps. Some people need very high color contrast, while others want a style that matches their mood. Material 3 is the first step towards making apps not only functional, but also comfortable, whether you're colorblind, need a screen reader, or currently obsessed with pink. So the Compose Material 3 Jetpack library is an implementation of Material U based on the Material 3 design system. The first stable release has just been launched, so now it's a great time to start using it in your apps. Thank you. Let's look at some key features of Compose Material 3. So the library has new features like dynamic color, as well as updated theming and components. The updated theming system gives you more flexibility in expressing your brand. It's also designed to be cohesive with the latest OS visual style and system UI, so your app feels right at home on Android 12, 13, and beyond. The foundation of a color scheme is a set of key colors: primary, secondary, tertiary, error, and neutral. The color scheme provides a set of colors needed for expressing interaction states, errors, and accessible contrast. The type scale contains text styles with simplified naming based on use and size. The shape scale defines the style of component corners, offering a range of roundness from square to fully circular. You can connect these in the material theme composable to brand your app. We recommend using the Material Theme Builder tool to generate color schemes derived from your brand's colors and export a Compose theme. Dynamic color is a key personalization feature of Material U. Starting with Android 12, users can generate individualized color schemes through wallpaper selection. To implement a dynamic color scheme in Compose, start by checking the build version SDK. If dynamic color is not available, we can fall back to using a light or dark color scheme as before. Here we can see a sample app's dynamic color scheme adapt to the wallpaper selection of a user. Compose Material 3 also includes a variety of updates to components like buttons, chips, dialogues, and switches. These updates use the new Material 3 theming values and include fresh new updates to each component specification. We also updated the app bars and navigation components, so now they have built-in window inset support. The library provides 4 types of top 5 bars: default, formerly known as small, center aligned, medium, and large. When scrolled, the top left bars fill with a contrasting color to provide visual separation from the content beneath. The library also has composables for navigation bar, formerly known as bottom navigation, and rail, as well as 3 variants of navigation drawer: modal, dismissible, and permanent. In Material 3, the navigation drawer is decoupled from the scaffolds. There's also a new drawer sheet component to allow easier customization of the drawer content. Using the navigation components together with the Material 3 window size class API allows you to define the right navigation based on the available screen size. There are a variety of other updates to components in Compose Material 3. To get a full overview of the components and how to use them, check out the API reference on developer.android.com. It's a great time to use Compose Material 3 in your Android apps, and we've prepared tools to help you get started. First, all new Android Studio projects will use Material 3 by default. We've also updated the Material Theme Adapter library and the Material Theme Builder tool. Next, there are new guides on Material 3 and migrating from Material 2, as well as associated code labs. Lastly, the Compose samples and the Compose Material Catalog app have also been updated. To learn more about building with Material U, please check out these talks. Thank you.
Hello, my name is Leland Richardson, and I'm a software engineer working on Jetpack Compose. Today I'd like to talk to you about modifiers. And as the title of the talk suggests, I'm going to take a little bit of a deep dive, and that means that some of this content might assume a little bit of knowledge about Compose, but I'll try to do my best to walk you through it. Okay, so to start, I want to provide context on the design decisions that led to the current modifier design. And then I'm going to talk about how modifiers are getting used differently than we initially expected and how this impacts performance. Finally, I'm going to talk about some major work that's been going on recently. And this has really changed how modifiers have worked under the hood, and some new experimental APIs have showed up that we believe result in significant performance improvements. So some of you may have noticed that the first major milestone of this effort landed in the first beta of Compose UI 1.3. This was titled Modifier Node Refactor, and this was a completely backwards compatible change and should not have had any effect on your app, but it was the first step in enabling this major shift in modifier architecture. So first, let's talk about how we got to the current modifier design and what was considered along the way. So first and foremost, Compose was built to manage trees. And in Compose UI, the nodes of this tree are described by an interface called Compose UI node. We often refer to these as layouts or layout nodes, since in Compose UI, the only way to create them is through the layout composable. And as we can see here, modifier is one of the parameters that layout accepts. But let's take a step back and imagine that we're creating a UI toolkit from scratch, and we have no notion of what a modifier is or what we might use it for. So in our imaginary UI toolkit, we're going to probably have a base node type. And whether this is an interface or a class doesn't really matter. But there's going to be certain cross-cutting concerns that we're going to have to make sure that our UI can handle. So for example, we want users to be able to click or press on a node and then to be able to execute code as a response. So we'll add an on-click property. We also might want our node to have a background color. We want to be able to specify padding around the node to separate it from the others. And so we might play around with this for a little while. And then we might realize that, okay, well, padding might not be the same in all directions. So we update it to have one property for each direction. And as we kind of keep going down this path, we can start to see how the strategy might not scale. What if we want to not just have solid backgrounds, but gradients? What if we want not just an on-click handler, but an on-long click? Or better yet, a more general gesture system? So these types of cross-cutting behaviors are things that we want every node to be able to do. But there are so many things, and most of the nodes won't utilize almost any of them. So we learned from our prior mistakes, and we didn't want our base node type to have the weight and cost that was needed to enable all of these behaviors for every single node. So we started exploring other options. Another option we explored was instead to encode each one of these behaviors as a node in the tree itself. So in this case, padding, background, clickable, these were composables themselves and added to the tree. So with this approach, there's some syntactic overhead, there's a little bit of nesting of lambdas and things like that, but overall it works pretty well. The main problem with this approach was that each behavior composable then also had to have a content lambda parameter. And this is where its children would go. However, we were thinking of these things as single children composables, but there's nothing stopping you from sort of having multiple children. In Compose, composable lambdas can compose arbitrary content, and we didn't want that to change. So in this case, we have to answer the question, what happens when you put multiple children below clickable? Do we stack them vertically, horizontally? What? So in order for this to work, clickable would have to encode some sort of a layout policy in it. But layout policy isn't really something that we think of clickable needing to know about. And so in reality, we expect layout composables like row and column to be concerned with layout, but not any of the other things. And so in the early days of Compose, we kind of went with this approach, but it ended up being a little too error prone and confusing for users when this was an issue. And eventually we decided that all composables needed to allow for multiple children, and that everything needed a layout policy, and that was just how it was going to be. The other behaviors, we ended up deciding that it was okay for this to be passed in as a parameter, for these behaviors to be encoded in a thing that we ended up calling Modifier. And so with this approach, one of the neat things that happens is that you're allowed to pull out modifiers as an expression and do a temporary variable, and then pass that into multiple layouts as a result. This is a pattern that we liked, but it's actually trickier than it might seem to make it work. Consider the case of clickable. Clickable has stateful behavior in it. If you think about it, it tracks touch up, touch down, has delays, and there's even ripple effects. So critically, if we end up passing clickable into multiple layouts, we need to make sure that that state ends up getting created per layout. It's possible for 2 ripples to be going on at the same time, for instance. And in order to handle this use case, we came up with a new API, modifier.composed. And modifier.composed allows you to define a modifier with a composable lambda factory, and that itself is a function that returns a modifier. And so in that lambda, since it's composable, you can leverage compose to manage state for the modifier that it produces. And the whole special thing about this API is that this ends up getting called per layout. So the state ends up being per layout like we needed. We do this by having a materialize API. And so this materialize call takes in a modifier, some of which might be composed modifiers. And then we end up returning a modifier that's semantically the same thing, but all of the modifiers have sort of been expanded by calling the modifier.composed lambdas. We then ensure that materialize gets called before every node that it gets applied to. And so then the modifier that ends up getting passed to the layout is the one that is fully expanded, and then the state for those modifiers is living in the compose hierarchy. So an implementation of clickable could look something like this, right? In this case, we're using remember to create some state, and then that state is going to have the lifetime of the node. And this sort of solved the problem, but it didn't do so perfectly. The modifier.composed API introduces a few performance issues. One of them is really about skipping. So even though we're using composition, one of the key levers that can make composition efficient is to be able to skip functions. But we can't skip functions that have a return type. And in this case, modifier.clickable has a return type because modifier.composed has a return type. And so every modifier that used modifier.composed would be unskippable as a result. because the function that calls modifier.compose isn't composable itself, we can't leverage the compose compiler in order to cache the lambda that it uses. And this means that the resulting modifier will never compare equals with the one before it. This is a pretty big issue because modifiers being comparable is actually the only way for us to determine if something has changed during recomposition. So in this case, every modifier will look like it has changed even though it hasn't. This also meant that modifiers that were stateful required a lot of remember calls in order to make sure that state updated while other state didn't. Because these end up getting composed every recomposition, these remember calls kind of add up. And they ended up being more expensive during composition than we initially expected. But despite these issues, we kind of figured that modifier.compose would only really need to be used in a few special cases. We were wrong. So in practice, we've seen that modifier.compose gets used a lot. And it's really shaped the way how modifiers work in practice. So let's take a look at an example. Consider the small example of a counter. We have a column with two text nodes. One displays the count, the other has a clickable modifier. One way to think about this is that this will produce a tree with one column node that has two text child nodes, where each text node has a text property and a modifier property. Each modifier, so one way to think about modifiers is as a lens through which everything above it sees the thing below it. So we can think of clickable as being part of the same overall tree. And it has the child text node. And the reality is that Compose UI doesn't produce columns and text. It produces really just layouts with modifiers applied to them. And so in the same way, text isn't really a text at all. It's just a layout. And we can start to think of the unique behaviors of a text composable as really just being a layout with a text modifier applied to it. So this is, what we have here is like a pretty reasonable mental model to have for the resulting tree that Compose produces. But it's actually still pretty far from the truth. In reality, there's no single text modifier that we have. Instead, text is made up of several modifiers that are required to encode the behavior of a single text element. And likewise, clickable also isn't just a single modifier. Clickable ends up using several modifiers to encode all of the things that a clickable needs to do. And this still isn't really the complete picture. There's several modifiers here that would also end up using several modifiers as a result. And to be honest, this also isn't the full picture, but I ran out of room. So the result is quite a large tree, and it's composed almost entirely of modifiers. And so instead of building a tree of layouts, we're really building a tree of modifiers. Going back to our example, this tree was produced from some pretty innocent looking code with just a single modifier visible. If we go and look at this modifier, so modifier.clickable in this case, we can see that it called modifier.compose 13 times. It had 34 calls to remember, 11 side effects, and this all resulted in 16 modifier elements in the final tree. So what does that mean? Let's try and understand the impact of this. And let's take a better look at like what the life cycle of a modifier is and what the costs associated with them are. So we can take a simple example of this chain of 4 modifiers. And this modifier chain is going to get initially created during composition. While initially this modifier has 4 modifier elements, one, as we saw earlier, is a composed modifier. This modifier will then get passed around, and eventually it's going to end up getting applied to a layout node. And as I mentioned earlier, this is where we expand that composed modifier by calling that materialize function. So this will end up executing the composable lambda that was used to create clickable, and it's going to result in several more modifiers. And we can think of then the state that is built up during Compose as living alongside these modifiers here. And as I mentioned, this isn't the complete expansion. This is actually going to get materialized called on a lot of them, and we're going to recursively kind of go down, build up a tree. And so just to keep the slide manageable, let's just abbreviate this by saying, we've got many modifier elements, a lot of which end up having state that live alongside them. And so after we're done materializing the full modifier chain, we call set modifier and apply the modifiers to the layout. And in this case, when the modifiers are applied, we end up allocating these sort of owning objects for each modifier. And we call these entities, and they're really an implementation detail, but in a way you can think of these objects that they're objects that manage the behaviors between the different subsystems and dispatch things to these modifiers. So in a way, this is what the resulting tree looks like from our initial composition, but that's only half the story. What happens when we recompose and update the tree? So let's say that this time we have 16 dp of padding instead of 10. So we've updated something. During recomposition, we end up reallocating the original list of modifiers. Eventually, we again reach the point where we need to apply this chain of modifiers to the layout. And like before, we call materialize, and we expand the modifier. And at this point, the state that was previously remembered is going to be reused for these new modifiers. So both the entities and the modifier elements on the layout end up getting disposed at this point, and we apply the new modifiers to the layout, and we end up allocating new entities to deal with these new modifiers. And so the key thing to understand here is that many of these modifiers need to have state, and that state, it's critical that that state ends up being per layout node, per layout that they're applied to. And there wasn't really any API to enable doing that except for modifier.compose, at least not until recently. So the recent major changes that I alluded to earlier are meant to address precisely this issue. So let's take a look through the example that we just walked through, but instead look at what this will be like when we finish the migration of modifiers over to this new modifier.node world. So this refactor included an addition of a new abstract class, modifier.node. This is an addition to modifier and modifier.element. It doesn't replace these types, but instead works in addition to them. And it's probably important to clarify that these APIs are still experimental, and we're still validating different use cases and ensuring that they have the right API shape. As a result, the rest of this talk isn't really going to go into the details of the API, but really just talk about the general idea. So let's take a look at that same example and walk through it. During composition, we allocated a new modifier chain. And critically, these are all modifier elements. Importantly, clickable would no longer be a composed modifier. Instead, all 4 of these are a new type of lightweight, immutable modifier.elements, which know how to maintain an instance of a corresponding modifier.node class. So eventually, we go to apply this modifier to a layout. And this is significantly cheaper than before. Since there's no composable modifier, before we would need to do a lot of composition at this point in order to materialize the composed modifiers into modifiers. Now clickable is just a single element, and no materialize is needed. So we just pass in the modifiers directly as is. At this point, each modifier element then gets a modifier.node, gets a create function called on it, which then allocates a modifier.node instance. These node instances are directly part of the hierarchy. And they have the same life cycle as the layout that they're applied to. And as a result, these objects are ideal owners of state for the modifiers that need it, like clickable. So then what happens when we recompose? Just like before, let's imagine we recompose with 16 dp of padding instead of 10. We allocate a new modifier chain. And now that these modifier elements are immutable, we can very easily compare them. And this is important because if nothing in the modifier had changed, which is a pretty common scenario, then Compose would have been able to skip early and might not even needed to apply the modifier at all. And so, but in this case, the modifier chain has changed. So we do have to set the modifier. And when we do that, Compose then diffs the previous list of modifiers with the new ones. And each of them are comparable, and so we can update only the modifiers that have changed, which in this case is just padding. The rest of the modifiers were the same, so we simply do nothing for all of them. So if we go back to our early example, we can see that with modifier.node, we're able to get from a tree like this back to our nice mental model of something that looks like this. So as you can see, there are several benefits to doing this way. One is fewer allocations. We don't have to reconstruct the chain during materialize. The chains themselves are shorter, and we don't allocate entities on the layout every time we recompose. The other is that there's just less composition going on here. There's no need to remember state or use snapshot state to proxy updated parameters. And so there's a lot less overhead that comes along with modifiers. And then finally, the tree itself is just smaller. Modifiers like clickable result in a single node instead of 16. Subsystems that are traversing the whole hierarchy are going to have a lot less work to do. So this sounds nice, but what does this mean for you? So first, you can expect that in the next few releases, you might be seeing some pretty significant performance improvements. So that's good. Second, if you're using Modifier.compose to create custom modifiers, then these new experimental APIs might be something that are worth looking into, especially as they stabilize. And third, it's important to understand that pretty much all of userland code won't need to change. This is a pretty big deal. When I first started working on this, I was pretty concerned. I was concerned that I wouldn't actually be able to make the changes necessary to do these performance improvements. And at Google, we try to be really thoughtful about what public APIs we put out there, and we only make public what's absolutely necessary. And so this can sometimes be really frustrating to developers like you because it feels like we're actively preventing you from using these useful APIs. But this was absolutely critical in enabling us to essentially rewrite the whole modifier system. And that's maybe the single largest API service in Compose. And so to do it in a completely backwards compatible way is a really great thing, and I'm really glad that we were able to do that. So I'm going to end and just say stay tuned. We're going to continue working on this, and let us know if you end up seeing any performance improvements as a result of this, or any issues that come along. I'm going to be around all day to talk about this if any of you have any questions. And yeah, that's it. Thank you.
Hi, my name is Daniel Santiago, and I'm here to talk to you about database migrations with Room, not a Compose talk. All right. To start, not every database needs to be migrated. So just letting that out. If the data on your app is some sort of cache, or if the source of truth is your server, then there might not be a reason to perform a database migration. For these cases, Room can simply recreate the database when the app gets updated, and you can enable this via the fallback to destructive migration API in the builder. However, and this is the important part, if the data on your database is indeed the source of truth, then it is very important to perform that schema migration, because otherwise it can be a very unpleasant experience for a user to update their app and to lose it. All right, so how do we get about doing that? Well, with Room, it can be quite easy. In Room 2.0, you can take advantage of auto migrations. You simply define the from and to versions where you want to migrate. Room will look at the schemas, analyze it, and create a migration implementation. It's important to know that exporting the schemas is mandatory for auto migrations to work. Auto migrations can handle most things out of the box without any additional input, adding new columns, adding new tables, changing foreign keys, indices, and views. However, there are certain cases where auto migrations need a little bit more information. In this example, there's a table rename, and Room is looking at these two schema files, and it can't quite really tell whether a table got deleted and a new one with suspiciously similar columns was created. For these type of cases, what you can do is provide a migration spec, and in this migration spec, you can annotate it with one of these annotations to help resolve this ambiguous situation. There's 4 total annotations you can use: rename column, rename table, delete column, and delete table. The other cool thing about migrations is that Room will actually take the old data from the old table and transfer it to the new table. But be aware that there might be certain schema changes where you might need to do a little bit of extra processing, and you can do that on post-migrate in the migration spec. And one example of that here is if we had a column that was a Boolean and we were trying to change it to an enum-like string where we change the affinity. For these cases, then you can implement that on post-migrate and execute some queries to get your data where you want it to be. Now, if data processing needs to happen before the migration, then you can use a manual migration with an auto migrations. And since manual migrations and auto migrations are compatible with each other, you can have them back-to-back to perform 2 version bumps. The idea is that in your manual migration, you perform the necessary data changes in preparation for that auto migration. I'll give you an example. One example of this is if you had a table and you wanted to add a new foreign key, but the child table has invalid references to the parent table. So what happens is if you were to add the foreign key, a foreign key constraint failure will occur. So what you do is in your manual migration, you write the necessary queries to sanitize the data and get it ready for that auto migration to then add that foreign key. Some migrations are just easier when SQLite is there to help you. For example, if you add a new column that is not null, then you need to provide a default value. And you can do this with the column info so that when Room migrates the data, it fills the existing rows with the default data that you specify. Nice. So migration bugs are not very common, which means that it's an area often overlooked during testing. But it's really important to test your migration because they can lead to some really bad bugs. Especially they tend to lead to databases and apps getting into a crash loop because they're trying to update the database and failing, and the user ends up reinstalling the app and they lose their data. It's not great. The good news is that Room does offer APIs for testing migrations, including auto migrations. And our recommendation is that you write a test for each version bump that you do. It's also good to put some data on the database so that you can then verify it. To do this, you use the Migration Test Helper API, and it will enable you to create the database at an older version. You put some data in it, and then you use run migrations and validate to go over manual migrations or auto migrations, and then you'll get a database that has been migrated, validated, and then you can verify the data on it. So run migrations validate will also find those auto migrations for you. And that's really it. Thank you so much. You can find more information in that link over there, and that's it. Thank you.
Hi, everyone. My name is Ian Lake, and I'm here to share 5 best practices for writing type-safe, multi-module code with Navigation Compose. That's a lot. So let's just go step by step. The first step is in defining your screens. So if you think about the simplest single-screen app, you could just put all of your content directly in set content. But as soon as you get more than one screen, it's going to make sense to move those out into separate methods. So best practice number 1, define your screen in terms of the state it receives as input and the events that it outputs. Your screen shouldn't care if your data comes from a ViewModel or it's just static state that you've created for an individual test. It also shouldn't care about who's receiving the events that it's sending out. This is just a generally good idea for any of your composables, but it's particularly important to make sure that each one of your screens is testable in isolation and works great with previews. Next, best practice number 2, split up your navigation graph just like you split up your screens. Just like moving your entire app out of set content, Your entire navigation graph, the definition of all the screens of your app, should also be split up down to that same per screen level. You do this by pairing your screen with a nav graph builder extension method. This layer fully separates the navigation-specific code from the screen itself. And it provides encapsulation around navigation-specific concepts, like routes, the unique identifiers for each screen, which should never leak outside of this individual file. This is also the same layer where you provide where the state actually comes from. For instance, from a ViewModel scoped to this individual screen. Events that can be handled at this individual layer get handled here. So, for example, if you want to hand off an event to your ViewModel, do that here, while other events that can't be handled at the individual screen layer need to be passed up a level to the navigation graph. Number 3, build out only the public API surface that you need. Now, that single extension method provides all of the runtime verification, such that when you navigate to a destination using the nav controller, your arguments are correct, typed, and that all the required arguments are already there. Now, Navigation Compose doesn't generate the compile time type safe code for you yet, but that means that you get complete control over the type safe code you want on a destination-by-destination basis. This is the type safe code you put right alongside that nav graph builder extension method. So at minimum, this should include an extension on the nav controller, our stateful object that maintains the backstack, that fully encapsulates how you reach that destination. Now, it could also be extended to provide a type-safe wrapper around extracting arguments from your save state handle for your ViewModel. Now, this is where the Kotlin visibility modifiers really come in handy. By using internal, we separate out the internal implementation details of a module from the public API surface that module provides to other modules. Now, this same concept of choosing the right visibility applies to modules that have multiple screens as well. This self-contained set of screens is called a nested navigation graph. This lets you roll out multiple screens into just a single nav graph builder extension that encapsulates all the screens as an implementation detail. The key part of this encapsulation is the navigation element that wraps all of those individual screens. Now think of this as one level up from our individual screen builders. Since we're in the same module, we can access our type-safe methods and link these screens together in a totally type-safe way that's transparent to any other module. Now, this also gives us control over how we want to start that flow. For example, our nav controller extension that navigates to the whole graph might set up the right flags so that it's treated as a separate backstack when you're using a bottom navigation bar. That takes us to best practice. Number 4, use your module structure to guide how to combine your graphs together. Your module structure and how you've decided to modularize your app already defines which modules have visibility to the public APIs for other modules. So that means navigating across modules is really just bubbling up those on-navigate events up to a level to the module that has access to both. So it's at that higher level where you have the nav graph builder from one module and the navigate method from the other module, both visible, that you can tie them together in a type-safe way. Now, there's a lot more details to cover, so best practice number 5, check out our updated documentation and see all these in practice in our sample app now in Android. Thank you.
Good afternoon. My name is Jerome Daucher. I am the tech lead for the Android Gradle plugin. And I'm here today with Boris Farber, a developer relations engineer. And in this talk, we're going to introduce what is new in Android Gradle plugin. It's 0. So the agenda is the new features. We're going to shout out some of the new features we have. Then Boris will come and talk about some of the behavior changes that we introduced. talk about the behavior analyzer, and then I will come back to talk about a big change in terms of API support, which is the transform removal. So it is something that if you are using, you must be aware that we are removing. So it's an API change. So let's talk about the new features. And the first feature I want to shout out is the DSL variant API. So I personally have talked about this many times already in previous ADS last years and 2 years ago. So I'm not going to get into much details today, but I just want to say that now this interface is stable. It is safe to use. We are not going to change it unless we go through a normal deprecation period. And it is definitely a huge improvement in terms of usability compared to what we had before. So have a look. It's ready to be used. Next thing is support for text fixtures. So this was something that was really requested by a lot of our users. So if you develop a library and you want your users who are using this library to have the ability to mock some of your interfaces, to be able to test more easily with your library, it's a neat feature that was developed by Gradle, and we added support on the Java side of things. In 8.0, we are still working on the Kotlin side of things because it involves the Kotlin Gradle plugin, so it's a bit more complicated, but it's going along as well. And so now you have the ability to define text fixtures for your libraries, and you have the ability to consume them and use them in your test projects. The next thing is incremental Kotlin support. So as you probably know, at the beginning, the incremental Kotlin support was relatively shaky. Each time you would make a compilation mistake, it would start from scratch again, and we would completely move away from incremental to a full build. So now we've added a lot of support for incremental plugins, for incremental compilations, sorry. And so it really has changed a lot, the build speed if you're doing Kotlin. As you know, the Kotlin compiler is not nearly as fast as the Java one, so it was one of the feedback we got. So by working with making it more incremental, at least we are closing the gaps in terms of performance. It's still not as performant as Java, but it's a better language, so I think we all can bear a little bit of performance in compilation to have access to all these features. And finally, I want to chat about configuration cache. So configuration cache is a feature that we developed with Gradle. And that is really a huge improvement compared to what we used to do before. So before, as you probably know, the configuration cache is this stage in the build of Gradle execution where we basically constructed the task tree, right? It is all the tasks that needs to be eventually run, and that takes time. It's relatively slow. Depending on the size of your project, it can actually become real slow, maybe a couple of seconds, maybe 10, 20 seconds, and this is a cost that you were paying every single time you build. And so this was really annoying, obviously. And so we worked with Gradle to introduce this feature where we can actually cache this information. So basically, we can cache the task tree and can reuse it, and it makes the configuration cache a lot faster. So it's still not like, disappeared. We still have to get it from the cache, but usually it's a local cache, so it goes really, really fast. So it is now something that is not fully stable. There is a flag that you can use to turn it on, but we are working hard with Gradle to release this feature to stable by the end of this year. And so it would be really, really useful that you try to turn it on, and if you find issues, to please report them, because we would like to fix those, obviously. And so look at the documentation about the name of the flag. It really is something that will really improve your build speed and your iterative cycle, so I really recommend using it. And Boris will now talk about the behavior changes.
Thanks, Jerome. So here are the behavior changes. The upgrade assistant will guide you through most of them. However, as Android developers, we need to understand the changes and their impact on our app. Let's start with the first behavior change. The namespace property is now mandatory in the build.gradle. Namespace is a Java or Kotlin package name for generated R classes and build configs, replacing the previous package attribute in the Android manifest. To understand why we are making this change, let's take a look at the previous behavior. Previously, the package attribute was used both for setting the application ID and R classes, unnecessarily coupling the two mostly unrelated concepts. On top of that, the application ID could also be set in the app.build.gradle file, creating confusion as to the source of truth. By disallowing setting the package name in the manifest file and introducing the namespace property, we are cleanly separating the application ID used for your app identity and the R class's namespace. This ensures that there is no confusion to where the value comes from, and that you can freely refactor your app code and resources without affecting your app ID. The namespace property is available from AGP 7.3 and enforced from AGP 8 Alpha 3. The Update Assistant will help you to migrate from the package attribute in the Android manifest to the namespace entry in the build.gradle. The next behavior change covers the following features that are off by default: config class generation, AIDL, and the render script compilation. pconfig is a Java file containing static information about your current build, such as package name, flavor name, debug flag, and others. Previously, the build config was always generated. If you develop a multi-module app, you can end up with a lot of big config files that AGP needs to process that affects your build speed. Most modules will likely not require any of the information from the build config class. For modules that do rely on it, such as the app module, you can re-enable it by adding the snippet to the module build.gradle file. If you still want the old behavior for the entire project, you can set this flag in your Gradle properties. However, you shouldn't do it, as it creates a lot of unnecessary files. Another thing worth mentioning is that build config is a Java file, which, assuming you use Kotlin, further affects your build performance. You can use similar methods to re-enable AIDL or render script for modules that require it, or for your entire project. However, please note that render script was deprecated in Android 12. The next change is R classes are not transitive by default. As you know, R classes are the generated classes that map your resource names to IDs in your application code. Until Android Studio Bumblebee with AGP 7.1, AGP generated keys not only for the library R classes, but also for all its dependencies. This generation resulted in bigger executable size and longer build times. In non-transitive behavior, each R class includes only the resources declared in the module itself, thus reducing the size of the R class for that specific module. And of course, Android Studio helps you to refactor your project from transitive to non-transitive R classes. The transitive R classes behavior is controlled by the non-transitive R class flag set in Gradle properties file. This flag was introduced in AGP 4.1 from Android Studio Bumblebee with AGP 7.1. It is set true for the new projects, and from AGP 8, it is true when not specified, and thus becomes the default. And the last behavior change, await is now in full mode by default, enabling even more optimizations. If your keep rules were configured correctly, there is no action needed for this change. However, you might need to double check that your project builds correctly with the new optimizations enabled. As we finish the behavior changes, let's discuss the build analyzer, an Android Studio UI feature. Downloads are often neglected area in the build performance. Let's see how Build Analyzer can help you there with a new tool that helps to visualize the downloads information. As you know, Gradle searches plugin and dependency repositories in the order they are declared. Let's trace a simple dependency fetch, say Android X Compose UI. First, let's look at the Maven repo. Not found. Yeah, then let's look at the Maven Central. Also not found. Finally found in the Google repo. Here's the problem. Your build might spend time on redundant network calls from the repositories listed first in the repository blocks. The solution is repositories listed first should contain most of the dependencies and plugins. In now on Android, we improved the sync time by experimenting with the repo order. If you see a number of failed network attempts with time, this means you should experiment with the repo order and use Build Analyzer to track the impact. The Build Analyzer can also help you spot other build problems, such as dynamic versions. Dynamic version is a dependency version that uses plus or multiple wildcards in the dependency declaration. Dynamic version causes Gradle to make network calls to fetch the latest dependency versions between the builds. You obviously should not be using them. If you are using dynamic dependency versions, you will see downloads right after running incremental builds. As we finish sharing what's new for app developers, I want to share what's new for plugin developers. So back to Jerome.
Thank you. Yeah, so I'm not sure that's new because we actually remove it. But basically, the idea here is that we have finally removed the Transform API, and this is going to have some impact. So the Transform API has been deprecated for quite some time, and we removed it in 8.0. The reason why it's been removed is that, first of all, it was not a very easy-to-use API, and second, it has this tendency to create bottlenecks. So it was both not very performant and hard to use. So we tried to do a new solution, which is going to be more performant and easier to use. I'm pretty confident that it's going to be more performant. We'll see if it's actually simpler, but we at least tried. There's not going to be any help with removing the Transform API with the Upgrade Assistant. And the reason is that it was basically code that was basically interacting with the build system. So the build assistant cannot, or Upgrade Assistant cannot really help you with changing your code, which was using one set of API, to new code that uses a completely different set of API. In particular, we've replaced the Transform API with two sets of new API. One is called the instrumentation, and the other one is the artifacts API. So we're going to delve into some of the details about why we have two, but basically you can see it as very different needs, very different solution. So let's talk about instrumentation first. Instrumentation is basically when you have the requirement of bytecode enhancing, for instance, your class file, right? So your class file just got compiled, and before they get dexed, you would want to go through the bytecodes and maybe add some logging statements, some security things, who knows. And that's a very common usage pattern of the old Transform API, was to just do that. You could do this today by basically using the artifacts API, for instance, that we've had for quite some time, but that is forcing everybody to go through the stages of loading the class file, doing the bytecode instrumentation, writing the class file. Now, if you think about it, that there can be several of these transformers chained together, it becomes very quickly very inefficient, right? Every one of them will do load, transform, write, load, transform, write. So it takes forever. So basically, what we came up with is an API where we take care of the loading and the writing, and then we call back an ASM visitor that can be chained with other visitors, with everything that gets registered. So that means that it's only loaded once, then you have the chain of visitors that will transform the bytecodes, and eventually this will be written once. So it should be much more performant and also easier to use because you don't really have to care about incrementality, you don't have to care about loading the classes and where they're from and stuff. You will be called, your visitor will be called with the right class files when it's the right time. How do you do ASM? I'm not going to get into these details. This ASM library has been around forever, like at least 20 years. Basically, you write a small visitor type interface where you can visit methods, you can visit fields, you can visit outer classes, interfaces with the parent and everything. So it's really convenient. Obviously, this is bytecode manipulation. This is not as convenient as source files, but at least it's machine readable. It's very easy. So you write yours and you do whatever you need. Again, plenty of documentation on the web. ASM is a public open source API. Look at it if you're interested. And then you register it using a factory method and then you register your factory using the variant API. So basically, you just say, on this variant, I want to have this particular factory that will eventually create the visitor. This is the only thing you have to do, and then, like I said, we will take care of all the steps related to Gradle, about incrementality and caching, and all that kind of stuff. That's one usage of transforming your classes. Sometimes your usage is a bit more complicated. Maybe you don't want to change existing classes, but you just want to add classes, for instance, right? So very different usages. And in this case, you want to go through the artifacts API, which is the other API I talked about earlier. So this is really a good API if you have some generated classes that maybe uses something else than a language as an input and generates some classes that needs to be added to your final deliverable, to your final APK. So to do this, it's not convenient to use, obviously, a bytecode transformer because you're not interested in changing code. You're just interested in doing new things, in adding generated classes. So you can do this with the artifact API. It's, again, relatively easy. What you have to do is to write a task that will basically either produce new things or, in this particular case, modify existing things. So here is a bit more complicated example. This is a case where you want to have access to all of your classes and create a new version of them. You can add stuff, you can remove things, you can basically do whatever you need. The result of this task execution is that a new set of classes will be available throughout the pipeline of the build system and will be used for the dexing part, okay? So if you want to interject yourself between the compiler and the dexing, this is a way to do this. So the modify classes task here is relatively easy. You have input files either as directories or as jars, and your job as the task action is to take those inputs and create a single output file, which is going to be a jar file, which is here denoted as the output. Okay? I'm not going to get into the details about what you need to do in the task action, but it's relatively easy to understand. And then you need to register this. So here, this is like, again, probably the most sophisticated example of how you need to do this, but basically you create a task provider where you create your task, and after that you can use here the artifacts API. As you can see, the variant.artifact is how you access the artifacts API, and here you're saying, look, I want to have access to all the classes for my project scope, and I want to use that task to change all these classes, basically. And you indicate these are the input fields, the out jars and all the directories, and you indicate where the output will be placed. Once you've done that, you've basically introduced or interjected this task inside the build, and whenever the compiler is done, your task will be called, and whenever the dexing will happen, we will use the result of the output for the dexing part. There's nothing else you need to do. The wiring will happen automatically. So what does that mean? You need to use this new API because we are removing the old one. We've provided a lot of examples in the Gradle recipes GitHub project that you can go to. There's about 20 to 30 examples, both in Groovy and in Kotlin script and in Kotlin using plugins. So really it's good inspiration if you really need to use these APIs to change manifest, to change dex. You can change your dexes the same way. You can change also classes, like I just showed. There's a bunch of different things you can change, and this gives you an example of how to do things. All right, so what do you have to do? Well, if you use the Transform API today, you need to change to the new ones, because in 8.0, we are going to remove the old Transform API support altogether. There's no choice around this. If you are an app developer, you probably didn't use those APIs directly, but what you may have is you're using a plugin that was using those APIs. For instance, the Hilt Gradle plugin that was delivered 2 years ago was using the Transform API. So even though you're not using it directly, you were using it indirectly, and that needs to be resolved. And to do this is basically most of the time we worked with the most used plugin community, and we've tried to tell everybody to change their plugin implementation to get rid of this old Transform API. So you need to basically update to the latest version, right? So if you start having issues with the Transform API, look into either your sources. If you don't use it, look into your plugins, see if there is a newer version that fixes the problem, and upgrade. Otherwise, well, you have to go back to the plugin author and say, look, your plugin is incompatible, you need to change it. If you need to learn more, there's those links. The Gradle recipes, again, is very important. I have good examples, and then there's some more documentation about why and why not remove those things, and some of the other changes that Boris talked about in the release notes. Thank you very much.
Have you already learned the benefits of Jetpack Compose but aren't sure where to get started with converting your view-based app to Compose? I'm Chris Ariola, a developer relations engineer on the Android team, and in this talk, I'll answer that question by showing you how you can migrate. So, you have an existing view-based app and you want to convert it to Compose. But of course, you don't want to stop building new features just to make this migration. The good news is Compose was designed with view interoperability right from the start. So you can make this migration while still adding new features to your app. Here's an overview of the strategy that you can take. First, start your adoption of Compose by building new features in Compose. This way, the features you build take advantage of the benefits of Compose. While building features in Compose, you want to identify which components can be reused in other parts of your app, and then start building a library of common UI elements. And lastly, continue your migration by replacing existing screens to Compose one screen at a time. These steps don't necessarily have to happen in sequence. Depending on your team size and your app size, these can all happen in parallel. So let's dive into the first step, which is to adopt Compose and new features you introduce in your app. This approach to migrating allows you to modernize your app while still addressing business needs by being able to add new features. If your feature takes up an entire screen, you would still be working under the constraints of your app's architecture. So if you're using fragments, you would create a new fragment with its contents in Compose. And if the entire screen is in Compose, you would return a Compose view in the fragments on create view lifecycle method. And then you would provide the fragments composable in the set content method of the Compose view. If the new feature you're adding is part of an existing screen, on the other hand, you would add a Compose view to the view hierarchy just like any other view. And if you have multiple Compose views in the hierarchy, you want to make sure that you have unique IDs so state is preserved across configuration changes. So as you're building new features, you'll probably realize you're reusing a lot of components. So to encourage reusability, consider creating a module of common UI components in your app. This would be a great opportunity to work with a designer in your team to help identify what those components are. Think buttons, app bars, chips, and so on. This technique is especially useful if you're building a custom design system for your app. Try to also find complex UI components that can be reused, like dialogues, cards, and so on. The features you build can then depend on this component library, which allows you to style and change the look and feel of your app's components all in one place. The last stage in your migration is to incrementally migrate existing features one screen at a time. Note that it's also best practice to rely on UI testing while migrating existing screens to ensure you're not introducing regressions during migration. So how do you go about migrating existing screens? A good place to start is to try to find simple screens. These are low-hanging fruit, as migrating these screens can be done in a few lines of code in Compose. The next place to look for are mixed screens, so screens that contain a bit of Compose code already. For these screens, you can take the bottom-up approach of migration by piece migrating UI elements until the entire UI tree is in Compose. Keep repeating this process until all your screens are in Compose. Assuming you're using navigation component and all your screens are in Compose, what should you do about fragments? Once all your fragments' contents are in Compose, there's really little benefit that fragments give you at that point. So at that point, once all the contents are in Compose, you can remove fragments entirely and replace them with a corresponding screen-level composable. You can then use Navigation Compose to navigate and pass data between these screen-level composables. If you're ready to get started with migrating to Compose, make sure to check out our documentation, Adopting Compose in Your App, to learn more about implementation details. And if you want to learn more about case studies on different strategies that work for other teams, check out our Adopt Compose for your teams page at this link. Now, you should know where to start. Thank you.
Hello, everyone. You've made it. It's the last talk of the afternoon, the headliner, the one you've been all waiting for, how you can test at scale with Gradle managed devices. My name is Adarsh Fernando. I'm a product manager for Android developer tools. And before we kind of get into what are Gradle managed devices and why you should be using them, I think we can all take a moment to appreciate that Android ecosystem is quite diverse. Lots of different screen sizes, form factors, OEMs. And while that diversity is great for users, for quality-driven teams who want to catch issues across all these devices before they hit users, it can still be a real challenge. Now, Android emulators does provide a lot of flexibility in allowing you to create those different types of device shapes and sizes across different API levels, but properly leveraging them to run scalably and reliably on your CI is still a challenge. That's why we've worked on Gradle managed devices. What if you could just describe to Gradle the devices you want to run your tests on, and then it tries to do so in a reliable, optimized way for you? Well, let's take a look how that would work. Well, in the initialization phase, it creates the devices you ask for, including downloading SDK components as required. It creates a zero-state snapshot that it can then snap the devices back to between test runs for more consistent test results. And then as it's running your tests across those devices in parallel, it's also generating a test cache, so it can automatically skip tests that don't need to run again. Finally, it tears down your devices, releasing resources back to your workstation for its next job, and then generates the test artifact that then you can use to open up in a browser or an Android Studio. Now, this all sounds great. How do you get started? Well, it only takes a couple of lines in your build.gradle file, starting with the manage devices closure. And in this closure, we define a device. Here, we're defining the Pixel 2 device that's running API level 31 and uses the AOSP image. We could use Google if we wanted the Play Store, but we're going to stick with AOSP. And just as easily, we can run our tests on that device using the Android test task, modified with the build variant and the name of the device. But we want to run the tests on more than one device. And you can do that. You can define multiple devices and add them to a device group. And then just as easily, run your Android test task against that group, and Gradle Managed Devices runs your tests across those devices in parallel. Now, the more devices you add, you're going to start hitting your memory and CPU limit. And we're trying to help with that using something called automated test devices. This is a new type of device image which strips out a lot of the apps and overhead and background processes that developers typically don't need when they're running their tests on CI. And this can lead to significant reduction in memory and CPU usage based on your workstation. And here, it's just as easy as targeting that image type, so AOSP-ATD. And we only currently support API levels 30 and 31, but we are adding more along the way. Now, with the additional resources that you're saving, you could either run on more device configurations, or you can even use test sharding to execute your tests even faster. Gradle Managed Devices is stable in AGP 7.3, and 7.4 is in beta with even further stability and performance improvements. And we're continually improving that feature, so please give it a try and provide us feedback. Now, there's one aspect of testing on devices we haven't covered, and what if you need to test on real physical OEM devices, for which sometimes there is no substitute. For that, we're turning to Firebase Test Lab. And in the latest AGP, you can now target any of Firebase Test Lab's virtual or physical devices as a Gradle managed device. So you get the benefits of test caching and seamless integration that GMD provides now with FTL devices. So once you're authenticated via G-Cloud, you just add the new Firebase Test Lab plugin to your build, and then you target the Firebase Test Lab device type in your device definition. And it's just that easy. So please give it a try in the latest version of AGP 8.0. We are continuing to develop this feature, so any feedback is really welcome. And that's Gradle Managed Devices, a feature in Android Gradle plugin we hope makes it easier, more scalable, and with the power of Firebase Test Lab for you. And I think that's my cue to leave. Thank you so much. Whoops.
Okay, well that concludes our talks for today, so thank you very much to all the presenters. There are even more mad talks than we've had time to give live today, and they're already uploaded onto the Android Developers YouTube channel, so I hope you enjoy checking them out. So we're going to take a quick 5-minute break, and then when we come right back, we're going to be having a mad panel. So be sure to get your questions into us, either by commenting on the live stream chat on YouTube, or by posting them with hashtag AskAndroid on our Twitter channel. So yeah, we'll see you in 5.
Compose is clearly the future of Android development. It requires less code and it's easier to maintain. I'm Anton Tananaev. I'm a staff Android engineer at Lyft. Lyft offers ride-hailing, scooter and bike sharing, and other transportation services. Lyft adopted Compose to improve developer velocity, improve maintainability, and remove legacy code. We re-implemented the whole UI framework in Compose that allows us to break down features into smaller reusable components. Compose significantly reduced the amount of code we need to implement the UI. For example, we re-implemented the button component using Compose. It's gone down from 800 lines of code and 17 XML files to just a single Kotlin file with 300 lines. It's a 60% reduction just in Kotlin code, and we completely remove all XML files. Our productivity has significantly increased with Compose. We've seen teams implement a whole flow with several screens just in a few days. This isn't something we could have done before. Compose is built with flexibility to support material design and custom design systems. It makes it easy for us to build custom UI components that support our special requirements. A team is experimenting with Compose to support dynamic changes for the server-driven UI. Developers like working with modern tools, and that's why Compose is a key for hiring and retaining talent. Over 90% of new feature code is in Compose, and we plan to increase that number in the future.
monetization was off.
Hello, and welcome back to the Modern Android Development panel. So we have an excellent panel with too many people to introduce, but hopefully there's some familiar faces, and we have skills in Compose, Jetpack, testing, architecture, more Compose, Studio, lots of great panelists here. So we're looking forward to answering your questions. So once again, if you want to ask questions, you can do so on the live stream by asking with the, in the chat, or you can do it on Twitter by using the hashtag AskAndroid. We only have 20 minutes for this live panel, so let's jump straight into questions, please. Can I get the questions up? Please?
No questions.
OK, there we go. The first one is coming in. It says, is Compose the future of Android?
Can I try? I don't think it's just the future. I think it's already the present. So one of the things that we mentioned in the keynote is if you're just learning Android, start with Compose. If you're building a new app, start with Compose.
Wait, that's what we said in the keynote.
We still believe in it.
Oh, yeah, you were there.
So I'm going to push you on that. Is there any situation where you shouldn't use it?
Yes, we are aware that we're still working on the view parity story, so there might be things that right now you can only implement in views. So those would be the specific parts in your app where you would still go back to views.
And I would add to that, please use Compose so you can tell us what's missing, so we can edit, so you don't have to ask us what's missing anymore.
Unless anyone wants to build on that, then maybe we can go to our next question, which comes in as, how is the Android team trying to ease the learning curve for native Android development? Because Android is hard.
You're DevRel, you can answer that. What are you doing about it?
Well, we're trying to make it easier. We understand that, and I think that's where Jetpack comes from, right? I'm expecting you have some thoughts here as well. That we want to kind of try and take on the things that you all had to do for yourself and try and package them up into libraries that you can use and have our best practices baked into them. So I think hopefully you've seen a lot of that in our modern kind of Android development approach, which is taking on some of that complexity for you. So there's that. I think we've been more opinionated in some of our guidelines. I think for a long time we're famously a little bit, it's up to you. You do what you want. You bring whatever architecture you want. We'll give you the interaction with the system, the platform, but your own architecture or whatever. And I think that's changed. We've become a lot more opinionated, and hopefully that helps people at least have somewhere to start from. We're not saying you necessarily always have to follow the letter of whatever developer.android.com says. Sometimes you'll have to deviate depending on your needs, but at least we give you a bit more recommendations there. That's my thoughts. Anyone?
I'll pile a little bit on. So, the core of modern Android development is really about making it as easy as possible. And it is difficult to build apps across all these form factors. But we're trying to be opinionated about the best tools that you can use, the most productive experiences, from Studio to Kotlin to Jetpack. We also want to build APIs that you don't have to think as much about. So backwards compared across Jetpack. When it comes to building for large screen layouts, trying to build APIs like window-side classes. Things that mean you don't have to think about every dimension of your app. But at its core, it is modern Android development and driving as much consistency about the skills you learn and reuse across all the different form factors, and APIs that make it easy, and tools that really make it easy to build the right apps.
Yeah, something I just want to emphasize that Nick said really quickly is that, so we are very opinionated, and it's more that we're trying to give you solutions. Like, if you don't care, we have a solution for you. But if you do care, it's okay, you can do your own thing, right? Like, there's not one way of doing things. We just want to make that very clear.
By the way, one last thing. Anything we add also adds up to the complication. So there's always a difficult choice between, do you want to add something that makes something easier, or which also happens to make the overall story harder? It's always hard for us to find, like, just because we are not doing certain libraries, whatnot, doesn't mean they're not important. It's just that it adds to the overall complexity, so we try to be very conservative on the things we do.
Cool. Hope that helps. Next up, we have a question saying, any plans to make UI testing easier?
I will ask this person if they've tried out Compose, because it made things much, much better in general. Plans, are we not talking about future? We haven't talked about that. We are looking into screenshot testing. It's a hot topic right now in the community and everywhere. So we know it's kind of necessary for Compose as well. And apart from that, we're improving the guidance all the time, documentation, samples, code labs. We're probably going to have video series and a code labs pathway next year. So yeah, definitely something we're investing in.
Maybe I'll pile on 3 more things as well. We really think about, we want to build APIs that mean you don't even have to test some of the things that you're building for the UI. Again, window-sized classes, great example. Things that we take away the complexity through. And we also think about UI testing really in 2 major forms. The inner loop, where you're doing your build, edit, config. And obviously, we've made investments with live edit there, with the preview that you saw, and being able to preview across multiple devices. And then an outer loop, where you're coordinating with the rest of your team. That's unit testing and testable surfaces. And in the future, hopefully some screenshot testing support. So we do want to make it a lot easier. We know it's not trivial, but we're investing across all the major fronts.
And on the setup side, we have the Gradle managed virtual devices, which, if you do need to run UI tests across a different set of devices, we make it a lot easier now to have your tests just run on the CI without having to manually configure AVDs.
Okay, next question is, are there any efforts to make Compose compiler more intelligent with state reads? It's really easy to accidentally create a poorly performing UI by accidentally reading state, e.g. in an animation.
Yeah, we should ask Leon what he's been doing. Is Leon in the room? No? Do we have anybody who wants to answer that?
So we do have making Compose more clever, sure. But also, we have just introduced the compose tracing, so now you can see your composition in your trace results, and that actually, even my personal app, sometimes you don't really understand why it is recomposing, and now with tracing, that actually becomes very, very easy to figure out why is it, when what changes it starts to retrace. We're gonna add more to that, make it more usable, but I think that part is frankly more important than Compose trying to get more and more clever, because there's limits to that. Versus if we give you all the information on what's happening, you can fix it. So we don't need to do anything.
Yeah.
That worked with views for 15 years. Why not with Compose?
Yeah. It's kind of a hard problem as well, right? Because you sometimes need to read state in certain places, and it's hard to tell when's accident and when's intentional. So I think part of this is the mental shift of getting used to the state read model and understanding how that works and using tools to detect when it's not working. So interesting question. Next up, we have a question. Would it be possible to give any insight into what capabilities to expect soon with the Glance framework, or approximately when it might reach beta? Anyone want to take Glance?
I can take another shot at this one as well. So yeah, the Glance framework, for those who don't know, is really about an abstraction, a composable-like abstraction to creating widgets across multiple runtimes. And really what we're trying to do is extend it across a number of runtimes. We're largely focused on large screens and phones in the first iteration, and we have a relatively stable API that we're building out there. But the idea is with a common programming model, which is actually the central element of modern Android development, if you like. You learn a few concepts that we apply in many different places. We abstract you from the underlying implementation, which is things like remote views. And we want to extend this across all the places that Android runs. But again, we're really starting first on large screen and phone. Large screen because there's so much space for glanceable elements. And of course, I keep on forgetting to say and where with tiles and complications. So that's where we've started today. We've actually got a reasonable amount of work to do to make it easy to build and test glanceable components. So stay tuned.
Cool, thanks. Next question is, are baseline profiles available for Compose or only for XML?
I can get that one. So I'm not sure if the intention of the person asking is to know if they're available by default or out of the box for Compose or XML, or if they're available in general. So let me answer both questions. So first of all, baseline profiles are not tied to any view system. They can work with any part of your app. Any code that you have in your app can be optimized through baseline profiles. And so it doesn't matter if you're using Compose or XML. Now, to answer the other question, is it available out of the box? Compose was one of the first libraries where we actually shipped a baseline profile rule set for the library itself, so for all the building blocks of composable views. But we also now ship baseline profiles with other Android X libraries, so many of the libraries are already covered. Now that said, you do get those rules by default, but in a best case scenario, you will regenerate or generate a baseline profile for your specific app anyway, in addition to those rules coming from the libraries, so that all the code that you write will be covered by a baseline profile. Doesn't matter if it's Compose code, backend code, Vue code. If you haven't seen the talk today, you should watch it. It's all explained how to do it for your app.
Also, Recycle View has, so I'm pretty sure it's got added.
Yeah, a lot of the Android X libraries are embedding the rules. Yeah.
I highly recommend doing it for your app. Like the gains we are seeing is amazing across Google Apps. So one more shout out, please use baseline profiles.
Okay, thank you. Next question is, if sending activity context to a ViewModel is bad practice, how can I request a file URI using file provider, since that would be in the data layer?
Want to take this, Dave?
Sure. I mean, you can get to the context. It just doesn't need to be activity context. Does it require activity context, the file URI access? You just need an application context, which is fine to access from your ViewModel. It's just the hierarchy of, or the life cycle of things. You have like your whole application that lives the longest, and like one layer less ViewModels lives throughout the reincarnation of your activity, and then under that, the activity. So if you pass this activity to the ViewModel, it is bad, because that will stay alive. But your ViewModel also has the application on top of it, which is a context that should be enough to access the file access. So yeah, don't use the activity, use the application scope, and then you're fine.
I think a common misconception here is that you can only access the context from the activity. This is something that we see a lot. So if someone needs to do something outside of the UI, they think of the Android ViewModel because it has a context. So it's important to know that you can grab a context in your data layer. You don't have to grab it from the UI. You can do it manually or using dependency injection for that. So I think that's probably where the question comes from. And actually, the Android ViewModel is something that we just released a bunch of very, very, very opinionated recommendations, best practices for architecture. And actually, we recommend that you don't use the Android ViewModel and only the ViewModel, because it can lead to bad patterns to grab context or use context in ViewModels.
Yeah, just to be clear.
We're not deprecating Android ViewModel, just so you know.
I mean, I think that one of the challenges we have with all the recommendations is that we don't necessarily know how complex your application is or how many other libraries you have adopted. Like, if you're using Hilt, for example, or Annual Dagger, yeah, you just use a ViewModel. But like, if you're not using dependency injection libraries that we provide or other people provide, suddenly, yeah, like Android ViewModel gives you an application context, which is very handy. So that's why, like when Roman was saying, you don't need to follow what we recommend, because it's very hard for us to figure out how much you follow. So always take them with a grain of salt.
Some good context.
Keep the day job.
Any plans to run Compose UI tests without devices?
Any plans? I mean, you can do it today. You can run UI tests on Roboelectric. That's the end of the that's the answer, to be honest. This is something that we want to support more because it makes almost no sense to use a device to run UI tests if they are pure isolated Compose tests. But the truth is you can do it right now.
Or snapshot testing might be, or screenshot testing might help you here as well.
If the question is about screenshot testing, it's an interesting moment for, thank you for that, Nick. So what the community is using right now in host site screenshot testing is a library called Paparazzi. Right now, as of today, I don't think it's compatible with API 33. So there's some forks going on, and yeah, it's in an interesting moment.
Yeah,
but definitely, I recommend you check it out. It's super.
Yeah, that library relies on a few private APIs, right?
Should we open that kind of worms?
Maybe not here, but
yeah. So Paparazzi uses layoutlib, which is part of Android Studio. It's not officially supported, but I mean we're very aware that they are using it. So if we are about to break it, they would know for sure.
So Tor, when will it be officially supported?
We don't talk about future releases.
I tried.
Next question comes in is the App Actions API allows you to deep link into your app. How should this be handled in a Compose app?
So I mean,
Blank faces.
wait, so how we should handle deep links in a Compose app? Is that?
App action, yeah.
Yes.
Yeah, so if you happen to use Navigation Compose, it handles for you. See? That's the answer. You don't need to do
Navigation Compose is the answer, is that?
Yeah, use Navigation Compose and it's handled for you.
Okay, next question comes in is what do we use for TV Android development? XML, question mark?
Maybe I can take this. So I think right now there is lean back of using XML, but we're making now the first steps towards Compose for TV. So I think the first alpha release of Compose for TV was launched a couple of weeks ago. So yeah, we've got big plans for it.
Yeah, I think just to expand on that a little bit, I think our goal is to bring Compose to everywhere you build Android UI. So expect that to be our answer going forward is Jetpack Compose. So invest in learning it now, and it will hopefully extend to all the platforms you care about.
And you just answered the next question.
Oh. Including automotive.
Yeah, so next question is, can we use Compose in, they can't see the next one, so can we use Compose in Android automotive apps?
Yeah, so we want to bring Compose everywhere. We want to unify development, right, to make it easier. It's okay. No, but it's interesting because, of course, we're not talking about the future, so we're not making any promises and all that. But it's also more than UI, right? Like
so when?
Some folks, stop it. But the Compose model, like this highly declarative and reactive model, is very interesting beyond UI. So there are also areas where we'd love to see more of Compose. And I know there have been folks in the community looking at UPY and some of your coworkers who've been looking at using Compose for non-UI stuff or other types of UI. So expect more to come. We just have to take them one at a time.
If I can add one thing, because we've been getting questions around roadmap and stuff. We do have the Compose roadmap, like a high-level overview of it online. What is it? go.gle/compose-roadmap, or just Google for it. And then there you'll be able to see what is in focus for us right now, what is in backlog, and what we've just shipped. So we
do talk about future plans.
We do.
We talk about some of them. If it's not in the roadmap on the website, don't ask. Because you know the answer.
We talk about some future plans.
Yes.
Sean's crying inside.
Sorry, one of the things, just again to stress the point, Compose is important to us because we do want to expand across everywhere that Android runs. You already heard us talk about glanceables before as well. It's not just about the programming paradigm, it's about the toolchain as well. Previews, live edit, everything that you get. So we are sort of investing so that you learn one set of tools, practices, and skills, and basically you get the benefits of those wherever Android runs. So you should expect us to see us pushing down this path more and more. Obviously, Wear 1.0, stable for Compose, just came out recently, and this is true for Wear, everything I just said. So yes, Compose matters.
Okay, next question. Which layer is better for handling analytics events?
Is there a best
analytics layer?
I would say data. I mean, handling events. It depends. You capture them in the UI probably, maybe in the ViewModel, maybe in the data layer. So I don't think there's an absolute answer to that, if I understand it correctly.
It depends. What do you need analytics for?
Yeah, but you use analytics across all the layers. So.
Okay. We have 2 minutes left, so let's go to the next one. Are there any plans on previews working with composables having view models passed as a parameter? I think they already do. I think that works right if you have a parameterless view model.
But it's so nice if you don't.
The recommendation is that you don't. Is that you normally have a stateful and a stateless pair of composables. Do you want
to? What are you looking at, Nick? Me?
You're Jay.
Okay, sorry. Yeah, go for it.
No, I think for previews, we're trying to compose first for the previews, and so we're aware, obviously where a lot of users are still using XML, so we are kind of exploring that as well. But I think if you're using Compose in Kotlin, that's the preferred path. I can't promise anything in the future, but I think it's definitely aware of us that we have to do both XML and Kotlin for some time going forward.
But yeah, It's much better if you don't, if you have two versions of the same composable, one using ViewModel and one stateless, so that you can not only preview it much easier, but also test it in isolation.
Next question is there a method to quickly convert an SVG to a compose path?
So an SVG is more than just a path. There's a lot more information. So a compose path by itself cannot represent an SVG. Now, if you just want the path data that's inside an SVG, I guess it would depend on how you load that SVG. There are parsers that will give you an Android.graphics path, and you can convert that to a compose path, because compose paths are just an Android.graphics.path under a different name. So we have extension functions, so you can go back and forth between the two. If you want to do more than that, you will need another library that doesn't exist yet, as far as I know.
I guess it's a good feature request.
We have enough work. Talk to my PM.
Who's that?
So unfortunately, we've run out of time right now, so I'm going to just close by saying thank you very much to our panelists for answering all of your modern Android development questions. For folks on the live stream, thank you for watching, and we'll be back on the live stream in November at the next stop for ADS, where we're going to be in London to talk about form factors. So thanks very much for joining us.
Hey everyone, this is Miłosz from the Android Developer Relations team. In this video, we'll discuss 3 ways of modularizing your Android application and see how they compare. We'll also talk about 3 properties that you can use to describe your modular codebase. Let's go. There is no single modularization strategy that fits all projects. Due to the flexible nature of Gradle, there are a few constraints as to how you can organize a project. One way of doing so is to encapsulate each architectural layer inside a separate module. The recommended Android architecture describes 3 layers: data layer, UI layer, and optional domain layer. In a typical Android application, we could organize the modules as follows. The data module contains all the repositories and data sources. The domain module contains business logic and use cases. The domain module depends on the data module. The UI module consists of a user interface and stateholders, most likely ViewModels, composables, or views. It depends on the data and domain modules. So how do we know if this is a good strategy or not? We can use the 3 properties of a modular codebase to measure the quality of modularization, and those are cohesion, coupling, and granularity. A module with high cohesion has clearly defined responsibilities and consists of code that acts together as a system. Architecture layers tend to be cohesive by nature. They all have well-defined responsibilities and act as a system. Cohesion test passed. Another characteristic of a modular code is coupling. Coupling measures the degree to which modules depend on each other. Modules should strive to achieve low coupling, meaning they should be as independent as possible from one another, so that changes to one module have 0 or minimal impact on other modules. Let's see how loosely or tightly coupled is our layered codebase. Any change to the UI module will be limited to the UI module itself. However, changing the public interface of the domain module might result in recompilation of the UI layer. Altering the public API of the data module might lead to recompilation of all the modules. In a small codebase, that might work perfectly fine. However, if your modules are growing too large, you might consider increasing the granularity of your codebase. Granularity is the extent to which your codebase is composed of modules. In other words, it's the codebase module count over its size. It's not measured in any concrete unit, but rather serves as a concept. A more granular codebase has more smaller modules. If your modules are growing too large, you might end up with yet another monolith and miss the benefits that modularity has to offer. In a small project, it's okay to put the data layer inside a single module. But as the project grows and your modules with it, you might consider splitting some modules to smaller and more cohesive ones. Another way of approaching this problem is modularization by feature. Imagine a sample ebook application with 3 screens: books, authors, and reviews. We could encapsulate each of those screens in a module and call them feature modules. Each feature module has distinct responsibility, acts as a system, and can be developed in isolation. However, if the book screen wants to show authors and reviews information, that could mean one of 2 things. Either that the book module has to implement author and reviews related functionality, which is already part of other modules, that means redundancy. Or that feature modules depend on each other. This, however, makes coupling too tight and prevents features from being developed in isolation. Seems like both solutions have their pros and cons. How about combining them? By grouping the modules by layer and feature, we increase the codebase granularity. Layers are no longer monoliths, but consist of multiple building blocks. Just like with separation by layer, modules can only depend on other modules from a layer below. UI modules are part of the UI layer and can only depend on domain and data modules. Domain modules depend on data modules only. Data modules do not have access to any modules in the upper architectural layers. This ensures that modules are cohesive because each one is highly specialized and independent. Modules are loosely coupled, so codebase can scale. Modules are granular, so they can easily be reused. I hope this video lightened up some modularization concepts for you. If you're hungry for more, be sure to check out the official guide to Android app modularization and the Now in Android project. Cheers!
Hi, I'm Sean, an engineer.
I'm Diane, an interaction designer.
We're part of the team building Relay, a new UI toolchain for better designer-developer collaboration. Diane and I are going to tell you a bit about the problems we're solving and how Relay can help you. Today, delivering pixel-perfect UI is slow, inaccurate, and complicated. It requires a ton of back and forth between designers and developers. It requires fragmented design artifacts living in files, emails, tickets, etc. And design intent, such as color, typefaces, and behavior, is misinterpreted or simply lost in the swirl of collaboration. We refer to this phenomenon as the handoff problem. It's one of the biggest frustrations we've experienced in our own work, and when we speak to you all, we hear about this challenge again and again. Today, we're excited to release an alpha version of Relay for Android, our first big step towards solving the handoff problem. At the heart of Relay is a simple but powerful idea, a shared model for UI components that allows constant collaboration between designers and developers. We call this a UI package. Using this model, early users of Relay are finding they can go from design to implementation much faster and can update and iterate more quickly. I'll hand it off to my colleague Diane to give you a sense for how this works.
Thanks, Sean. Relay works by translating UI designs from Figma into Jetpack Compose code. And this workflow is enabled by plugins for Figma and Android Studio. Using the Relay Figma plugin, you can create UI packages to be used in Android apps. In Figma, you can mark which elements should be dynamic, such as text or images, and also specify which elements support gestures, creating opportunities to encode behavior and logic. When ready, you can import UI packages from Relay using the Android Studio plugin. UI packages live in your codebase as updatable, inspectable artifacts, and they're automatically converted to composables for use in your project, like any other code. Dynamic elements and interaction handlers defined in Figma become parameters, allowing developers to provide real data and behavior for components. Properties like color, typography, shape, and flexible layout are all carried through. Assets such as images and font files are placed in the right locations, so you don't have to waste time looking for them. As Sean mentioned, Relay provides a shared model for teams to work with. When UI packages are updated in Figma, you can then apply these updates in your Android project at the click of a button whenever you're ready. Many of our customers are using design systems to build their apps, and Relay supports that as well. Component libraries in Figma and their code implementations make it easier for us to design and build at scale. That's why we built the Relay workflow to also capture design system information. Relay supports color and type styles, allowing designs with Figma styles to be translated into Compose themes. This allows you to use tokens and variables like surface or title instead of raw values, which can be really useful when changing the theme of your app. Design systems can also have components, some with code implementations containing behavior that can be hard to describe in a Figma file. In these situations, you can define a mapping between a Figma component and their implementation and code. This allows you to create designs in Figma that reference custom components written by your developers. And Relay for Android Studio will use the custom implementation instead of generating new code. You can also supply properties for these implemented components using the Figma plugin. Visual properties like placeholder or non-visual properties like accessibility labels are piped into the composable as parameter values.
Last year at ADS, we shared a glimpse of what we're building, and today we're happy to announce the open alpha release of Relay for anyone to use. We are committed to a better way of building, where more time is spent answering product questions than documenting them, where small details aren't lost in translation, and where designers and developers have a shared understanding of a product's experience. Relay is an early product, and we'd love for you to use it and tell us how it does and doesn't meet your needs. The best way to get started is to head over to relay.material.io. If you're interested in working directly with our team, you'll be able to sign up to join our research and early access programs there. We'll also be hosting a live stream for a deeper dive on how to use Relay. We're just getting started on this journey and have some big plans ahead of us. Relay is currently an alpha product, and we'll be making regular releases that include improvements to performance, translation, and overall workflow based on your feedback. The handoff problem is something we all face, and we are truly excited to work with you to shape this future. Thank you so much for watching.
Hi, I'm Jolanda, and I'm an engineer on the Developer Relations team. Today, I'll show you how to write your first UI test using Jetpack Compose. We will test this calculator app, and on the way learn about different testing APIs. We will fill in a formula and try to break the calculator by entering an invalid formula. Let's get started. Before we can write any tests, we need to go to the app's build.gradle file and add the required library dependencies. Then, we right-click our Android test source directory, choose New, and create a Kotlin class. We'll call it Calculator Test. In the newly created class, we add a JUnit test rule. This test rule allows us to set the test content and interact with our app inside the test. A test class should always have a test rule defined. We also add a method with a test annotation to indicate that it should be run as part of our test suite. In the test, we use the test rule's setContent method to set the content of our screen to be our calculator. In here, we're in a composable context, so we can call any composable functions needed to set up our test scenario. If we run this test, we will already see the calculator in action. We can also see that our test succeeds. However, it's still not doing much, and we didn't actually check anything. So let's change that. Our test rule contains different finder methods to search for elements on our screen. In Compose, elements on the screen are represented by nodes. So in our test, we can search for a node with the text string 1. In our calculator, this will match the element with the number 1 on it. When you find a node, you can call the different perform methods to perform actions on that node. In our case, let's click on the node. If we now run our test, it successfully finds and clicks the number 1. Amazing. Let's make our formula a bit more complicated and add some more clicks. When we now run our test, it correctly clicks on 1, plus, 2, plus, and wait, clicking the number 3 fails. Why is that? Looking at the error message, we can see that our test found 2 nodes that have the text 3. Not only our button is matching, but also the result of the current calculation. We can fix this issue by creating a more complex matcher. Instead of using onNode with text, we use a more generic onNode. In it, we can use one of the has methods to create our matcher. We still want our element to have the text 3, so let's start with the has text matcher. Then we can use the AND operator to add another matcher. In our case, we can use the has click action to only match clickable nodes. Our button will match this requirement, but our result won't as it's not clickable. Let's change our other matchers as well. Now, although this works, it gets a bit unwieldy. Instead of writing out the matchers each time that we need them, let's extract them into variables that we can reuse throughout our tests. That's starting to look nice, but we still haven't verified anything. Let's look for the node that has a text 1 plus 2 plus 3. We can call different assert methods on it. In our case, let's verify that this node indeed exists. Congratulations! We made our first test. If for whatever reason our formula field doesn't work as expected, this test will fail and you can investigate the issue. Now, we tested the happy path, but let's try to do an invalid action and verify that our app handles it gracefully. We will enter a percentage sign into a formula field and press the equal sign to try to perform that calculation. How will our app react? Wow, it shows a nice error message to tell the user that there's a format error. Let's validate that this format error is shown by finding a node with the text format error and asserting it exists. Then, when pressing the backspace to undo our mistake, we can validate that the error is correctly removed and the node doesn't exist anymore. Now, in this test, we don't really care about the actual string that we're showing. We could change it to validation error or just error, and our test should still work. So instead of matching on a hard-coded string, we should match on the string resource from our strings XML file instead. But accessing string resources means that we need access to an activity, and that's not default behavior for our compose tests. To access the activity, we need to change our compose rule to an Android compose rule that references an activity to start before the test runs. Component activity is an empty activity that serves as a host for our compose content. Now we have a working test that keeps working when the string changes. Looking at this test, there's another property that would be interesting to test. What if we want to verify that the error code is shown in this orange color? There's actually no method to assert the color of our text. To understand why, we have to understand a bit more about the concept of nodes in Compose. The nodes we match in our tests are so-called semantic nodes, and they're part of the semantics tree. Parallel to the UI tree that contains visual information of your app, the semantics tree is an alternative representation of the information on your screen, where each node describes the semantic meaning of a screen element. It contains properties such as text and content description, but also actions such as onClick and setText. It also has a reference to its parent and to its children. The matchers in our tests use these properties to test the semantics of our UI. That's why we also call these tests semantic UI tests. In comparison, you can use so-called screenshot tests to verify visual properties. But that's a topic for another talk. And with this last bit of theory, I hope you learned something about UI testing in Compose. We barely scratched the surface, so here's some other resources on the subject. Now, start adding tests and subtracting bugs.
Hi there, I'm Alejandra Stamato, an engineer on the Android Developer Relations team. In this talk, we'll take JetChat, our sample chat app, and style the chat bubble, customizing the font using downloadable and variable fonts. We'll also make the message expandable when it is longer than a certain number of lines. Then we'll move on to styling the message box. How about giving it a gradient border, a cursor that changes color as you type, or a custom decorated box? So, let's get started. Our designer has given us the design using material tree components. We'll start by configuring the app's typography, which allow us to tweak the material default text styles to match our designs. You do this by creating text style blocks for the style you need to specify, like body large, medium, and small, and changing what's needed. Each text style allows you to style your whole text with parameters like font family, weight, size, but also your whole paragraph, with line height, letter spacing, and many more. So now we have a body large style configured with all these parameters. It's time to style our chat bubble. Here's the design we want to implement. So open the text composable of the chat message and set the style parameter to be materialtheme.typography.bodylarge. And that's it, you're good to go. If you need to customize a specific parameter for your text, for example, color, we can copy the style and customize what you need, similar to a data class. Alternatively, the text composable exposes the most common styling attributes like color, font size, font family as parameters, so you can set them directly. Note that supplying a parameter directly will override it in the style. Next up, the send button. We implement this with a button and a text composable inside. When we run the app, we notice that without configuring any style, the text knows how to style itself as a button. In bold, white color, maybe even different letter spacing. So let's take a look to see how Material Button does this. One great thing about Compose is that you can navigate the source code, and it's all very readable Kotlin code. Inside Button Composable, we'll find a call to provide text style, which creates a composition local, configuring local text style.current to be label large. If we now take a look at the text composable, we'll see that style defaults to local text style.current, meaning it adopts the style configured in the current portion of the composition. In this case, label large from the button. Similarly, the default text color is provided by local content color, based upon the color of the button, so you automatically get light text on dark buttons and vice versa. This mechanism allows Material to style your material components for you across your app without you needing to be explicit if you don't need to. Now, let's customize the chat bubble further. If text doesn't fit our available space, we show an ellipsis and a button to view the entire text. So first, we configure the text with two parameters: max lines set to 8 lines and overflow type ellipsis. Now our text shows an ellipsis if it's longer than 8 lines. And what if we have more than 8 lines of text? We add the button to expand the bubble and see the whole message. To do this, we can use onTextLayout Lambda, which returns text layout result with measurement information captured after the layout phase. By querying has visual overflow, you can change your UI just in time, displaying the More button. You don't emit UI inside onTextLayout Lambda because this call is not part of the composition. Instead, you can change a state variable, triggering a recomposition, and then decide to show a button or not based on the value of this state variable. All right, now let's play with fonts a little bit and configure the chat message font. Let's try the Lobster 2 font, which looks like this. You could bundle the font increasing the APK size, or instead, you can use the new Downloadable Fonts API. This also makes the font available for other apps that may require it. Let's see how to use it. You just configure your Google font provider, pick your Google font and build your font family as a chain of font fallbacks in case any font in the chain fails to load. And set the font in your typography or in your individual texts. The font is downloaded when you need it, without you having to worry about any callbacks. You may optionally pre-fetch fonts to make sure they are available before first usage. To do this, get the local font family resolver in composition and use the preload method asynchronously, which will suspend until the font family is fully preloaded or fails. If successful, the font is cached and ready to be used. Be mindful that fonts might take up to several seconds to time out. Check out the docs to learn more about Font Family Resolver API. If you want to up your fonts game, Variable Font is ready to use from Compose 1.3 for Android O and above. A variable font allows you to take the same font file and configure it in multiple ways or axes to create dramatically different styles. Here we're using a variable font called Recursive, which has standard axes like weight and slant, but also custom axes like casual, monospace, and cursive. How do we configure a variable font in code? You download the file locally and set the axis you need using the Font Variation API. And then you add this font to your font family. So for instance, setting weight, slant, and a custom casual axis like this results in this design. Check out the Font Variation API docs to learn more. Okay, one more feature for our chat bubble. We want to be able to style text wrapped in backticks and style it differently with code format, changing the font family and background color. We've been talking about styling your entire text using text style. Now, annotated string allows us to style parts of our text or paragraph. We start by using build annotated string block. We create a span style with font family monospace and a new background color. We use the with style method to apply the style to the portion of the text we need to style. And finally, we append it to the final text. All right, now it's time to customize our message box. Text field allows for several styling options, including redefining all default colors. Here, we're setting the focused and unfocused indicator color for this text field to be green and orange. You can customize the colors of all text field components like cursor, content, label, icons, and selection colors like selection handle color, and in all their states, focused, unfocused, disabled, and error modes. But what if we have this design here with a full border instead? We can use outline text field for this and configure all colors, just like we did before, with outline text field colors. If you're looking to customize the border of your box even further, the border modifier will help you. Here, we're using a text field We create a border stroke, which receives a brush. In our case, we'll use a gradient brush. Configure the thickness and shape of our border to be cut corner shape. But you might receive a design that deviates entirely from material with custom colors, cursor, decorations. In this case, you can use a different component altogether. So far, we work with text or text field, which are material theme components and sit at the top layer of the Compose architecture. But if you need more customization, you can drop down and use basic text and basic text field from the foundation layer. So here we have a design in which our cursor changes color as you type, from green to red, as you get closer to the end of the line. Basic text field has a cursor brush parameter that will allow you to style the cursor color with a brush API, and you can define a solid color, or in our case, we define a gradient. So as we approach the character limit, our cursor changes color. Lastly, what if we want to completely customize the display of our text field? Here, we're setting a custom background and leading icon. We can use basic text field again and set a decoration box to achieve this. This allows us to add decorations around the text field, such as icons, dividers, placeholders, and so on. We create a row with modifiers like background to configure shape, color, and padding, add the Jetpack icon, and then add the input, which is placed next to it in the row, and we're done. We barely scratched the surface of what you can do with text in Compose. To learn more, go check out our docs and Jetpack's code on the following links. You can also check our text blog post on the new line height API, text field state management, and brush API integration with textile and animations. That's it. I will close this talk with a fun joke, but to be honest, I'm not bold enough. Hope you learned something new, and stay tuned as there is lots coming up for text in Jetpack Compose. Thank you.
Hello there, my name is Yi. I'm a software engineer on the Android Studio team. In this session, I'll share how to accurately measure your app's performance using profilable builds. When an app has poor performance, such as animation jank, frozen frames, and high memory usage, it negatively impacts user experience. And to fix these performance issues, we first need the right tools to measure them. This is where profiling comes in. Profiling helps you find where CPU cycles and memory are spent at the time of inspection. Android Studio offers a suite of profilers to help with the inspection. When working with profilers, there are some things to keep in mind. Historically, profiling an Android app requires a debug build. As Android developers, you are most likely familiar with the debug and release build variants, which are automatically created by Android Studio. The debug build allows you to use features useful for development, like apply changes, working with the debugger or the database inspector. In addition, it also enables profiling tools to inspect the state of a running app unavailable to the release build. Under the hood, the debug build sets the debuggable flag in the Android manifest to true. While useful, the debug build is meant to provide more information at the cost of performance. That's because when debuggable is true, a lot of compiler optimizations are turned off. Let me show you the performance difference. To visualize the frame rendering time, I turned on profile GPU rendering and developer options. Each vertical bar on the bottom of the screen represents how long each frame takes to render. So the shorter these bars are, the smoother the animation is. Here's a screen recording showing you the same app running on the same device. The left-hand side is on the debug build, the right-hand side a release build. As you can see, the debug version has more stuttering frames, also known as UI jank. This means when you profile the debug build, you may see timing measurements significantly different from what your users see in the release build, and you may end up optimizing something that is not the problem in the end. To address that issue, the Android platform introduced a tag called profilable. It enables many profiling tools that measure timing information without the performance overhead of the debug build. Profilable is available on devices running Android 10 or higher. Let's look at another screen recording. This time, the left side shows a profilable release app, and the right side an unmodified release app. There's little performance difference between the two. With the profilable, you can now measure the timing information much more accurately than the debug build. The feature is designed to be used in production where app security is paramount. So we decided to only support profiling features such as call stack sampling and system trace, where timing measurement is critical. The memory profiler only supports native memory profiling. The energy profiler and event timeline are not supported. All these restrictions are put in place to keep your app's data safe. Now that you know what profilable tag does, let me show you how to use it. There are two options, automatically and manually. First, automatically with Android Studio. With Android Studio Flamingo and Android Gradle plugin 8.0, all you need to do is just select the option from the Profile drop-down menu in the Run toolbar, Profile with low overhead. Then, Android Studio will automatically build a profilable app of your current build type and attach the profiler. It works for any build type, but we highly recommend you to profile a release build, which is what your users see. Notice when a profilable app is being profiled, there's a visual indicator along with a banner message. Only the CPU and memory profiler is available, as I mentioned earlier. And in the memory profiler, only the native allocation recording feature is available due to security reasons. This feature is great for simplifying the process of local profiling, but it only applies when you profile with Android Studio. Therefore, it can still be beneficial to manually configure your app in case you want to diagnose performance issues in production, or if you're not ready to use the latest Android Studio or Android Gradle plugin yet. So here's the second option, manual configuration. It takes 4 steps to manually enable profilable. First, add this line to our Android manifest.xml. Then, switch to the release build type or any build type that's not debuggable. Third step, make sure you have a signing key configured. To prevent compromising your release signing key, you can temporarily use your debug signing key or configure a new key just for profiling. Finally, build and run the app on a device running Android 10 or higher, and now you have a profilable app. You can then attach the Android Studio Profiler by launching the Profiler tool window and selecting the app process from the drop-down list. Many of you may wonder if it is safe to leave the profilable manifest tag in production, and the answer is yes. This tag is designed to be usable in release builds to enable local profiling. No memory data is readable by the host profiling tools and the shell process. Only stack traces are readable, which are typically obfuscated or lacking symbols in release builds. And that's it. We've shown you that profiling the debug build may skew performance, and therefore it's better to analyze the release build with the profilable tag enabled. In summary, the release build is for production. A profilable release build is ideal for profiling CPU timing, and the debug build is for the other tasks. To learn more about profilable builds, start by reading the documentation in the Android manifest section and the Android Studio guides. You can also find these links in the description below. With these tools provided by the Android team, we hope you can make your app run faster and smoother. Thank you.
Hi everyone, I'm Manuel Vivo. In this talk, I covered why you should collect flows in a lifecycle-aware manner in the UI, and how to use the repeat on lifecycle, flow with lifecycle, or collect a state with lifecycle APIs to do so. Coroutines and flows are the recommended way of doing asynchronous work on Android. In an Android app architecture, flows are used to communicate state changes over time. Flows are exposed and transformed through the hierarchy until they reach the UI, where they are usually collected. Typically, a ViewModel exposes a state flow to the UI by combining flows from the domain or data layers. Once in the UI, the flow should be collected in a lifecycle-aware manner. Here, you can see the typical lifecycle events that happen in the Android UI. In the light blue areas, the lifecycle is at least started, which means the app is visible to the user. Let's say we are building an app that shows the user location on the screen. collecting in a lifecycle-aware manner means collecting flows when the UI is visible and stopping collection when it is not, for example, when the app is sent to the background. In green, on the lifecycle pyramid, you can see when the flow is being collected. No more location updates are received when the app is in the background. This allows the app to save system resources when the information isn't displayed on the screen, for example, by closing a WebSocket or stopping a GPS location provider. Flow, however, is a platform-agnostic Kotlin API that isn't aware of the Android lifecycle. If you collect for the entire lifecycle, the flow collection will be active by default until the UI is completely destroyed, even when the app is in the background. This wouldn't allow the rest of the app to optimize resources if needed. What's even worse is that updating the UI when it is in the background is dangerous, because it could throw exceptions in some cases. Okay, we've got work to do now. Let's see how we can collect in a lifecycle-aware manner. Nothing prevents you from manually starting the flow collection when the UI is started and stopping when it is stopped, like here with the UI state collection job variable. That's fine. However, doing this manually can be error-prone in activities and even more in fragments, where we must use a default lifecycle observer in the view lifecycle owner to follow the current best practices. We can make this easier. The Android X lifecycle libraries provide some APIs that do most of the work for you. The Lifecycle Runtime KDS artifact offers the Repeat on Lifecycle API, an extension function on Lifecycle and Lifecycle Owner. And it also offers a flow operator called Flow with Lifecycle. The Lifecycle Runtime Compose artifact brings the Collect State with Lifecycle composable function, available as an extension function on both Flow and Stateflow. Let's cover them in detail. Repeat on Lifecycle is a suspend function that takes a lifecycle state and a suspend block as parameters. In its block, you can collect the flow. To start and stop collecting when the UI is visible or not on the screen, we pass in the lifecycle start state. This works because Repeat on Lifecycle automatically creates a new coroutine that executes the block when the lifecycle reaches that state, and cancels the coroutine running the block when it falls below that lifecycle state. In green, you can see the flow is being collected. If you pass in the resumed state, the flow collection stops when the lifecycle post event occurs. As Repeat on Lifecycle is a suspend function, you need to call it inside a coroutine. In activities, you can launch one using the lifecycle scope in the onCreate function. As a fragment and its view have different lifecycles, make sure to use the view lifecycle owner when collecting flows in fragments in the onViewCreated function. Repeat on Lifecycle is a suspend function that will return only when the lifecycle is destroyed, so usually you shouldn't put any code after it. An alternative to Repeat on Lifecycle is the Flow with Lifecycle flow operator. It emits values from the upstream flow when the lifecycle is at least in a certain lifecycle state, started by default. When it falls below the state, the upstream flow collection is cancelled. In a similar way to Repeat on Lifecycle, you use this operator before collecting from the flow in the onCreate function of an activity or onViewCreated if using fragments. If we take a look at the implementation details of this API, you can see it uses the Repeat on Lifecycle API to start or stop collecting the upstream flow, giving a min active state passed as a parameter. It creates a flow using callback flow to emit the collected items until the lifecycle is destroyed. Then, the flow completes by closing its backend channel. When it comes to Jetpack Compose, we offer an API which is currently experimental and in an alpha version. Collect a state with lifecycle is a composable function that collects values from a flow and represents the latest value as compose state in a lifecycle-aware manner. Use it in a composable function of a particular screen like this. Since it returns compose state, every time a new flow emission occurs, the value of this state object updates, triggering a recomposition where the value is read. Under the hood, this API also uses Repeat on Lifecycle. In this case, the lifecycle-aware collected values are used as the source of data for the Compose Produce State API. And that's pretty much it. Remember to collect flows in a lifecycle-aware manner in the UI. When working with the view system, you can use Repeat on Lifecycle and Flow with Lifecycle. And when working with Compose, you can use Collect a State with Lifecycle or the other APIs. To learn more about this topic, take a look at these blog posts that cover these APIs in depth. Hope you enjoyed this talk, and see you next time. Bye.
Hello everyone, my name is Mayank Jain and I'm a product manager on the Android Studio team. In this session, I'm going to talk about how to address crashes in your app very quickly and easily from within Android Studio. High quality apps have happier users. Happier users engage more with your app, which often results in more revenue in your app business. One of the biggest sources of app quality problems are crashes. Apps that crash a lot have higher uninstall rates as compared to apps that are running smoothly. A highly reliable way to find crashes in your app is Firebase Crashalytics. It gives you a complete view in your app's stability with respect to crashes. Firebase Crashalytics helps you to find and fix the most critical crashes before they start impacting a large number of users on production. When using Firebase Crashalytics, this is the usual crash debugging workflow. First, you discover a crash maybe when your users complain or via the Crashalytics console. Next, you switch to the browser, open Crashalytics console on Firebase and look for this crash. Uh-oh, looks like we have a crash in our network handling code. Then, you have to read and understand where the crash originated in your codebase, memorizing the exact method or the line number. And then quickly switching back in Android Studio, opening the file to find that specific line before you forget it. If you forget the line number or need more information, you're back in the Firebase console and have to repeat the process all over again. Context switching is distracting, especially when you're working on those important issues or chasing tight deadlines. So we had an idea. Let's optimize the workflow and make it easier for you to see crashes. Let's bring crash reports from Crashalytics directly inside Android Studio and highlight the exact lines of code in your app which are causing the crash to your users. So we created App Quality Insights in Android Studio. App Quality Insights window has a lot of information, so let's dive in. It shows you the most impactful crash reports from Crashalytics directly in Android Studio. Notice now they are sorted by the number of impacted users, so you know which crashes are most impactful to fix. Clickable stack traces is one of my favorite features of App Quality Insights, as they directly link into app's code base. This helps you to narrow down immediately the lines of code which are causing the crash in your app. And because some crashes can be very device specific, App Quality Insights also shows you the most popular devices on which this crash was observed. If you want to narrow down the scope of crashes listed, you can quickly filter by crash type, app version, or even recency. To catch potential crashes in the code you're already working on, Android Studio highlights the lines of code that are associated with known crash issues. So you can quickly pull up those stack traces in App Quality Insights to investigate. Isn't this awesome? Android Studio Electric Eel ships with the first version of App Quality Insights. Give it a spin and let us know how you feel about it. While this beta of Android Studio is graduating to stable, our team is already working on building the next version of App Quality Insights. So let's take a sneak peek. First, we are making it easier for you to collaborate with your team when squashing bugs. With Notes, you can keep your team updated with the latest status of your bug fix. And when you are done, let your team know by closing the issue right from Android Studio. We are also making it easier for you to prioritize issues. For example, select the production track only to see crashes from the latest stable version of your app you just launched. And Signals, a popular addition to Crashalytics console, is now also available in App Quality Insights. Signals help you quickly identify crashes that are fresh, early, repetitive, or even a regression. All of these new features and app quality insights are available today in the Canary channel with Android Studio Flamingo. As always, your feedback helps us create the best developer tools for you. So please try out App Quality Insights today by downloading the latest version of Android Studio. We cannot wait to see how you use App Quality Insights in Android Studio to build amazing, crash-free apps that delight your users. Thank you.
Hi everyone, my name is Rebecca Franks and I'm an engineer on the Developer Relations team. Does your app look super static and you want to learn how to make it super fancy, super fast in Compose? Let's learn how to add some movement to our apps in a few minutes. Okay, let's go. If you're hiding and showing content on screen, just like we are doing here in the JetChat app, you can see that the timestamp is visible and invisible on click. You might not like how jarring this looks to your users. Instant changes in UI states are painful to experience, so let's make this better. Taking a look at how the text is shown on screen, we can see that it is using just a simple if statement to show or hide the timestamp. All we need to do to improve this is to wrap our changing visible states in an animated visibility composable, and this will magically transform how state changes are shown on screen. Let's take a look. That looks way better, don't you agree? Animated visibility also has a range of different customization options that I recommend reading about in the docs. Next up, this Now in Android screen is showing more text on click of the item card. But the size change looks very static and doesn't transition smoothly between the two states. Taking a look at the code that powers this, we can see that we toggle the expanded state on click of the text by changing the max lines that will be drawn on screen. We can easily fix this jumping state with a built-in modifier. Simply add animate content size to your modifier chain to get an instantly smooth change. And this looks a lot better already. The change in sizes is way smoother. But what if we wanted it to be a little bit more playful, maybe with a little bit more bounce? Having a look at the code again, we can change the animate content size modifier to take in an animation spec. Most animation APIs offer the ability to set an animation spec that we can use to define how the animation happens. In this case, if we are using a spring spec and setting the stiffness to low and adding slight amounts of bounce, we can see that our UI will now look a little bit more playful with this added bounce. Ready for another one? In Crane, the content underneath the Fly, Sleep, and Eat tabs is switching between completely different composables, without any smooth transitions between the content. These changes could definitely do with a little bit more magic. Taking a look at the code that decides what section to show in the purple area, we can see that there is a conditional used to determine which composable to display in that section. Using a when with different composables is a sign that you can probably use animated content to animate between these different composables. So let's wrap this conditional in animated content composable, providing the target state that will be transitioned to. Using the target state inside the animated content composable, we can then switch our content based on that target type. Instantly, our transitions between the different composables is now fading and scaling between each other, which looks a lot better than before. But we can make this even more interesting. Okay, so back to the code. By changing the transition spec on animated content, we can customize how the new composable coming on screen will enter the screen and how the old composable will exit the screen. In this example, we are using slide into container to slide the content towards an upward direction and slide out of the container in a downwards direction. We have also customized the animation spec to set a custom duration and easing function. So let's take another look at what this looks like. How does that look? Our new content slides in from the bottom of the screen and the old composable slides out from the bottom. Of course, this is customizable. Check out the different enter and exit transitions available to you in the docs. All right, on to our next animation example. We have the progress bar in the Jet Survey app, and when you navigate between the different pages of your app, the progress bar shows your progress remaining of the whole survey. At the moment though, this looks pretty bland. Taking a look at the code, we can see that the progress calculation is using state information to determine how far along in the survey you are. In this example, as a user progresses along the survey, the question index will increase. We can switch this variable to use one of the animate as state functions. In this case, we are using animate float as state. These functions automatically perform the animation when the state of your input variable changes. So by passing this animated progress to our linear progress indicator, we will see the progress animates between the first state it was passed and the second state that it is using. It is worth noting that we've used the value on a specific composable parameter, but we could also use the animated progress to change a value anywhere in the composable, such as a modifier's parameters. So let's take a look at the small change in action. Now the progress bar animates between the different survey pages and looks much neater. Now say we wanted to animate something repeatedly, like this custom rainbow border. We would like the colors to rotate around the outline of the image. In order to draw this, we have an image composable with modifier.drawBehind that draws the rainbow gradient brush. This circle is what we will be animating. Now to animate the changes, first we create an infinite transition using remember infinite transition, and we define a single float rotation animation that we want to animate from 0 to 360 degrees. We supply it with an infinite repeatable animation spec that is going to animate between these two values in 1000 milliseconds. So we've defined all the variables, but we aren't using the rotation animation variable anywhere. All we need to do to animate this now is to use the rotation animation value and call rotate in our drawBehind function. This will rotate everything that we are drawing on screen. Compose takes care of updating the rotation animation variable for us and will automatically trigger a redraw as the variables change over time, creating the animation on screen. Now take a look at that rotating rainbow gradient. Adding a simple rotation animation makes the profile pic stand out way more. And that's it. Hopefully you've seen how quickly you can add animations to your Compose apps. For more information on animations in Compose, check out the following links. Right then, I'm off to go move some more pixels around on a screen. See ya!